电脑都还没开呢。 Good morning, fellow speakers and distinguished guests. For those of you who don't know me, I'm Anupam, and I work at the Delft University of Technology in the Netherlands. So today in the morning, I think we have some fantastic presentations in line. So at first, we have a presentation from Professor Kamil Kolos. Yeah. And it is my pleasure to invite him. So Professor Kolos is a FOTA professor of Pavement Engineering in the School of Sustainable Engineering and the Built Environment, affiliate faculty in the School of Sustainability, and he's also a co-founder in National Center of Excellence on Smart Innovations at ASU. He's also a registered professional engineer and has over 35 years of industrial experience and academic experience. And that is why he doesn't need more introduction. We all know him. But he has also filed for several patents, which is in line. And so it is my pleasure to invite you, Professor Kolos. Without further ado.
Thank you, Anu. Bom dia. Good morning, everyone. Let's see if I can get my... Before I get started here, I really want to extend my sincere appreciation and thanks for the co-chairs, Professor Paulo, Professor Elizabeth, and the organizing committee, Professor Foy, for the invitation, kind invitation to be here with you this morning. Talking about a subject about urban heat and such a beautiful day in Gamaleya here. It's a nice, I did not even sweat that much when I walked over here, so just a beautiful day. But heat island effect and pavements. This is the subject for this morning. I come from a United States. I live in Arizona. Well, it's going to be red on red in the Phoenix area. The Southwest is known for its extreme heat. Typically, we have very, very high temperatures in the summertime. And on the right-hand side, you see the landscape of the Phoenix downtown. It can be different in terms of the canyon geometry and the different types of building architecture that we have in town there. So we have experience with heat, and I think this is a timely topic that I'm trying to make some connections to this morning. In Europe, maybe we have forgotten last year, the extreme heat in 2022, that has initiated a lot of concern from a lot of public officials as well as news media. But 2022 was one of the hottest years last year with the fires, associated fires. In fact, just yesterday I heard in Spain they already have the highest temperatures in April, 39 degrees C. These extreme events or extreme heat waves have a devastating effect, of course, on human health, especially in places where we are not really prepared to handle such high temperatures. If you look at the bottom paragraph here, lowering heat stress in urban environment, and that's what hopefully we will be talking about today, is crucial for, of course, to ensure that we have a better quality of life, not only in Europe, but all over the world. Those of you who are not familiar with the urban heat island effect, let me just describe it here as quickly as possible. If you look at the left-hand side, and I apologize, this is in Fahrenheit, 100 degrees, about 38.8 degrees C. This represents the high temperature during the day. This represents the low temperatures during nighttime. You're looking at different types of landscape, anywhere from a desert to an urban-centric to agricultural. And the problem with the urban heat island is the fact that the built infrastructure that we have in urban areas, they will have tendency to absorb temperature during the day. All the concrete, the asphalt, the other construction materials. And they will have tendency to emit that heat during the nighttime. So nighttime temperatures are higher comparing to everything else you see outside the city center. Why? I mean, obviously, these are more of loose materials, porous materials. The heat release rate is much easier and it's much faster comparing to the dense infrastructure that we have in an urban city. So why do we care? I'm not going to go through all this, but it has been documented, for many decades. Increased concern about the health, but also energy demands, air conditioning. the associated greenhouse gas emissions from this, all these mechanical systems, the AC, that can create anthropogenic heat, another source of heat that will add to the complexity of the problem here. If I give you a little snapshot from our campus, we're going to start talking about paving materials or paved surfaces. This is from campus at Arizona State University. Asphalt, concrete, everything surrounding area during the day. It's quite hot, actually. On the scale here, you can see the temperature can go up to 153 degrees Fahrenheit in certain spots. So what happens to pavements when we subject them to these extreme weather events and the high temperatures? If you are dealing with asphalt pavements, we typically have problems with the high deformation. So if we are designing asphalt to be performing within a certain range, and all of a sudden we are exceeding those temperatures, we will end up with a higher deformation, what you see here, the rutting and the shoving that we see typically at intersections. You might see some bleeding or flushing, depending how you define that. Again, this is because of these higher temperature over-densification of the asphalt mix and the softening behavior of the asphalt binder. In my area, this is a big problem, the thermal cracking. You don't even need load to get cracks like this. You can actually design a parking lot, you can fence it, you don't even allow anybody even to walk on it. But the expansion contraction or the temperature cycling that we go through can actually generate some wide thermal cracks, what you see here, especially in areas where you might have day temperatures about 45, 46, 47 degrees C, and nighttime temperature maybe around 28 and 29. So it's quite temperature swing. You end up with a problem with thermal cracking. If you deal with concrete pavement, Portland cement concrete pavements, this is the type of problem we get for these extreme heat. We design concrete pavement, we do the jointing process to sustain or to kind of work in a certain temperature. The biggest enemy for a lot of these materials is this temperature gradients. The high surface temperature on top and the lower surface temperature at the bottom can really create what we call the curling stresses. More curling stresses, more cracking at the joints, and more cracks in the middle of the slabs. And sometimes the expansion characteristics end up with what we call a blow up. So these are the expectation, what you see, or the on pavement or Portland cement concrete pavement from these extreme temperatures. So we have programs that has been, like I said, for maybe 20 plus years in the US. It's called the Heat Island Reduction Program by the EPA, or the Environmental Protection Agency. They address specific 3 areas. What you see here is the urban vegetation. And actually, you do have a very nice example of that even outside the building here, where you have some trees that can provide some nice shading and little mitigation effect of all that heat to be hitting on the paved surfaces. There's a program on the cool pavement or the cool roofs. Again, having a highly reflective roof to reduce the amount of energy in attics has been also successful to a certain degree. And then the third one that they started is looking at cool pavement. What else we can do to these paved surfaces to create a cooler mechanism, especially at nighttime. So in my talk today, I'm going to address 2 specific areas. Hopefully, I will answer some of these questions as we go through the set of slides I have here. How big of a role pavements play in this urban heat island phenomena? And it's quite big. Like in the Phoenix area, the paved surfaces cover about 40–45% of the landscape. Okay, these are highways, local roads, parking lots, and so forth. How to evaluate them, how we have classically done that. What are the driving factors? It's really a complex phenomenon. It's not about reflectivity or one property. It's a combination of many factors that we'll see here shortly. And thermal properties, I think Dr. Fua mentioned yesterday the importance of the thermal properties when it comes to pavement design. We haven't really spent a lot of effort in documenting properly or engineering property or engineering the thermal properties that we need for these pavements. We have different types of pavement, mentioned asphalt, concrete. We have composite pavements, asphalt over concrete, concrete over asphalt. And they all actually work differently in these urban heat island phenomena. So hopefully I'll give you a little bit of our experience with these designs and their characteristics. I'll summarize from our experience, what are the best mitigation strategies for the urban heat island and pavements. And I'll probably mention quick tools, and there are several tools and models out there that actually addresses some of these analysis where you can predict specific designs and how they interact with the environment. Second part, we'll also go very quickly. Maybe focus on materials innovation. I'm kind of excited. There are 4 or 5 other presentations after me here, but talks about some of these innovative materials that can help in mitigating some of these temperature effects. So here what we have, just a documentation, how much of a difference it is. The message in this particular slide, so what we are looking at here is that I'm looking at a temperature cycle over 24-hour period. I'm looking at what we call Sky Harbor, the international airport that we have in Phoenix. Why the airport? Because it's a massive oasis of concrete and asphalt and buildings and everything else. And typically it's a hot spot, as you will see here shortly. And then looking at some kind of park facilities within a city, and then looking at the outside the city in a rural area. So during a day is really the temperatures for all of these are very similar. Again, high temperatures for a lot of these environments might not be impacted by the high environmental temperature that we have anyhow. But at nighttime, we do have almost about, 4.5, 5 degrees C difference, again, between the rural areas and what you see in the city. So the city here in the urban will maintain a much higher temperature comparing what you see in the agriculture or the rural areas outside. This is a nice image that actually attracted me about 15 years ago as a hobby, urban heat island pavement. I'm more of a pavement designer, materials designer, and so forth. But when I looked at these satellite images, here is the Sky Harbor, this is the airport that we have, this is the Phoenix area. There is no doubt pavements are very well seen here. Everything in yellow is the highest surface temperature, almost at midnight, like about 38 degrees C in October in the Phoenix area. That's quite hot. And here you also see some of the mountain ranges that are also characteristics of a very dense materials that can actually absorb the heat and retain it and emit it slowly at nighttime. But definitely the road network is very well seen here. You can see some images with drones, with thermal cameras, again, roofing types, different landscape within the residential areas. Again, roads here are the hottest spot that you see at night in this subdivision. So we don't really have time to go through a lot of these factors and the detailed level in terms of how they interact, but these are really the 5, 6 factors can drive the urban heat island mechanism, especially at nighttime phenomena as I described it. Canyon geometry is the way we design our cities. The different tall buildings, the wind that flows through them, so that geometry can actually affect the mechanism of heating and cooling rates that we have in urban areas. Thermal properties of materials, very, very important. And I'll discuss here shortly again. An example is the thermal conductivity that Professor Fwa mentioned yesterday. Mechanical systems, anthropogenic heat can drive also a complexity to the issue here. The urban greenhouse effect, again, all of these mechanisms can create this little heat bubble, just around the urban city, and in a way it will have that, what we call the urban greenhouse effect. Reflectivity is also very important, having light colored surfaces versus dark surfaces, and it also plays a role, but it's not the only role as part of this. And then the type of evaporating surfaces, if you notice that in the definition of the urban heat island effect, during a day, the city might be actually a little bit cooler than the desert, and for a reason that we have evaporative cooling. We have misters that kind of spray things around restaurants and walkways and so forth. So you might have that cooling effect during a day, but again, not necessarily at nighttime. And the type of, again, the wind flow that actually can help sometimes in cooling things, especially at nighttime. So that's what reduce turbulent transfer of heat within the city. All of these factors are also complicated about the humidity level, what type of environmental condition that we have, and so forth. So I hope you appreciate that it's not a matter of people saying, well, let's just paint everything white and we're going to solve the problem. It's not going to be solved in that simply. So we have thermal properties, fundamental materials of properties. When I have the solar radiation, incoming solar radiation, my heat is either conducted into the pavement, reflected, or I have some kind of convection and emission or emitted heat from that structure. What really controls the mechanism of all these four is these properties of the material. Thermal conductivity, specific heat capacity, how much heat can be held and released, how fast, and that also is driven by the density or the porosity of the material. Here you can see actually near our campus, the reflectivity of plaque pavers, about 7% or up to 35% depending what they are. Concrete typically 10 to 35%. Asphalt is much less, depending on, again, how much of that film thickness have been worn and so forth. We run laboratory tests in our special laboratory to address urban heat island study that we can measure these properties, okay? So density, of course, is very straightforward. This is the ASTM plate experiment to measure thermal conductivity. We don't like it as much because you have to create plates to do the testing, and in pavement engineering, everything we do is cylinders, right? So we created our own cylindrical specimen that have documented, 15 years ago, and we have been using it very successfully. Again, specific heat measurement, thermal conductivity on different types of material. And the idea here is really if we are changing the properties, you really want to capture that value and use it in our pavement design and our analysis. A lot of these properties can go into simple models. I mean, this is on a spreadsheet in Excel that can take all of these information, and you can actually analyze very accurately what's really happening within a pavement structure. If I have air temperature of 50 degrees C, what's happening to the surface, what's happening below the surface, and so on. We have done some studies where we can take such information and we can take a large part of a city block and we can play this what-if scenario. What if I add more parks? What if I change my asphalt roadways to concrete roadways? What if I coat them with different types of material? So again, a simple thermodynamics heat transfer model can actually provide some useful information about the degrees of temperature change that you might expect from such changes. Here's an example of different types of pavement design. Maybe I'll spend a few seconds on this one here. So what we have here is the HMA or typical dense graded asphalt, hot mix asphalt, represented with a red line. You have a 24-hour cycle temperature variation. Then we have a Portland cement concrete, which is usually are much thicker. Typically during the day, they are also lower in temperature quite a bit. But here you can see, for example, in the early morning hours, they are not. They are actually, because of their thickness, high thermal mass, more dense materials, they hold the heat, and the release of the heat is much slower. You end up actually with a higher pavement temperature during the nighttime and early hours. Pervious concrete or porous materials have a great advantage. I'm going to talk about that here in my second part of the presentation. But this pervious concrete design, we have done several of these around campus, and you can see during the day, actually, the pervious concrete is hotter than the Portland cement concrete. And that's perfectly fine because the conduction of the heat from the surface is much less. So pervious concrete actually can have higher surface temperature during the day, but if you look at nighttime, because of that porosity, just everything is released very quickly. So again, it's just a great advantage of parking lots, local roads, can take advantage of that. And you can do the same thing with porous asphalt as well, too. Ultra-thin white topping, it's the same concrete, right? The only thing it is a thinner pavement structure comparing to what you see here. So this is about, 10 inches, 250 millimeters versus a 50 millimeter design. And this typically goes on top of an asphalt. You can see actually it is, because of the lower thickness, can release that heat and actually can serve very well the urban heat island at nighttime as well too. So again, there are different type of designs. These have been validated, measured in the field as well too. But again, these could be run from a simple tool that I just showed you here. Here's the pervious concrete, the first one we have done in the Phoenix area around campus. This is the pervious concrete right here. This is the conventional concrete. We can see the thermal imaging camera during the day. It's actually much hotter surface, even though we changed the color here for decorative purposes. Again, the amount of conduction is much less, and therefore you end up with higher surface temperatures. This is a porous asphalt in the Phoenix area network. This is the thermal image we just saw earlier. When I was looking at this in my early years, I was noticing this is actually this highway, and this highway is the same, interstate highway like what you see here. However, at nighttime, this is much cooler comparing to what you see up here. This is a huge shopping center area and so forth. And basically, the difference between this section and this section, that this has been covered with a small friction course layer, very thin layer, that is able to release that heat and provide that cooling mechanism, compared to the other section, that's basically the Portland cement concrete, the thick layer. So again, just another evidence, and that's really what you see here, is that 90 millimeter friction course that we have on top of these highway structures. What other things we are doing? Okay, there's a lot of move, especially in the last few years. Cities, they like these coatings, decorative coatings, but also they call them cool pavement surfacing to reduce the pavement temperatures, to provide better mitigation to the urban heat island. But honestly, also, they provide good measure of pavement preservation. So we are actually studying the aging characteristics of these asphalt pavements and how these layers are actually protecting the pavement structure, not only providing the heat reduction benefit, but also preserving the asphalt and extending the life of that pavement. What's really nice about these, they can be actually created with different colors. They don't have to be the very light color you see up here. In fact, here's your reflectivity values. So, you can sacrifice the high white is about 68% reflectivity. I can go to a terracotta color for about 23%, still better than 9 or 8%, for example, with the dark surfaces. So there is a lot of different products out there, and they really do a good job in this aspect. Currently, with the City of Phoenix, we have some test sections. We have developments in neighborhoods. We are testing. We're trying to document what's happening to the pavement temperatures and the benefits of such material. Here you can see actually there's a lighter color products. We're shying away from that because of the tire marks. People don't like how dirty it gets. But there are also some, very useful products like what you see here, almost very identical as well too. And again, we are measuring field temperatures, documenting the reduction and so forth, in addition to many other small studies as well too. We measure the thermal conductivity of these materials. We have developed, again, a small little experiment for that. And another expansion contraction experiment, because we feel a lot of these temperature fluctuations have to be controlled and understood better. And that's really what we are doing with these types of setups. I am not sure, maybe the other speakers will talk. This is an area where we don't really have a lot of standards. You will see different organizations having different types of, testing. But nonetheless, if you really have a controlled specimens and you're able to run the test and validate that these numbers, what you're getting, are accurate, you should be okay. And another test we are running that, like what we do with slurry seals and microsurfacing, we're trying to look at the wearability, how durable these are from laboratory point of view in addition to the field monitoring. So again, this is just a simple laboratory evaluation of how fast we can wear these materials. Reflectivity have to be balanced. There's a lot of studies out there. There's a lot of debate out there. Too much reflectivity can really affect the buildings nearby and so forth. So here actually you can see from UC Davis a study on some experimental side looking at asphalt concrete, 60 degrees C. The wall that they have set up next to it and monitoring is about 52 degrees C, where if you have a concrete, which is actually 15 degrees lighter or lower in temperature, and then but the amount of reflected energy or the temperatures can increase the wall by 3 degrees in this case. So again, all of these have to be evaluated and balanced in this aspect. So from our experience over the years, this is a short list of the winning strategies for mitigating the urban heat island effect. Porous pavements definitely have a huge advantage, I believe, whether it's porous asphalt or pervious concrete or any mechanism of introducing porosity on pavement. Smaller aggregate size, again, just because of the ability of that material to not to absorb too much heat and retain it. So the smaller aggregates will be favorable using friction courses, as I showed you. Using light colored aggregates because that film thickness with asphalt eventually will wear out and the aggregate color will show up. Okay, so whatever aggregate color you're using is going to end up with a showing up in this case and provide that reflectivity, the albedo factor. Surface coatings are good. Whoops. And again, they have to be, sorry, I'm just, fingers are too big for this thing here, okay. Reflective asphalt pavement techniques, the National Asphalt Pavement Association, they have used techniques where when they pave asphalt roadways, they will actually come back and they abrade the surface. They do shot blasting where they try to remove that film thickness early to provide the benefit of higher reflectivity. This is one of my favorites, for asphalt pavement, for porous materials, you can always emphasize, well, during the day, everything hot in the Southwest and Phoenix, even your swimming pool is hot. But really what we care about sometimes is the nighttime. So if you're trying to design to mitigate nighttime temperatures, you can come up with excellent materials to satisfy this criteria. Sometimes actually we can reverse the engineering of all of these. Everything I'm talking about heat today, but think about it, you can take the opposite and you can actually take the benefit of providing that heating mechanism during cold seasons or places where we have a lot of ice and snow and so forth. So I think, again, you can promote some of these benefits or the opposite or reversed properties for cold climates. We can look at the cover tree, but be careful. A lot of trees sometimes can hold heat at nighttime, and I have seen that over and over. So too much trees, not. Again, it's really about a balance. You cover everything up, you're going to hold that heat if that heat can penetrate into that landscape. And then the next part here of the presentation, there's opportunities to talk about thermal resistance materials. We have used a lot of crumb rubber, rubberized asphalt in the Phoenix area. This friction course I was talking about has rubber. Rubber is an insulating material. I was asking yesterday about the tires and how they change and so forth. But rubber can provide the porous design characteristics that you're looking for. But we have seen also some reduction in terms of the heat exchange that we get in some of these materials as well too. So taking some quick points here. So I hope that I played enough information here to kind of convince you that pavements really play a big role into this urban heat island effect. We should be mindful of how we design the roads, how we select the materials and so forth. But also appreciate that it's, there is not one pavement design is going to fit all of our city blocks. Complexity of all of these different design factors can play a role and might actually need to be looked at in depth. So daytime versus nighttime, talk about that. And then surrounding areas, I haven't talked much about that, but sometimes you have a depressed highway section. That's a place where you can actually trap heat, where another highway section is at elevation surrounded by fields, can release that heat also much faster and so forth. So I do have 10 more minutes, right? About 10 minutes? How much do I have? I think I started 5 minutes? Okay, let's do it. So let me go through this very quickly, 5 minutes of the material resistance, something that we have been working around for a while here. The question, can we push the limit by increasing the asphalt pavement resistance to extreme temperature variability? And again, I think the 4 presentations coming here later on the session, they probably provide some great knowledge in this area. My answer to this, yes, if I increase porosity or reduce the temperature susceptibility of the material, we can really have a good control of what's taking place. How do we do this? Why increase porosity? I like to show this. I have this machine in my office, coffee. You make an espresso coffee, you end up with this little foam on top. That's porous material right here. This is very hot coffee, and this is a cool foam right there. So again, you can understand the porosity can really help to cool things down very quickly. So I like that, and that's the example I gave earlier with the friction cores being porous on top of the concrete, reducing the temperature gradients. So this is the only equation I'm going to show here today, and it's for a reason. So if I want to reduce my thermal stresses in my asphalt, okay, in my pavement, because of cooling rate, and I can make the argument that I can do it because of the rate between, again, 45 degrees C to 35 degrees. It doesn't really have to be very cold. It's a function of the stiffness of the material, the temperature fluctuation, the delta T you have, and this is a very important parameter that we have ignored as scientists for a while. Alpha, expansion, contraction characteristics, okay? So we actually focus on that parameter. So how do I go back and I can reduce the amount of expansion and contraction I have in the asphalt? This is the inspiration right here. So I was sitting on an airplane, watching how things are made. The aerogel came up. Like, what's aerogel? I had no idea what's aerogel. So aerogel is a very light, not very light, it's a lightweight material, but it has the lowest thermal conductivity you can ever think of. Asphalt, binder, look at the thermal conductivity. Aerogel is very, very low. It's about 0.1 or even less, depending on the material. This is here showing that we use it in construction panel, has a high thermal resistance, as you can see here. You can dip it in liquid nitrogen. It also has very high resistance to the very cold temperature as well, too. So the inspiration came from here that can we actually use this material for our usages in pavements, right? And sure enough, looked it up, 1956, Standard Oil Company in Cleveland, Ohio, they had the patent on the use of aerogel in asphalt and bitumen. Since 1956 until 2018, when we start exploring this, zero work has been done in this area. Why? Because it's not easy to use it into asphalt. The safety, lightweight material can fly. It has certain protocols in terms of grounding equipment and so forth. And we believe that because of all these complexity, everything stopped. Nobody has done anything from 1956. Back in 2018, we were persistent. We want to find a way how we can use it in asphalt pavement. So we found a way how we can pre-coat, we can encapsulate these aerogel particles to use them in asphalt pavements. And we call that the aerogel modified bituminous materials A and BX. It's one of the patents that Anup talked about. We were able to carry that. We have done 3, probably 4 years of research in terms of materials, characteristics, mechanical properties, and so forth. And just to give you an idea about how this material is less susceptible to temperature variation, here you're looking at bitumen binders that we were poured in silicone containers. And then we're looking at a PG 70-10. This is the type of asphalt we use in our area, performance grade. And this is a little stiffer, PG 76-22. And then this is 2 types of our product we're evaluating at 20% dosage. And they were chilled in refrigerator, and they were taken into this chamber at 70 degrees C. And just to give you, comparative results, how typical binders are, melting affected, and how this product is able to kind of withstand or to kind of block the temperature ramping up into this material. The question, if I run this for 5 hours or 6 hours, eventually everything's maybe going to melt down, right? So, but again, here, running for 2 to 3 minutes can provide such benefits. This is the test we run for thermal conductivity, or the expansion contraction, for asphalt mixtures. There are different types of configuration. We selected the cylindrical type of material, but here what we are measuring, and we have calibrated and validated this test process, we measure the expansion, the contraction, and the average value. They're not identical, as you would expect, but typically we'll take a lowest value. You can see here is actually 20% of this product can really reduce the expansion contraction by a lot. In fact, if you want to see that in a plot, in a chamber, here is the air temperature that goes up and down from 20 degrees, minus 20 degrees C to plus 50 degrees C. Here is the conventional asphalt. This is strain development as an indication to how much expansion contraction is taking place. And then this is two dosages, 10% and 20% of this material. 20% of this material, as you have seen with the numbers, almost flat. Okay? It's insensitive to that temperature variation. So, summarize a couple slides here, and I'll end it. So we talk about urban heat island effect and pavements, opportunities in modifying materials to provide that lower temperature susceptibility, reduce the cooling, heating loads, in the winter times as well too, save energy, obviously. It's just another product in the asphalt business industry. A lot of you are very familiar. It's quite large, the asphalt additives, polymers and other things. It's a huge market as well too. And there are opportunities to utilize some of these materials in such designs here. So with that, I have two more slides. I'm going to have just a little bit of a thank you for the opportunity to be here. Some pictures of our plant production and test site and paving and so forth. And if I may just add, in November, coming up this year, November 14th, 17, we have our annual Pavements and Materials Conference in Phoenix, Arizona. And this year is going to be combined with the IRF, the International Road Federation, their annual conference, Roads to Tomorrow. And if you go to this website, you will see we're expecting about 1,000, 1,200 people attending on campus at Arizona State University. I'll be happy to see you and host you there. If you need more information, go to these websites or just simply email me at kalush@asu.edu. So with that, thank you very much for the opportunity to be here.
Thank you for your presentation. That was very interesting. So next, I would like to invite Clever Pinheiro, who is going to talk about review on the incorporation of phase change materials into asphalt mixtures to mitigate urban heat island. Please welcome. Thank you.
Yeah. Good morning, everyone. I need 1 second because I sent my slide. I forgot to put the thank you slide in my slide. Are you changed? Sorry. Yes, I think this is right. Let me show this, I'll work, yes. Restart. Good morning, everyone. My name is Clever Pinheiro, and today I bring to you this work entitled Review on the Incorporation of the Phase Change Materials, PCM, into asphalt mixture to mitigate the urban heat island. This work is divided in the sections. It's introduction to the problem, aim to the resist, very important. What is the systematic review? Very important too. Review of PCM types, result from the systematic review, mitigation of leakage. It's a problem we have when you use PCM. Conclusions and the project information. Of the problem, we have uncontrolled growth of the cities. And this uncontrolled growth is related to environmental issues. And the people need to live in somewhere. And for this reason, growth, the constructions of the buildings, and they need the infrastructure. And this infrastructure is constructed by road pavements, and these pavements are made by mostly bitumen. And bitumen, as a binder, can reach temperatures higher than 60 Celsius degree during the summer. These higher temperatures cause the thermal cracks and deformation in the asphalt, and also contribute to urban heat island formation. Also, another problems we can point with the increase of the temperature, like the elevate of the greenhouse gas emissions, the compromised air quality, the problem with water resources, the altering the ecosystem, and for me, the most important, the reduced the thermal comfort for the people. This work the aim of this work have the objective to research some kind of the materials called PCM, phase change materials, and this PCM is put into the pavement to minimize the harmful effects like of the urban heat island. What we made? We made a research when I saw some kind of PCM materials, and these materials used to decrease the temperature when put inside the pavements. The use of the phase change materials in asphalt pavement has the potential to contribute to a suitable solutions. And like the global temperatures continue to rise due to climate change, the use of the PCM in asphalt pavements can serve as a proactive measure to help cities to adapt to increased temperatures and reduce the risk of the health issues. And how we made the work? We proceed a systematic review. The systematic review is not an ordinary review. We need to follow this topic in these color squares. We need to define the topic and criteria, identify the databases and the keywords, execute the search, select articles by the title or abstract, and after, normally, yes, read and assess the full articles. And after, if the article is not in the subject, exclude the articles. Extract the data, analyze and synthesize the results, and write an article, a paper, a work. A systematic review is a comprehensive and structured analysis of existing literature on a specific topic. This type of approach helps to ensure and understand the subject and identify gaps in the knowledge or areas to require further research. If we follow the systematic review method, the review provides a rigorous and unbased assessment to current state to knowledge on the use the PCM in asphalt pavements for urban heat island mitigation. This approach contributes to the reliability of the results present, ensure that the conclusions are based on the comprehensive and understanding of the existing literature and can inform future research and practical applications. Which topic we choose to make our systematic review? We choose the material, the PAG, the polyethylene glycol, called PAG, sorry. And what problems we have with the PAG? Leakage problems, and we need to avoid the leakage problems. And we have a benefit. It's the decrease the temperature of the pavement. And here we show to you the reference of these authors. We use the P and the other means. And we made this research in a 40 papers, I think. And we identify with the PAG as the most used and its variations. And when the prevention the leakage, we have the encapsulation by the silicon dioxide and the polycramide as the most used. And here you have the range of the difference of decreased temperature of these pavements with the polyethylene glycol. The polyethylene glycol, PAG, is a water-soluble polymer and used to applications for its excellent thermal properties, include a high heat storage capacity and moderate phase change temperatures range. However, it's important to point that when I put these materials in my pavement, we have mechanical problems. Yeah? And here, we have a chart. In this chart, we can see in blue is the pavement without PAG, the temperature, yeah? And in orange, we have the pavement with PAG. And for example, in this example, here we have the difference in 9.3 Celsius degree to, if I compare with the standard pavement, when I use the polyethylene glycol. And the challenger to use the polyethylene glycol, we said to you, is the leakage. Contamination is I think is the main problem with the mechanical problems. And when I use the PCMs in the asphalt, we need to create a kind of shell or a kind of material when I put the PCM inside, and this material will encapsulate the PCM. And in our research, we identify the encapsulation was the most review is silicon dioxide and polycramide pen. And this encapsulation is good in one hand, and like everything is bad on the other hand. The advantages of the encapsulation, it's minimize the risk of the PCM leakage of the asphalt layers, and avoid this PCM reach the soil. In the part of the mechanical properties, the encapsulate of the PCM can help to maintain and enhance the mechanical performance of asphalt pavement. The problems with have to use this kind of encapsulation is probably the main problem is the expensive costs associated to this process. And in some kind, if I use some encapsulation, this material have limitations in the term of the thermal conductivity and sometimes compatibility with the asphalt pavements. So, to conclude, the incorporation into asphalt pavements of the PCM can reduce the temperatures by an average of 2.9 Celsius degree, with some cases showing 9.3 degree Celsius degree, if I compare to the conventional asphalt binders. The use of the PCM can help to mitigate urban heat island formation, acting as a thermoregulator factor. And asphalt pavements with PCM can provide acceptable mechanical performance and improved environmental benefits with further studies also. And here we have our project, research project. And today we try to make the PCM encapsulated in a fiber. Yeah. We use the PAG PCM, the polyethylene glycol, and the fiber have a characteristic is made for acetylene acetate, I think, yes. And it's a waste material provided by the older tissues. And here we have a photograph for this fiber, and here I have a microscope photograph for this fiber. And the principal slide, I forget. Thank you for your attention and enjoy the symposium.
Thank you, Clever, for such an interesting presentation on PCM. So, yeah, our next speaker is Orlando Lima, who will talk about thermochromic asphalt pavements. So please welcome Orlando Lima.
Esse? É isso. Tu vai usar o...
Morning, everyone. I'm Orlando Lima. I'm a PhD student in Sustainable Built Environment of the University of Minho, and I'm part of a research group that developed new abilities for road engineering. And today my topic's related to the thermochromic materials applied to pavements, aiming at the mitigation of the urban heat island effects. So my presentation is divided in the following sections with a brief introduction, the materials used and the methods, the main results and conclusions, the main results and discussions and conclusions. So, urban heat island is characterized for the increase of the temperature in the urban centers. It can have many causes, for example, the replacement of the vegetation for infrastructure. And among these infrastructure can be the conventional pavement, the asphalt pavements that present a dark coloration and consequently a low albedo and a low reflection. So, with this dark coloration, the conventional pavement receives the incoming solar energy, has a low reflection, and consequently absorb high amounts of energy as heat. So, what's the thermochromic material and how they can help to mitigate the urban heat island? The thermochromic material is a group of smart materials that change color when due to the temperature variation, And there is a range of thermochromic material, but in this research we will use the leucodye. That's thermochromic material that below the temperature transition presents a colored state, and above this temperature transition presents a colorless state. And how it can help to mitigate the urban heat island. The conventional pavement, as I told you before, presents a dark coloration, and with the thermochromic pavement, it can reversibly change color, present a high amount of reflected energy, and a low amount of energy absorbed as heat. So, the materials used in this research are thermocapsules, commercial thermocapsules, yellow dye, epoxy resin, asphalt binder, and an asphalt mixture AC10. The thermochromic solution is composed of an aqueous solution of thermocapsules, yellow dye, and epoxy resin in the following amounts. But how does this thermochromic solution works? It can see a little complex. Here is how it really works. But I did a scheme to easy understanding. So, as I told you, the thermocouples below the temperature transition present a colored state, very similar to the color of the conventional pavement, but above the temperature transition, it becomes colorless, and the yellow dye present in the thermochromic solution appears in the surface of the pavement. This is why it becomes lighter and contributes to the mitigation of the urban heat island. So the functionalization of our substrate was done by a surface spray coating in two bituminous substrate, that's the asphalt binder and asphalt mixture. And the following tests were performed in the substrate that I will comment in more detail in the next slides. So the first test performed in the asphalt binder was the Fourier transform infrared spectroscopy. And here we have the peaks of the characteristic bonding, chemical bonding. And here we can see the presence of the most characteristic peaks of the resin, thermocapsules, and dye, and also of the asphalt binder. So here we can see the occurrence of the surface of functionalization. Here we have a very important test, that's the thermal differential, where it was a cyclic variation of the temperature from negative to positive temperature. And we can see here that there is a high color change at temperature above 20 degrees Celsius because of the temperature transition of the thermocapsules. And a very important one is the color reversibility that we can see in the cyclic temperature variation and also in this video. So the following test was performed in the asphalt mixture, not in the asphalt binder anymore. And here, the scanning electron microscopy, we can see, for example, the surface of the asphalt mixture with the aggregates and asphalt binder. And the chemical analysis, we can see the peaks of the main components of the asphalt mixture, for example, silicon, calcium. And here, in the functionalized asphalt mixture, we can see a big difference in the surface. The peaks of the asphalt mixture are less expressive, obviously, and the carbon peak is higher due to the presence of the thermochromic solution. So here we can see also the functionalization from a chemical approach and from the spectroscopy. And here we have another test performing the asphalt mixture. That's the chemical, that's the quick ultraviolet accelerated weathering test. It's an adaptation of this test. And the weathering conditions were simulated here by the ultraviolet and temperature. And immediately after the performing of this test, it was collected the color coordinates and calculate the color changing. So the asphalt mixture with the thermochrome solution has a high change in the lightening coordinate and a high color change. That's a very important characteristic for our intention, that's mitigate the urban heat island. So finally, it was performed an adaptation of the accelerated polishing test. And here we simulate wear conditions in 1, 2, and 3 hours. And in the end of the test, we can still see the yellow color of the thermochrome solution emerging in the surface of the asphalt mixture. We can see also that is a wear condition really strong, so the asphalt mixture is also damaged. And finally, the main conclusions of this research is that there is a surface morphological and chemical evidence of the thermochrome solution in the substrate. The thermochrome capacity was verified, and also a very important one, the color reversibility. There is a noticeable color changing and a high increase of the luminance. That's very important for our goals in this research, that provide a lightened surface to the pavement. The wear resistance was partially conclusive and satisfactory, and there is a potential to contribute to reducing the absorption of energy as heat by the pavement, mitigating the urban heat island effects. And finally, some future research, this study, is to assess the effects of this functionalization in the pavement friction values, study new methods of immobilization of these particles on the surface, not only spray coating, for example, analyze the maintenance of the thermochrome capacity after the mechanical wearing, and assess the surface temperature in the surface of the pavements, below and above the pavements, to check the real gains in terms of decreased energy absorption. And finally, I would like to invite you to check our very recently published article with the complete information of this research, and I would like to thank you for the attention.
Thank you, Orlando. That was a nice presentation on thermochromic materials. So next, I would like to invite Lei Hai, who is not here, I think. Going to present. It says Lei Hai on novel experimental numerical determination of thermoconductivity.
Good morning, ladies and gentlemen. It's my pleasure to give you this presentation. My name is Chu Longjia. That is me from Chang'an University, China. This is the topic today, the normal experimental numerical determination of thermal conductivity of pavement materials. The thermal analysis is very important for different reasons related to the design, construction, performance, and also maintenance of roadways. In the design and the construction phase, understanding how different pavement materials respond to temperature changes is very essential for selecting the suitable materials. And in the performance evaluation phase, by analyzing the effects of temperature on pavement materials and structures, the engineers can optimize their pavement designs to improve the overall performance. And for this one, thermal analysis actually can be used to study the heat island effect of payments, which is the increase in temperature in urban areas due to the absorption of heat by pavement materials. And for the last one, the cost savings. Understanding the effect of temperature on pavement performance can help engineers to develop a more effective maintenance and rehabilitation plans, which can extend their service life and reduce the overall cost. Even if we understand the importance of thermal analysis of pavement, the current theory to study the thermal properties of pavement actually is very short. Why? Because for most pavement engineers, they are not familiar with the thermal behaviors and thermal properties of pavement materials. And also, for many highway labs, they are not equipped to test the thermal properties of pavement materials. And this is the background and the reason why we are conducting our current research. There are two modes of heat transfer taking place in pavement, which is heat gain and heat loss. In terms of the heat gain, the main form is the heat radiation, and in terms of the heat loss, it includes air convection, radiation loss, and pavement conduction. So in our study, we focus the conduction of pavement materials. In the lab, we can measure the thermal conductivity K. It measures the ability of a material to conduct heat. The thermal conductivity K is quantified by the unit area heat flow passing through a unit thickness of material at a temperature differential of 1 degree Celsius. This equation is used to calculate the thermal conductivity K. And this is the picture of the device used to test the thermal conductivity K in the lab. Besides this, pavement researchers and engineers, they are also seeking for numerical approaches to solve the heat conduction problem. This is an example of the numerical approach. Many researchers and pavement engineers, they adopt this microstructure to represent the asphalt mix with this 2D or 3D simulation model. But unfortunately, this approach is not attractive due to the complexity involved to construct this structure. This step can be very time-consuming and tedious. And hence, in our study, we in the process of solving this thermal conductivity problem, we found that there is no need to construct this microstructure. The key factors affecting this thermal conductivity is the volume fractions of constituents of the mix. So in other words, in our simulation model, we only need to represent the volume ratios of each component. And there's no need to simulate the structure of the asphalt mix by simulating the shape, the size, the arrangements of each component. And hence, in our study, we propose a volume-based row column finite model to represent the structure of the mix. Because the mix consists of three different components, namely air, the asphalt, and the aggregate. So each cell in this diagram represents a constituent of the mix, with yellow representing air, the red representing asphalt, and the green representing aggregate. And all the cells have identical dimensions, and it's considered that the heat conduction is the only form of heat transfer taking place in the process. This 2D model is based on the volume fractions of mixed constituents, and it consists of single rows and columns with square cells with uniform unit thickness. And the size of each cell and the total numbers of cells are determined by the convergence study in our finite element analysis. In the analysis, the temperature at plate A of a top boundary and plate B of a bottom boundary is given, which is T1 and T2 respectively. And in the analysis, these two boundaries are completely insulated from heat transfer. So with the relationship given in the box, and also the constituent thermal conductivity of each cell, Ki, the heat conduction problem can be solved by using our 2D simulation model, and also by applying for the Forest law to the overall heat conduction from the plate A to the plate B. The thermal conductivity can be solved, of the entire mix can be solved finally. In our 2D simulation model, the heat transfer, we only consider the heat transfer in X and Y direction, while in this 3D simulation model, the heat transfer in X, Y, and Z direction are considered. And the main concept for solving the problem is almost the same between the 2D and 3D simulation model. So in the process of constructing this 3D simulation model, we need to calculate the percent volume shares of the three constituents of components, and also we need to create a regular row column structure with the same proportion shares of cubes of these three materials. So again, with this relationship and also the temperature at different boundaries, and also the constituent thermal conductivity of each cell, Ki, the thermal conductivity can be solved by using our 3D simulation model to obtain the temperature distribution within the row column structure. And this is the validation for proposed 2D and 3D simulation models. This slide actually shows us the comparison between the thermal conductivity results between from our simulation model and from other researchers who adopt the microstructure method, along with the experimental data conducted by other researchers. And also we can see that the average error between the results of a 2D simulation model and the experimental results is 4.72%. And the error between the results of a 3D simulation model and the experimental results is 4.88%. This slide shows us the comparison between another set of experimental results and the simulation model results. So again, the average error between the results of 2D simulation model and the experimental results is 8.38%. And the average error between the results of 3D simulation model and the experimental results is 8.39%. From the results, we can also see that there's the change of some experimental data points. Actually, they are not. They do not match with the model results. This deviation can be attributed to the errors occurred during the on-site experiments. Because this reason, we fabricate our specimens and test their thermal conductivity in the lab, and use this data revalidate our simulation model. So this is the flowchart for validating our proposed thermal conductivity simulation model. So the first step, we need to fabricate three types of mix A, mix B, and mix C. In step 2, here, we need to perform the lab test of thermal conductivity and obtain the thermal conductivity values for these three different mix, namely K mix A, K mix B, and K mix C. And in step 3, we need to utilize our simulation model, which requires the input of thermal conductivity value for each components, namely K air, K asphalt, and also K aggregate, to obtain the calculated thermal conductivity for the entire mix. To do this, we have to assume the thermal conductivity values for each component first, and use a model to calculate, to obtain the calculated thermal conductivity for the entire mix. This is the step 3. And in step 4, we need to compare the calculated thermal conductivity values for each mix and the experimental results, and adjust the thermal conductivity values for each component by trial and error method until the calculated value match the experimental results within an acceptable range of error. And at this point, we can validate our simulation model. So this is the gradation used to prepare for our 3 types of asphalt mix. And this is the schematic sketch for the lab measurement device used in our lab. This is the test results. So for each mix design, we prepare for 3 replicate specimens. And this table shows us the volume fractions and the density for each mix, along with the experimental results for the thermal conductivity for each mix. And the mix design A and C, they were selected for back calculating the thermal conductivity for each component, namely K air, K asphalt, and K bender, K aggregate. And the mix design B, this one was selected for validating our simulation model. So here, the first step, we need to assume and adjust the thermal conductivity values for each component until the calculated value match the experimental results. And this is the final solution for our thermal conductivity value for each component. We can see K air, K aggregate, and K asphalt. And taking this as the input of our simulation model, and hence we can get the calculated thermal conductivity for the mixed design B. So this table shows us the experimental results of thermal conductivity for mixed design B, and also the calculated results from our simulation model. So from the results, this can again prove our simulation model is correct. So finally, we come to the conclusions part. The raw column finite element model can be used to determine the K values of the asphalt mix, and the numerical procedure is much more practical than physical field testing for pavement temperature monitoring. And the experimental numerical approach can determine the thermal conductivity values K mix without having to measure the thermal conductivities for each component. This one is very important. And once getting the back calculated values for each component, the K mix, the entire mix of the thermal conductivity, can be from the same materials, of course, can be determined numerically without having to conduct any further lab testing. And the experimental numerical approach offers a practical, non-destructive approach for thermal conductivity determination of an asphalt pavement material. That's all is of my slides. Thank you.
Thank you, Longcha. That was an interesting presentation on obtaining thermal conductivity in an innovative way. Okay, so I would like to invite our next presenter, Jiasheng Dai, who is going to talk about assessing the effect of steering and binary eutectic phase change materials on asphalt, thermal stability and durability. Welcome.
Dear colleagues, good morning. Hello, everyone. And my name is Jiasheng Dai from Chang'an University. Currently, I'm a visiting student at the University of Bologna in Professor Sangirogi's team. So today I will discuss with you some of my research on effect of the phase change materials on the thermal stability and durability on bitumen. I will proceed with my presentation from following aspects, including background, experiment design, results discussion, and some concluding. As we all know, as global warming, the temperature of black pavement reached 17 degrees in summer, which posed a big challenge for road engineering. On the one hand, the increased temperature raised the air temperature near the pavement, causing the urban heat island effect. On the one hand, due to the temperature sensitive of asphalt mixture, high temperature environment cause some thermal disasters such as rotting, cracking, and oil founding. So to solve those problems, we can use the phase-changing materials to delay and reduce the occurrence of the pavement temperature. Our previous research have confirmed the feasibility of a phase-changing material as the asphalt pavement temperature control unit, showing the outstanding temperature adjustment performance, improving the anti-rotting performance of bitumen. For this purpose, the thermal durability of phase-changing materials modified bitumen under different aging conditions was assessed. The aging ability of bitumen were evaluated by major rheologic performance and low temperature cracking resistance. Finally, the asphalt bender's fatigue life and temperature adjustment performance were presented. In this work, A00 is the base bender and A1 to A4 is the modified asphalt bender with different phase-changing materials content from 5% to 20%. And the TFOT and POW test were employed to simulate the short-term aging and the long-term aging. POW test time can be adjusted to mimic the asphalt bender's performance during the various stage of service. Firstly, we conducted the DSA to collect the heat flow data of aged bitumen. Firstly, we can see that the upwards peak in the heat flow curves, indicating the PCM gives the bitumen the latent heat ability, indicating the temperature adjustability of bitumen. In addition, even though aging didn't remove the latent heat, but we can notice those peaks. Those peaks moved to left and some degrees in heat. So these changes are presented in the phase change parameters. To be specific, we can see some zero value in this finger. We can see some zero value in this finger, and the zero value of temperature and phase change enthalpy indicated the long-time aging caused the loss of the temperature adjustment ability of bitumen when PCM content is low. In addition, PAV aging also caused the decrease in phase change temperature and enthalpy, which may be due to the polymer network of the bitumen blocked the recrystallization of the PCM. Furthermore, the aging index was calculated to assess the aging performance and showing the finger. We can see from the equation that the aging index represents the area between the aging bitumen master covers and the original master covers of bitumen. First of all, the aging index we can first of all, we can see the aging index experienced a gradually increase with the aging degree increase, and meanwhile, under the same aging condition, the aging index always presented we can say presented parabolic trend with an opening trend with an opening upward as the increase with the PCM content. Then a more aging index value corresponded to a better aging ability. The aging index values of A2 to A4 under 20 hours per was about 44% and 85% and 12% lower than the base bitumen. Therefore, the aging performance of bitumen with high PCM content always better than that with low PCM content. Next, the GR parameters were used to analyze the cracking status of bitumen with PCM after aging. The finger displayed the all GR parameters was saturated in the pass zone, indicating there is no risk of cracking in the bitumen. Thereafter, as shown in the prediction fatigue knife, the bitumen's predicted fatigue knife experienced a gradual decrease as aging at the same strain level. For instance, we can see the fatigue life of A00 to A4 under 40 hours per was about 167 and 3, 2, and 1 times than that of 20 hours per at 2.5% strain level. Even though the fatigue life experienced increase with the increasing of the PCM content. You can see, but this decreased trend was diminished with the further deepening of aging. Those findings shows compared to base bitumen with phase change materials offered a better fatigue resistance because PCM compensates for the age-related loss of the bitumen lightweight components. Next, the different temperature lags could be observed between the temperature curves of the bitumen with PCM and the base bitumen under the same aging conditions. In detail, the temperature difference experienced a gradual increase after aging with increase of the PCM content. There were always a maximum temperature difference of 7 degrees and a temperature lag of 40 minutes between A4 to A0 after aging. So based on the above findings, we can conclude from the thermal stability and the durability two aspects. PCM enhanced the capacity to resist aging, showing good thermal stability, aging cracking ability, and thermal regulating performance. In our future work, I think we can to further eliminate the adverse effects of free liquid phase change materials moleculars. Some necessary encapsulation techniques are feasible. Thank you.
Thank you. That was an interesting presentation. So now I would like to invite the last presenter for this session, Elida Marcalo, who is going to talk about development of photocatalytic asphalt mixture using doped TiO2 nanoparticles. Welcome.
Hello, good morning. My name is Elida. I'm a PhD student in civil engineer here at the University of Minho. Today, I will present this research with the theme Development of Photocatalytic Asphalt Mixture using doped titanium dioxide nanoparticles. This presentation is organized into 6 topics. Scope of research, introduction, objectives, materials and methods, results and discussions, finally conclusions. This work was developed in the scope of the NanoWeb project. The NanoWeb project is funded by the Foundation for Science and Technology, and its goal is to develop smart road surfaces for air clean. This project is led by Professor Joaquim Carneiro as the PI and Professor Elizabeth Freitas as the co-PI. As you know, pollution is a problem faced society and its impact is far-reaching. Road traffic and industrial activities release harmful pollutants such as nitrogen oxides and sulfur dioxides into the atmosphere. These pollutions intensify the greenhouse effects, cause acid rain, and health problems for people. In this sense, finding innovative solutions to control and reduce pollution levels is crucial. Photocatalytic asphalt mixture are innovative surfaces that promote air clean. When a conventional pavement is functionalized with semiconductor to promote photocatalysis, it can be absorbed energy from sunlight and photodegrade toxic pollutants. Asphalt pavements are ideal for this functionalization because they have a large surface area and are near vehicle gases. Titanium dioxide is a semiconductor widely used to promote photocatalysis. However, it is activated in UV light, which consists of only 3% of the sunlight. So, to improve its efficiency for solar applications, titanium dioxide needs to be doped to shift its band gap to the visible region. The objective of this research is developed photocatalytic asphalt mixture with improved efficiency by doping of the titanium dioxide nanoparticles, which are immobilized on the asphalt substrate by successive spraying coatings. The materials used were asphalt concrete 10, titanium dioxide nanoparticles, iron 3 chloride, and Teflon. Titanium dioxide were doped with iron chloride at 4 concentrations, 0.1, 0.5, 1, and 10% iron chloride. The best doping results were applied to samples by 2 successive sprays, the first with dilute resin, and the second alcohol solutions with combinations of titanium dioxide, doped titanium dioxide, and Teflon. The photocatalytic efficiency of the doped material was analyzed by degrading rhodamine B. The nanoparticles were immersed in 50 milliliters of rhodamine B solutions at the 2 ppm and exposed to a lamp simulating sunlight for 3 hours. To determine the photocatalytic efficiency, the maximum absorbance of the dye was controlled as a function of time and calculated from this equation. The water contact angle of the functionalized samples was performed to analyze the wearability and characterized their hydrophility or hydrophobicity. In this test, a small drop of water is placed on the sample's surfaces, and the angle formed between the drop and the surface is measured for 2 minutes. The higher the contact angle, the more hydrophobic the samples. It can remove the water fast from the surface, preventing ice formations, and improve road safety. The samples functionalized on titanium dioxide were analyzed by gas degradation test according to the ISO 22197 standards. In the middle picture, it is possible to see the reactor we have here at the University of Minnesota. The samples were placed inside the reactor and exposed to nitrogen oxides and light for a period of time. The nitrogen oxides concentrations was monitored during and after the light exposure, and initial nitrogen oxide concentrations, dry air, and humidity were controlled. After the test, it was possible to calculate the net amount of nitrogen oxide removed and analyze the performance of the photocatalytic asphalt mixture in nitrogen oxides removal. The photocatalytic efficiency of the test solutions is shown in the graph. The best performance was of the solutions with 0.1% iron chloride. Look at the red line in the graphic with 95% efficiency. However, the solution that showed the best reduction in the band gap was the 10% iron chloride. These two solutions were chosen for functionalization. The graph shows the results of the water contact angle. It can be concluded that well-functionalized sample showed some degree of hydrophobicity, however, on those underlying shots a contact angle between 100 and 120 degrees, which characterizes a hydrophobic surface. For these results, there is presence of Teflon in the functionalization. The best results underlying header shows a 1:3:1 ratio, which means 1 gram per liter of 200 nanometer Teflon, 3 grams per liter of titanium dioxide doped 0.1% iron, and 1 gram per liter of 200 micrometer Teflon. Two gas degradations were performed. In the first degradations, a nitrogen oxide flow rate of 30 cubic centimeters per minute and the dry air flow rate of 300 cubic centimeters per minute were used. The power density of the UV light was 10 watts per square meter, and the initial nitrogen oxide concentrations of 200 ppb. at the end of 5 hours of UV irradiation, the functionalized samples could remove 192 ppb nitrogen oxides. In the second degradation, the nitrogen oxide flux was changed to 90, and the initial nitrogen oxide concentration to 700. At the end of 5 hours of UV irradiations, the functionalized sample could remove 770 ppb nitrogen oxide. The objective of this research was to develop a photocatalytic asphalt mixture with improved efficiency by doping of the titanium dioxide nanoparticles. The best combinations of the titanium dioxide and iron was 0.1% for efficiency by rhodamine B degradation and 10% for best band gap reduction. Better hydrophobicity was observed for the mixture with the ratio 1:3:1, and the promising results were obtained in the gradation of the pollutants. It was possible to remove an average of 476 ppb of nitrogen oxides. The next step in this research is to explore gas degradation using the functionalizations developed in this work. Thank you very much.
Thank you, Elida. That was a nice presentation. So before I open public discussion, I'd like to give a big round of applause for such an interesting presentation in this session. Please join me in hands. Thank you. Okay, so because the presentations were so interesting, I'm very sure that you have some questions in mind. So please raise your hands and I can come to you and you can ask your questions. So who would like to begin?
Yeah, okay. About PCM's phase change materials. I've got two practical questions. One, if you apply them, so whoever wants to answer, it's okay. If you mix it in asphalt, how do you do it in practice? Is it like an additive that is mixed in, or is it like pre-mixed in a bitumen, like a polymer modified bitumen? So that's one. And secondly, does anybody know how much it costs?
Thank you for your question. Who would like to answer?
Good morning again. And in our research, we saw the mixture can mix by dry and wet mixture, and the cost today is development. We don't know because I have a lot of materials, have a lot of options to make the PCM incorporate in the asphalt mixtures.
So, my name is Iran. I'm working the same project. Just to complement, we can include the PCM as an aggregate, for example, like a filler, or even modifying the bitumen. Thus, we have like dry and wet process.
Anyone else would like to add to that comment? I think you also raised about the cost, right? You get that answer? It's anyone?
It's expensive, titanium dioxide. What that we know, for instance, is the most expensive ingredient in the road markings. So I'm a little bit afraid, but okay. I had a question for Elida. I did understand well why you talk about the hydrophobic aspects of the surface. What is the interest of that? I didn't catch that one. Can you explain a little bit more?
So this was a challenging presentation for Elda because it was the first time that she presents in English. So I'd like to answer. Okay? So firstly, considering this test, we can confirm that we have particles over the surface. Because when we apply this material, we increase the water contact angle, you see? And this material should be just over the surface because it should be radiated by the light to start the photocatalysis. And from another point of view, in our group, we would like to have a multifunctional asphalt mixer, that is, with different types of capabilities. So, as I presented yesterday, we would like to apply as well superhydrophobic capability, like anti-icing effects, and also photocatalysis.
Anyone else? Question?
Thank you. I also have a question for the last speaker, so maybe Iran will answer again. It shows very nice results for the gas regulation tests. I'm a little bit skeptical because of my own experiences in that area. But I see, it's unfortunate that you cannot show the slide, but an immediate drop in your so-called phase 2 when there's no UV. So I'm a bit puzzled. Is that because it's only visible light and already has an enormous impact at that region as well? Yeah.
Thank you for the question. In those graphs, we had 3 stages. The first stage, the gas goes through the tester, like the chromatography tester. And then in the second stage, it passes to the sample, and we have that drop. And this drop is related to the adsorption of the pollutants to the surface of the material. And then we have the third phase when we turn on the light. And then we have another drop that is related to the photocatalysis. So the big drop is because of the adsorption.
Thank you. Further question? Do any of the speakers? If not, okay, then I can ask because, yeah, this is not my area of expertise, so I would like to ask Kamil. We were discussing about heat island and we were talking about the pavements. So I can understand the mechanism, that the overheating that it will do on the material itself. But what about if we are applying treatment on the pavement to reduce the heat surrounding area? Will that work? Because I think that the heating will also come from the nearby pavement area, and the fraction of road in terms of the total area that you will see will be marginal. So will that really contribute in cooling down the neighborhood, or how do you say this?
So what you're saying is that if we're just applying, blocking the pavement itself by some of these coatings, but what about the heat being conducted from surrounding sidewalks or other materials? That's probably, I mean, it's a good assessment, but anytime you have a chance to reduce the amount of heat penetration during a normal, cycle, a day cycle, it's definitely a benefit. We have analyzed one pavement section that has a coating that was applied for about 14, 15 years. And the amount of aging that was recovered from the asphalt, from the bitumen, was actually drastically lower comparing to another pavement that actually you get that has been subjected to the same type of environment. So these coatings actually work.
Thank you.
Thank you. Also a question for you, Professor Kalouch, a very interesting presentation. You mentioned a lot of possible scenarios that can help reduce urban heat island effect, but you didn't mention solar collectors. asphalt solar collectors. Is there a specific reason? Because it's too cost inefficient? We're also investigating that. We have our own test setup, if anyone's interested.
So solar like in the Wattway colas or something like this, or you're thinking about solar panels? Oh, okay. So more like, yeah. I mean, I think these had, we haven't really experimented with such mechanical system or embedded systems into the pavement. They have their own challenges in terms of how to integrate them as part of the, from pavement design, the stress concentration. But they're also, it's a good system that they can recover or, absorb some of that heat, and you can actually reuse it in different techniques back in the winter and so forth. But some of the other, I mean, I guess I mentioned the Wattway, the colas. I mean, anytime you have some type of a covering or reducing the amount of temperature penetration on pavements, whether it's on the surface or it's actually parking loss like with the solar, it's definitely a benefit as well too.
Thank you. Any other question? Okay, then I have a question for Alongja. Not a question, but a comment. I think that was very interesting presentation to get the thermal conductivity. But since you are considering random elements, so that could cause a certain source of uncertainty, right? Uncertainty will be there. So do you want to continue that research and finding out the sources of uncertainty because of considering randomness in your elements?
Oh, we need to find more samples to predict this one.
I understood you will continue the research, so thank you. Any other question for any of the presenters? If not, are there any comments on heat island, the topic that we discussed today? Do you have other remarks from anyone? Okay, if no more questions, then thank you. And a big round of applause again for the presentation for you all. Thank you.
Feedback from drivers concerned about what traction
These two.
The keynote and the...
Okay. And Elisabeth, okay. So, good morning, ladies and gentlemen, and thank you again, Professor Pereira, for this splendid occasion of being together and talking about our common topics. My name is Filippo Pratico, and I would like to invite Professor Sangiorgi for his key lecture, please. The floor is yours, Cesare.
Le dici tu? Ma non importa. Okay,
So, Professor Sangiorgi is a civil engineer in transportation since 2000, and he is currently an associate professor at the Department of Civil, Chemical, Environmental, and Materials Engineering of the University of Bologna, in Bologna. His research teams are related to the pavement materials and innovative construction technologies, as well as the use of recycled materials and low-impact solutions in collaboration with renewed research institutes. Also participating in various international research groups and associations such as the RILAM, APSA, and so on. And last but not least, ISMARTI. In the area of pavement materials, Cesare has a link with the Nottingham Transportation Engineering Center and TU Delft in the Netherlands. The Pavement Research Center, PRC in Berkeley, today in Davis, and other worldwide renewed research centers. Cesare, the floor is yours.
Okay. Thank you, Filippo, for your kind presentation. I thank also Professor Pereira and Professor Feite for inviting me to this great event that I'm really enjoying. So today I'll try to be quick. I have my chronometer here. And basically I will speak about some of the solutions I think are relevant for today, new kind of surfacing. Some of them you already seen them. Some of them already presented. But I would like just to talk them quickly again. The first one, as you see here, is impact-absorbing pavements that has been developed in my university. And then we talk about the use of PCMs, which was a key topic in the previous session. And then we go down to microsurfacing, in particular those that incorporate some rubber. And then we move to recycling asphalt, which is not a new thing, but you will see that in this peculiar approach, we have a new machinery that can do 100% recycling on the surface. So the first topic, just to mention the award that Christina got. This in Safer Project, my PhD student, you see her being awarded as a winner of the road transport mode back last year in Lisbon at the TRA. That was a very nice moment for her and for us. What it is, it's basically something that came from playgrounds. We thought, why not doing something similar to playgrounds and transfer it to pedestrian footpaths and bike lanes. And basically, the reason is that we want to save hips and bones and heads, schools for people that falls. And we do that by recycling a lot of rubber. How much rubber we recycle? Basically, we have a lot of rubber into the mix, about 50% volume. And we try to make a mix that is also sustainable in a way that we use cold procedure, cold emulsion, but it can also be done hot and warm. Other key points are, of course, the shock absorbing capacities. This material is able to increase the shock absorbing capacity about 6 times compared to standard asphalt. Of course, we also try to see all the other issues related with the use of such an amount of rubber, and we are still working on it. We have a relatively high level of TRL, but we have another project that will start in November to keep on with this topic. Just to give you a few hints of what has been done, here are the materials. Of course, we have rubber. This is a very specific and selected rubber. We use the one from Ghanaian. It's also present here, I think, in Portugal. Of course, we used all sorts of binders. We also use some transparent synthetic binders. We use aggregates, standard aggregates, but we are thinking to use, and we also did some tests on the use of wrap. Here is more or less what was the plan, and we accomplished it, and that should work. Here is the softness of the pavement. We also have some kids playing on it. And the overall results for the research were really positive in a way that the material was strong enough. We also tried to do some durability tests, including aging and prison cells. And we also included, of course, some uniaxial compression tests to see the relaxation capabilities of the material. Considering the potential leaching of these materials, we went with the friends in Coventry and we did some DSLT tests, which you will see they were all positive. We also did some modeling. Actually, this was done with the help of friends at the KTH that modeled the impact of 2 real accidents with a head with or without a helmet. In terms of results, of course, we found out that, sorry, I didn't thought it was noisy. So this is the fake head. This is called HIC, is the test that reveals what is the critical falling height of the material. And we saw that it's feasible, so we can mix it, we can do laying of the material. Also in the trial site, we saw it is possible to lay it with a normal paver. And we saw that as you see here in the lab, also in the lab, starting in the lab, sorry, we saw that the increase of height, if you look at the right side, the brown sample is asphalt. If you move to the left, you get thicker and thicker layers, including more and more content of rubber. And if you see the critical falling height, it's going higher and higher. So we go above 1 meter. This is also the result of the simulations showing that basically there is a good advantage on the use of these materials, and specifically decreasing the concussion and the skull fractures. This was based on on a simulation of real accidents that were reported, and they were modeled on the literature. In terms of DSLT test and leaching, we saw that there is indeed some leaching, like all materials, but we understood that everything was below the limit, the threshold limits imposed by the colleagues that, the standards in the country of the colleagues that were doing the research. And we also saw that it could be possible to do some pre-washing of the material in order to leach most of the pollutants before mixing. And also we were thinking about some coating. In terms of field trial, the one you saw before, these are the results. We paved a small section of pavement, and we ended up with height measurements, and we saw that basically we have 6 times higher critical falling height compared to the asphalt. So these are the results for this material. It's very promising to me. Of course, it has a lot of potential issues, and we're trying to sort them out. I believe that with some 3 years, again, more research, with this PhD that is starting in November, I think we will sort them out. And hopefully in the next event, I'll be able to tell you about a full trial site, larger trial site, instead of few square meters. Moving to the next topic, there was a question today about PCM and how to incorporate PCM in asphalts. And a few years ago, we did a research on using lightweight aggregates to be impregnated with PCM materials, and that was specifically made to tackle the issue of ice on pavements. We saw other presentations from our friends from here. And you also saw the presentation from Jianseng Dai, who was talking about the use of PCM in bitumen to tackle the issue at the higher temperatures. So PCM can be obviously adapted in terms of temperature if you want them to work at low temperatures or intermediate or high temperatures. As for the encapsulated balls, that was a tricky topic because we started thinking about how to incorporate the PCM into the pavement, and then we ended up with this impregnation of LICA, standard lightweight clay, and that incorporated that it was really good for impregnation, but the problem was how to keep the PCM inside. So we ended up with some coating. We saw also from the literature review from one of the presenters this morning that coating is sometimes something that you cannot avoid. And in this case, we coated with some resins. I don't remember the details of the resins, but you can see them in the paper below here. This was 1 to 2 degrees Celsius changing material, and actually we saw it with DSC test. It was really effective. So if compared to standard lightweight aggregates, we saw with DSC that there was heating and cooling effect, and the temperatures was within the range of the PCM material that was confirmed. We also tried to stress the material in a way that cycling for 5 weeks, this up and down of temperatures, and we ended up to see a slight change in temperature change, which was not too much in our opinion. So we think that the stability, thermal stability of the material was confirmed. People would argue about the effectiveness of the strength of the material, how much they can withstand loads in surface layers. So we did some PSV testing. We did other tests. I didn't include them here, crushing and et cetera. Consider in Italy we have special pavements made with LICA, so lightweight aggregates. So we took that standards and we compared with our materials, which are normally better than those. In terms of temperature, of course, it depends on the PCM. I mean, we don't have to think about PCM as a solution, universal solution can do everything depending on the temperature. So if you have a very cold climate, there's nothing you can do against freezing temperatures. But in Bologna, we have temperatures that are around 0 in winter. Sometimes you get to -4, -7, if it is a harsh period. So what we're trying to tackle is to avoid pavement to go down and freeze at night. And so no need to send people out with the salt or other additives on the pavement. As you can see here, the blue line, the blue curve is actually the change in temperature of the PCM LWAs. And if you see compared to porphyry aggregates in a cold conditions, they were above 0. Here you can see the actual effect. If you look at the picture on your right, after 50 minutes, you see that the porphyry was quite cold compared to the LWA with encapsulated PCM. Of course, we can do this with other aggregates, but this is an example just to show you the effectiveness of the material. Here is also the test. We were simulating a cold night. We took the data from the airport station, climate station, and we simulated the cooling night into the cabin. And as you see here, again, the blue line, it's slowly going down compared to the other ones. One is the temperature, ambient temperature, and the other one is the aggregates. So that gave us enough time to probably to reach morning and wait for the sun to rise again, and hopefully don't send people out to spread salt and don't risk accident or similar. Here it's what Jan Seng was showing you today. It was a pity that he was before me, but I took some of his slides, and basically I'm showing you how the PCM was incorporated in the bitumen from Jan Seng, just to show as an alternative use of PCM in binders in this case. And of course, the effect is this, mitigating the temperature, either higher temperature or lower temperatures, depending on the PCM that you use. This is how Jan Seng was producing. I don't think he mentioned this morning that he is incorporating the PCM into expanded graphene, small particles, and then he grinds them down to a powder, and this powder goes into the bitumen. So this is how it was incorporated. Was it effective? Yes. You see here the difference. You have the two inner lines are the bitumen, neat bitumen, and then if you start adding PCM-A or PCM-B to this SBS-modified bitumen, you see that you have an effect in heating and cooling. And in this case, temperatures, as you see, are well above 0, so we're talking about summer temperatures. He also did some, of course, interesting experiments back in China, and he already showed you this test configuration with the use of thermal camera, and I think you saw this image today, but just repeating it, I don't think he told you that the difference, as you see here, the average of the standard binder is about 52 degrees Celsius, while the PCM is well built. To see the difference, including 20% volume or 40% volume PCM into the binder. And you see that there is a 4 degrees Celsius difference in this case, which might not be considered a lot, but it is indeed effective. Same you see here. So the red curve is showing you the difference in temperature on samples that were exposed to direct sun. Okay, so PCM-wise, I'm done. I think it's a good topic to work on, and we saw that it's emerging, and I believe that we will see more and more in the next few years. Of course, costs are a problem, but Jan Seng was telling me that if you made the PCM on your own, and he was able to do them mixing some fatty acids,
they are not very expensive. I think you bought on Alibaba, right? Right. So it seems they are not that expensive. It all depends on how much you need. The next topic is related to a work that we did some years ago, but I think it's still effective, and it's still in my drawer. I would like to take it off again and keep on working on this, because I think it's a good topic, the use of microsurfacing. Because microsurfacing, we know them as a surface treatment to improve the skid resistance, especially as a maintenance intervention. But in this regard, I would like to stress how they could be converted and seen as a multifunctional material. In specific, we use rubber in them, powdered rubber. They are good because, of course, they are cold mixed and cold laid, especially, at least in Italy. Their first purpose is increasing the skid resistance, of course, and then we go to aesthetics, depending on the type of aggregates you have, and then, of course, on the acoustic properties. The acoustic properties is something that Elisabetta has studied, and she told us that if you have a positive texture, it's hard to get a reduction in noise. But in this case, we tried to have a specific granulometric curve, and we added the rubber in order to reduce the stiffness of the surface. So these are the materials that we used. As you see, there's rubber, there's emulsion, there's latex emulsion. And we did all the tests, ISSA tests. My friends from US will be familiar with this. Torque test, falling ball test, wet abrasion test. And we selected some of the materials here. You see, we selected, I'm sorry for the names of the mixes, K, Mod, BBB. It was a student, and I kept them like this. But what you see a small P means rubber. Polverino in Italian is rubber. We did a number of trial sites in the area of Bologna. These are places, and these are the sites. We basically selected the 2 lanes, and then we made 1 lane with rubber and 1 lane without rubber. And we went there before, after, to do tests, many tests, actually. We did tests on the surface. Of course, we want to assess that the microsurfacing is effective, and it was certainly effective in terms of skid resistance, as you see here. We got an improvement of PTV and improvement in MTD. But we also did some tricky SPBI measurements. I would say tricky basically because we made a fake traffic in those areas. I'll show you in a bit. For those of you who are familiar with statistical pass-by method, it's a time-consuming method. You need a lot of cars, you need a lot of passes, a lot of trucks, and they are supposed not to be overlapping. So what we did okay, this is how it works. We did a fake traffic mixing cars of our students and my PhDs and my car. At the time I had a Prius. And we also hired a truck, as you see, and we were circulating up and down on the road to simulate the traffic. So we did a lot of passes, a lot of noise measurements. Of course, we're trying to mix also the order of cars and use different cars in a way that it was similar to a real traffic. Just to remind you that if you have a reduction of 3 decibels in noise, then you have, it's like if you double the distance from the source. What we got, it might not be impressive, especially if you think about the errors of the methods, but at least we got some reduction compared to the original pavements. I remind you that in this case, the original pavement were sound, so we were not testing pavements that were failed. The pavements were good, so we just went there to overlay the material. And we got some decibels reduction, which might not be too much compared to porous asphalts or AA porous asphalts, but for a 1 centimeter material, it's good enough. And I believe that we can improve that also using other aggregates. So unluckily, in one of the trial sites, we had a drop in temperature the night before, and what happened, there was a loss of aggregates during the completion of the pavement, and there was no actual effect. So we had a more than 10% loss of aggregates on the surface. So we went there anyway to do the measurement, but it was kind of useless. Just to conclude on the microsurfacing, and then I will jump into the last topic. I would say that I am happy with pulling the microsurfacing out of the bag again as a valid material, not only for maintenance, because we need to think of this material as a potential solution also for new pavements. They are good for crack sealing in case you have issues of cracking. Of course, you cannot fill huge potholes with this. You cannot solve higher distresses on the pavement if there is major failure in the foundations. But what you can really do is try to tackle, apart from the skid resistance, other problems, and possibly make politicians happy with a black surface. That's what happens, at a less expensive cost, because the microsurfacing are normally cheaper, at least in Italy, than 4 or 5 centimeters of asphalt. Of course, including rubber, including recycled materials, it could be a good solution, especially if you also try to address the acoustic problem. How long the acoustic will last, God knows. We haven't done additional tests on this, and this is what I would like to do in the future. So I still have 10 minutes, I think, but I'll be quicker for the happiness of the organizers. Here, I'm going to talk to you about a new technology that is emerging now. It's a brand new thing that has been released in these days in Italy. We joined the company that was developing this solution. They were addressing the problem of surface maintenance, specifically of small sites like this one. That companies usually hire a small truck, and they put everything on the track, paver, well, not paver because there's no paver in this case. They put compactor. Normally they have frog compactors. They put hot asphalt. So they go in the plant in the morning, they buy the asphalt, like few 1-2 cubic meters of asphalt, and then they start going around in the city to close potholes and to fix pavements like this. And of course, when it comes to late afternoon, before they stop working, the asphalt is cold, meaning that there's no way that you compact it in a proper way. So in many cases, you get a good work, like the one on your left. In some cases, you get very bad works, which will require the company to go back and fix it again. So there is a company in Italy that is producing milling machines, and they ended up with saying, okay, why don't we do a solution with a machine that is attached to a skid loader, and it's able to do surface recycling. So you all know about deep recycling with big machines. So where you recycle everything. In some cases, you use foamed asphalt. You can use emulsion. In this case, inside the machine, there are 2 drums. I'll show you in a bit. And it contains also liquid chemical additive. Let's call it a rejuvenator, but it's not only a rejuvenator. Of course, you can try different materials in this case. We are now trying at least 7 different Italian products to be used with this machine. Here you see how it works. You can also, of course, couple lanes, and not lanes, but this is 1 meter wide. So you can couple 1 meter to 1 other meter. Of course, you need to be careful with the slope of the pavement, but you can also use the paver. In case you have larger sites, you can simply treat the material on site and just pick it up and put it in a small or large paver and then lay it, because material is cold. Sorry. Okay, this is how the machine works. And just to show you, there is a a milling drum in the front, and there is a crushing drum in the back with a sieving grid. You can change the sieving grid, you can change the speed. So we ended up doing a number of small sections, and this was it's a dead-end road that we basically used as a trial site. We used many other roads. We did at least like 30 different sites using different asphalts, and in order to understand how the milling machine works. And it was surprisingly good into producing a granulometry, a gradation that was always quite good for the compaction. Of course, you look at the end, you look at what you get in the end. So we were positively impressed by the final condition of the pavement. That was looking exactly like a hard asphalt. We also did some sand patch and pendulum test, just as an immediate test to see the condition of the surface. So we were also impressed by the fact that there was full bonding between the layer, the treated layer, and the bottom. I was expecting the top part to fall apart, to be, detached from the bottom, but it wasn't. So, and we saw this in many sites. So meaning that either the additive or the treatment does its job also towards bonding. Yeah, this is basically the last slide. Again, this is a technology for surface materials. It's one of the technologies available. I believe that this it's interesting because you can actually use it in small sites. Next month, we're going to do a larger section, so it's more or less like this podium here, using a paver. So we will see if it works well also in larger conditions. Let me take this 2 minutes, if I can, Filippo, just 2 minutes. I think I still have 5 according to my mobile here, to ask you to disseminate this. This is a new Marie Curie project called Green Nexus. I am coordinating. We just started the project, and we are looking for 10 PhD students, good ones. As you see here, we have a bunch of people, a bunch of companies, institutions, including Wageningen University, RISE in Sweden, Athens University, Istituto Tecnico Lisboa, which is not far from here, Teixeira Duarte, again, a company from Portugal, and of course, all the other ones. If you have time, please have a look at the links. You can just Googleize Green Nexus, Marie Curie, and you find the Euraccess call, and you also can find the landing site of the project. We are still working on the website. It's still on a beta version, but it's my fault. This, of course, doesn't deal specifically only with pavements. Only 4 projects out of 10 are somehow dealing with pavements, and especially 2 of them are located in Bologna. The first one is continuation of the impact-absorbing pavement, and the other one is on the biobinders with the University of Calabria and Iterchimica here. Okay, I'll thank you very much indeed.
Thank you, Professor San Giorgio, for the amazing and interesting presentation. We are perfectly in good time. And now I would like to invite the next speaker, Professor George Way, who is going to speak about new technological innovations in asphalt rubber? Professor, the floor is yours.
You want to get it going? My colleague here. Well, hello, everyone. And, I'm sorry, what do I have to do next year? I already did something wrong already?
No, not yet.
Okay. All right, not yet. I like the way you said that. That's very good. You know, it's interesting, this title, by the way. It says New Technologies, and you got a guy up here 75 years old. So I will try to be as new as I can be with all of you who are all alert and awake. And you should prepare yourselves because this is a joint presentation. I'm the easy part, and then my colleague, George, he is going to give you a lot of in-depth technical type stuff, and there'll be a test later, so pay attention if you will. Well, a long time ago, when I was a lot younger, about 1970, I went to work for the Arizona Department of Transportation, and this gentleman, Charles McDonald, who I knew very well, was inventing something called asphalt rubber, which I have to say is one of the most controversial subjects I've ever been around in my entire life. There seem to be people who either like it or, let's say, they dislike it. So we've been on this thing for a long time, I have, and so I've seen it since 1970. I've seen it through a lot of different phases, and I'm not going to bore you with all of that detail, as you might say. So what is it? What did this gentleman develop? He developed a product that you could actually put approximately 20% ground tire rubber and 80% of asphalt, and you could use it as a seal coat, you could use it as a crack sealer, you could use it in hot mix, and a tremendous amount of research has been done with that, and there's a myriad of papers on this, which both myself and George could lead you towards in a pleasant reading. Okay, what was his big invention? His invention was a way of putting these things together and creating a binder with, in my mind, superior properties at that time to just regular asphalt. Now, in the meantime, you know, a lot of the people have been developing superior asphalt products. So this is a big business in many ways. So what we're going to talk about today is not all of the long-term history. We're just going to sort of get you up to date. This is a family of products, starting out at the top with asphalt rubber, which has an ASTM definition, for that matter. And then over the years, there's been a whole family of products that have been developed. Now, in the beginning, there was another product which was called a dry process. It never really caught on tremendously. It was just to put the rubber in there, put it in with the mix, and pave it. At times it worked, and at times it didn't, but it didn't really have a mixed design process that went along with it. It had many other handicaps. But it had one thing that was really good. You just put it in there. It's a dry powder. So what are we talking about today? We're talking about a new type of product, a new type of family product, which George is going to talk about extensively, which is a powder. It's an asphalt rubber powder, and you just introduce it, but when it sees the hot aggregate, it changes, and that's the new innovation. So with that, prepare yourselves, because like I said, there'll be a test later for George.
Thank you, George. It's a great pleasure to be here today, especially with my old friend and partner, George Way, and in this venue where I started knowing Professor George Pais and Professor Paul Pereira many, many years ago. And they introduced in this university one key test, the 4-point bending test, which we'll be talking about later, but it started here at this university. So we'll be talking about reactive and activated rubber. Basically, we're trying to do the same thing as McDonald did, which is react the rubber, but leave it at a state where it's still a powder. So inside the rubber, you have the bitumen that will suck otherwise, so never think about doing dry, because in time the rubber will suck it in, the bitumen, and will cause raveling and loss of fatigue life. So we call it the semi-wet method because it's the advantage of the wet method and the advantage of being a dry product. Therefore, we don't need anymore the extensive and not friendly process of waiting 1 hour to cook the rubber like McDonald's did. So it's like instant coffee. It's ready to go. Just put it in the plant and use it. What we are presenting here is not invented yesterday. There are many, many, many roads already with this. There's a list, I can provide you with many. But one key project that I think is worthwhile mentioning is one that was done in Mexico, and where 80 kilometers of a divided highway, in which they wanted to use 18 centimeters of conventional mix to resist the reflective cracking that those slabs would impose. That was the standard in Mexico, according to the AASHTO method. So we produced an alternative in which we only placed 6 centimeters with a very high content of rubber, just like what they do in California. Still nothing new here. The concept is the same. Also in California, they reduce the thickness when the mixes have asphalt rubber. So in this case, we have a 9.4% binder, and we call it binder bitumen plus RAREX, okay? So the nice thing about this product is that it's pre-reacted. You see, the green curve is how the viscosity changes in time. It pretty much doesn't change in time. So it's ready to go, stable, as opposed to the red line would be what happens when you cook crumb rubber on bitumen. Viscosity increases. And you can see on the right, for those that are with the PG methods, that the PG grade of these mixes reaches values that didn't exist before. 120 PG grade, it pretty much guarantees that rutting will never occur in this pavement. So it's, this is the key graph I need you to remember, okay? Why are mixes with reactive activated rubber so good? Because as you increase the percentage of the crumb rubber, look what happens of percent recovery. It reaches very close to 100. What does it mean? It means that this is a binder that at 64 degrees C, this is hot, okay? It's pretty much an elastic. So you have an elastic binder, which guarantees you that, you know, the truck goes, deforms it, and recovers, deforms it, recovers. And in terms of fatigue life, it guarantees you that you're going to have a performance like a rubber and not like a viscous material. This is similar performance, and the important thing is to note as the softening point also increases tremendously with the amount of RAR in the binder. Now, I'm going to be focusing back on fatigue, which is something that I consider very important. And this is now the flexural fatigue life at one temperature, one strain, and at one frequency. Please, 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 okay? Why do we invent tests to complicate our lives? Somehow, and I was at Berkeley at the time, we invented 4-point bending fatigue test, and 500 researchers jump on us and say, you have to have different strains because we really want to capture the property of the mix at all different strain levels. Nobody cares about the property of rut resistance at all these temperatures. They have these cores that you test, and at one temperature, one condition. So why don't bring that concept to fatigue? So at one strain level, we can compare mixes. That's what we did here. So look at the N group, is what you're doing now. The planet is doing that little material that has that little fatigue life that we barely can see. Now, California is doing A, which is something about 10 times better than N. Now, with the reactive activated rubber, we can match that. We can do B. But nobody stops us from putting more rubber. There's no limitation of dumping more reacted rubber in a mix. So now we can add these with these very high fatigue performance. And you say, well, so can we predict this? Yes, we can. Shell method developed, 60 years ago? There's a little equation that you can see in blue the results of fatigue tests, and in red the Shell predictions. And please note that below you have percent binder, and you have bitumen plus RAR. Normally our mixes are at 6%, very good mixes, 6.5 SMAs with toilet paper and old newspapers called fibers, cellulose fibers, they're at 6, okay? You see the fatigue life they have 20, 30, okay. If you are lucky, it goes to 100,000, okay? Now, if you put more rubber, you can now increase the binder content to levels that go to easily to 2 million. Why wouldn't you do this? Because what we want from a pavement is fatigue life. We want durability. If you keep wanting the same, if you want less, okay, keep doing something at 4. But it's much, much cost effective to put, let's say, double the bitumen content, but double the binder content, and get 100 more times the fatigue life. Can we compute the benefit? Because each time I talk with somebody, say, oh, but you're going to put more bitumen, it's going to cost more. Yeah, but what do you get for it? Is it cost effective? Is it beneficial? Now, we also, to get the same matching performance, then we can do another thing, is reduce the thickness. So this is just to show you that the fatigue life actually obtained on 4-point bending tests that George Pais and Professor Paul Pereira can demonstrate for you here. We can match the expectations from Shell equation. Now, this graph makes me immensely, immensely happy because it shows that for the first time in the planet, a road organization, Infraestruturas de Portugal, made something very smart, which the planet should have done it after the sharp developing these tests. They now have in their books that they can reduce, they can demand from the contractors mixes with specifically fatigue lives. So they introduced 4 new mixes, and I call your attention for the SMA 14G, which is pretty much the same as the mix from Arizona and California. Actually, it's there thanks to the George Way. And now we pushed the envelope. We went above this. We put more rubber. Please note, this mix is there, SMA 10S, which has been placed in Portugal already, in several places. It was something that was used before by McDonnell many, many years ago, where he attempted to put what is pretty much the limit we can put in rubber, which is 25%. There are reports where he tried to do that, but because he was using the old method, the wet method, he had difficulty doing that. He had to put some liquids and to lubricate everything, okay? But his goal was then to do SMA 10S, which is fantastic rutting and impossible to rut. 2 million fatigue life when we are doing now 20,000 That's 100 times better. Now anyway, so I recognize the fantastic step forward that Infrastructure de Portugal did, and I hope that people here take this to their countries and start doing what is logic. This was invented 30 years ago. Anyway, these mixes, and there's the new specifications in Portugal that have the 4 levels of amounts of there are contents, and the key point in these new specifications is that you cannot just invent mixes that have, oh, I say they have this property. No, demonstrate, do the test. And these mixes will have many other benefits, okay? I'm just stressing the point where you can see the difference. It's because they have so much rubber, they are very, very resistant to UV, and they'll be very durable, and they have all these advantages, and that smooth ride. I put this in, I am the president of a road association, and I put this on the road. Sorry about that. I was very nice that the mayor of that group let it. And all the neighbors are so happy because they have less noise in the cars. Anyway, this is environmentally friendly. If I tell you if all the rubber, the rubber in Portugal was used in pavements, IP would save $100 million. Can someone register this number and call me a liar? Okay, George is not saying the truth. Challenge me. IP could save $100 million a year in energy costs. Anyway, so with rubber we can do much better mixes at all levels. So I see the future that we have all rubber going pavement, recycled pavements. Recycling is good. Just screen the sizes of materials. As I mentioned, Europe can save $100 million in equivalent to energy costs if we use all the rubber from tires in Portugal into pavements, or import them. If we need more, import them. Most countries don't know what to do with the rubber, so we get them. Anyway, sorry for being so passionate about this. I am passionate about this. Thank you.
Thank you a lot for this innovative presentation dealing with this new way to treat the crumb rubber. And now it is the time for Filippo Balzano to speak about laboratory assessment of microsurfacing bonding, characterization of the application surface, and Leitner shear testing. Filippo, the floor is yours.
Thank you. I'm Filippo Balzano from the University of Bologna. What we will see today together is our last research, very last research. So let me shortly introduce you the structure of my presentation that will see a brief introduction. Then I will move to the materials and to the methodology used, before finally going to the main results obtained and to conclusions. So our research, our work is focused on microsurfacing. As you heard this morning, but you already know, microsurfacing is mainly, not only, preservation treatment that usually can be applied at ambient temperature. So basically we are talking of a cold asphalt mixture that usually involves water-based modified bituminous emulsion, very dense graded aggregates, mineral or chemical additives if needed, and mixing water. Why are many companies turning in the direction of microsurfacing? Well, in general, to extend the life of our pavements, not only, as you heard from Professor San Giorgi, but microsurfacing is a good way, an easy way to restore the impermeabilization of the bottom layers by sealing the minor cracking, and also, of course, we use them to improve the skid resistance of the top surface. And all this involving way less money, way less energy, way less raw material and emission than the standard repavimentation. But also we are talking of a thin layer of material. So usually we have less than 1 centimeter of mixture. So we need, this mixture needs to be strong. That's why we use modified emulsion. And also, we need to be sure that our mixture is well applied and has last bonding with the support. And this is challenging because the compatibility between the new layer and the support depends on the properties of the support. And while we have a lot of guidelines tests to assess the mechanical properties for microsurfacing mixture, we don't have nowadays something unified if we want to assess the bonding level for this kind of mixtures. That's why we wanted to move in this direction. So we had a first step in our experimentation that where we collected a large number of cores from real pavements, existing pavement, with very different properties. You can see we have porous asphalt, dense asphalt, we have reclaimed asphalt, also some non-bituminous binder, the transparent one, and mainly we wanted to focus looking on the texture. We wanted to collect very different textured pavement. Why we wanted to, I want to remark the texture, because as you know, the bonding is basically a matter of 2 points. The adhesion, for sure, so chemical adhesion and physical adhesion, so the friction between the particles that can be relied on the micro texture of the surface of the support. And on the other end, we have the interlocking, the mechanical locking of the aggregates inside the microtexture of our pavement. And in order to assess the microtexture, the texture in lab, we wanted to work in 2 ways, in 2 directions. The first one, very simple. So using 2 very well-known, 2 very simple laboratory tests, as the one I'm showing, this is a sand patch, a very standard sand patch. Actually, it's an adapted version to be used in, on cylindrical samples in lab, but nothing difficult. It's just a way to evaluate the mean texture depth, so the microtexture of our supports. And along with this, we also included again, a very standard British pendulum test to assess the friction of the top surfaces, and so somehow some information on the microtexture this time of the support. But we also wanted to do an advanced description of the texture using a close-range photogrammetry analysis. As you heard yesterday from Professor Woodward, you can basically apply this technique to obtain the texture from 2D picture, collecting 2D picture. And you may say you will need professional equipment in order to do this, and it's true. You can use a full-frame DSLR camera, a prime micro lens, external flashlight, and you will obtain something high resolution, like the picture I'm showing on the top. But I also wanted to include the first picture, where you can see a homemade light box that can allow you to apply this technique using a way cheaper equipment. Also, we tried this method using a mobile phone camera. And using this approach, you can collect a large number, we are talking on 45, 50 pictures taken from different angles for each core, and you can merge the picture together, and you can obtain a 3D model, a high-resolution 3D model of your surface. This one is not a video, this one is a 3D reconstruction just starting from the 2D picture. And when you have your 3D model, you can use a software to map your texture, to obtain a topographic map, 3D, of your texture, and you can read everything you want. I'm showing, for example, the Abbott Firestone curve. That surely is something well working for this kind of problem. When we had all our supports described in terms of texture, we finally moved to the microsurfacing step. So we took from market a well-working microsurfacing recipe, and we applied this mixture in the same way on the top of each core. And when all the core were applied, I can finally move to the core of our research, which is the assessment of the bonding level. And we wanted to suggest this very simple test, if you want, the Leutner test, by using this apparatus, because you can apply a compression load in the cross section, in the cross direction of your sample. So basically, you will have a direct shear on your interlayer surface, and you will basically cut off the top layer, as I'm showing in this picture. And before moving to the results of Leutner test, let me take some few seconds to talk about the texture, because as you know, when you talk about texture, you can find 100 of parameters, reliable, and you can, depending on what you need. That's why we decided to select a list of parameters, taking from volume parameters from the Abbott curve, depth parameter from the 3D profile, also some shape parameters like for example the kurtosis. And I want to remark, all this list is obtained just thanks to the topographic description using the photogrammetry. So before going on, we needed to be sure that the value we read are true, are reliable. So we wanted to compare what we obtained with the standard methodology. And so if you, for example, compare the MTD value, so the sandpatch value, with, for example, the volume of valley obtained from the Abbott curve, or the mean texture from the 3D surface, you can see a huge correlation. And so this can result trivial, but it's not, because if you think we are measuring the same stuff, but in two very different ways. So, moving now to the results of the Leutner test. The results of Leutner test is a very simple, typical curve. So you have load of, if you want, stress versus displacement. And if we wanted to group together samples with very similar texture, so in the same texture family, but just texture. The only property this score share is texture. I want to remark that every time you see a different color, that stands for a different aggregate, different binder, different everything, just sharing the texture properties. And as you can see, you can have very similar behavior for different pavement. And again, as for the texture, when you have this kind, from Leutner curve view, you can read a lot of information. You can read energies, typical characteristic load, stress, displacement, and we did collect it. But we also wanted to keep it simple for this presentation, and we wanted to include a very reliable parameter, which is the resistance modulus of Goodman, the Ki, which is defined as showed. And if you go comparing the behavior, depending on the Ki, the resistance modulus of Goodman, just in terms of texture, for example, I'm showing the MTD value from the sandpatch, you can see a tendency. You can see a clear increasing in the resistance modulus by increasing the macro texture of the pavement, and also a good correlation if you want. So, if we want to resume the main results of our research, you surely can say that the same mixture can have a very different behavior depending on the properties of the support. In particular, depending on the texture of the support. We also showed how an advanced methodology approach in assessing the texture can be useful for some specific needed. And the main focus, we also showed how an adapted version of a very simple test can be used also in this kind of special mixture. Thank you for your attention.
Thank you, Filippo, for your fascinating presentation. And now, please welcome Carolina Moura, who is going to speak, to present his work titled The Importance of Microsurfacing Asphalt Mix Design in Improving the Performance of this Cold Surface Treatment. Please, Carolina.
Good morning. My name is Caroline Moura. I am a PhD student here at the University of Minho. And in my presentation is about the importance of microsurface asphalt mix design in improving the performance of this cold surface treatment. Filippo already introduced the microsurfacing, but I am talking about the mix design of this mixture. So microsurfacing is a cold asphalt mixture. It is a technique of maintenance of pavement surface cores that has the ability to seal and restore the surface properties of pavements. As a cold asphalt mixture, it has a low environment impact and a high sustainability. This mixture was composed by asphalt emulsion, aggregate, filler, and water. So what is the problem? Although it is a widely used technology, there are some challenges with the existing mix design procedure to find the ideal mix design that result in the mixture with good performance. So this work aims to propose a new mix design for microsurfacing based in European standard testing methods for this type of mixture, and the influence of the type and amount of asphalt, filler, asphalt emulsion, filler, and water on the characteristics of the mixture. To find the ideal mix design, we carry out 4 tests, 2 preliminary tests, the pizza test and the ball test, and 2 European standard tests, the consistency test and the cohesion test. About the materials. In this work, we used 2 types of asphalt emulsion. So for each test, we produced two mixtures. Mixture 1 with emulsion 65 BP4, and the mixture 2 with emulsion 6 BP4. The difference between the emulsions is about the binder content. So the first mixture has 55% of binder, and the second has 6%. And for all mixtures, the aggregate was the same, basalt 0.6, and the filler, cement, Portland cement. About the composition. In this work, we are looking for the ideal relationship between the amount of emulsion, filler, and water. So in each test, to determine the amount of these materials, we consider the aggregate as a reference. So the percentage of these materials was defined to consider the aggregate 100%. The mix design procedure. In this study, we also proposed a mixing procedure because we noticed that the way that we prepare the mixtures influences in the final performance of the mixture in tests. So all mixtures were prepared with the same procedure. First, we separate the fine fraction of the aggregates from the coarse fraction, passing the aggregates from a 2 mm sieve. So we put the fine fraction and the half amount of water in a bowl. Then we add the cement, and after we add the coarse fraction of the aggregate and the rest of the water. And finally, we add the emulsion. In each of these steps, we have to mix the materials until the mixture is homogeneous. This is the final aspect of the mixture, and at this point, we made 2 preliminary tests. The pizza test to determine the amount of water in the mixture, and the ball test to determine the amount of cement in the mixture. The pizza test, it is a simple test. We shape a small pizza and let it rest in a surface. After 30 minutes, we break the pizza and check your color. Your surface must be black, and your interior must be brownish. After 1 hour, all pizza must be black. If it doesn't happen, the amount of water must be reduced. The ball test is also a simple test. We shape a small ball and let it rest in a surface. After 1 hour, it must be dropped to the ground from a height of 1.5 meter, and it mustn't break. If it breaks, the amount of cement must be increased. This is the first mix design, the mix design after the preliminary test. And we can see that the amount of cement is the same in both mixtures, but the amount of water is different by 1%. So the second test is the consistency test. It is a European standard test to determine the ideal water content to assess the workability potential of the mixture. But in this study, we use this test to confirm the amount of water found in the pizza test. For this test, we need specific equipment. We produce 400 grams of the mixture, introduce the mixture in a cone. This cone must be in the center of the graduate sheet metal. So we remove the cone and check the flow mixture at 4 points. The flow mixture must be between 25 and 35 millimeters to show a mixture with a good workability. This is the result for the consistency test. For the mixer 1, we confirmed the previous water content, 11%. But for mixer 2, the flow was higher than it had to be, so we need to decrease the water content by 1%. This is the new mix design, the mix design after the consistency test. And now the difference between the amount of water in mixture is 2%. Between the mixture is 2%. The last test is the cohesion test. It also is a European standard test that aims to determine the curing process of the mixtures. But in this work, we used this test to define the ideal relationship between the amount of water, cement, and emulsion. For this test, we also need a specific equipment. We produce 200 grams of the mixture, introduce the mixture into the molds, 7 molds. Each mold has a different curing time. This is these curing times. And after the curing period, we put the sample under a piston in this specific equipment. And we apply an air pressure of 200 kilopascal and a torque force that is measured by a computer. This is the result for the consistent cohesion test for the mixture 1. For this test, we have 2 important results. The cohesion value for 30 minutes of curing and the cohesion value for 6 minutes of curing. So for 30 minutes curing, the cohesion value must be higher than 12 kilograms centimeter to show a quick set system. And to 6 minutes of curing, the cohesion value has to be higher than 20 kilograms centimeter to show a quick traffic system. So for the first sample that was prepared, we used the last mix design, 12% emulsion, 11% water, and 2.5% cement. The mixture don't achieve the expected result for the 6 minutes curing. So we made the other samples, changed the amount of emulsion and cement to find a mix design with better result for this test. We decided for this mixture, don't change this value, the water content, because it was confirmed in 2 tests. So we found that the mix design with better result for this test is the sample number 2. It was a mixture with 30% emulsion, 11% water, and 2.5% cement. This is the result for the mixture 2. We can see that this mixture has a different behavior. So for the first sample that was prepared with the last mix design, the mixture don't achieve the expected result for the both times of curing. So we made the other samples, changed the amount of the materials, in this case the 3 materials, but none of them achieved the expected results for the 6 minutes of curing. The best result, it was a mixture with 30% emulsion, 10% water, and 3% cement, the sample number 4. So this is the last mix design, the mix design after the cohesion test. We can see that the amount of emulsion is the same for both mixtures, but the amount of water and cement is different. The difference between the mix design of both mixtures can be explained by the difference between the emulsions. These two graphs show the characterization of the residual binding of the emulsions. And we can see that the binder used in each one has a different behavior. So it shows that the performance and the mix design of microsurfacing depend on the emulsion components, like asphalt type, emulsifier dosage, water being the content, binder content, and the type and the amount of polymer. So we have some conclusions. These tests allowed us to determine the ideal amount of emulsion, water, and cement for the microsurface mixtures. The preliminary test was essential to provide an initial idea of the water and cement content. The cohesion test was the most challenging because we had to find the ideal relationship between amount of three different materials. It's clear that the emulsion type strongly influences the final mix design. And to sum up, it's not easy to find the ideal mix design for microsurface mixtures because it's a system influenced by the composition of the materials and the chemical reaction between them. Thank you for your attention.
Thank you, Carolina, for your absorbing presentation. And now, please join me in welcoming Manuel De Rose, who is going to speak about the rheological behavior of chlorophonic rosin-based biobinders for road pavements. Manuel, the floor is yours.
Thank you, Professor Fatico, for introducing me. I want to thank also the PFDM organizing committee for this conference and for giving me the chance to be here today to introduce our work, which focuses on colophony rosin-based biobinders for road pavements. So let me show you the structure of this work. With a brief introduction, we're gonna move to the core of this research, the biobinders, and giving some latest development in this field, and then we're going to move to the materials and methods and discuss about the results of this research. So in the recent years, both road industries and researchers are moving towards the development of new technologies, green technologies for producing sustainable pavements. Also for trying to reduce the environmental impact in terms of carbon footprints and energy consumption. Some of these solutions are nowadays consolidated practices, like, for example, the cold and warm mixed technologies, or the use of reclaimed asphalt pavement, also with higher percentage. Another one field of research, which is now becoming popular, is the one that tries to replace the bitumen, which we know this is a non-renewable resource. And therefore, in the latest years, many byproducts from different industries process or wastes of the everyday life, but also renewable resource were analyzed with the aim of creating what is generally called a biobinder. With a biobinder, it's possible to reduce the dependence from the petroleum-based products of about 0 to 10%, which is a bitumen modifier, and it is an application mode rather mature. 25 to 75% bitumen extender, which is also gaining more, which is becoming more popular, up to 100% for it is a direct alternative binder. In the recent years, many materials were used for the production of biobinders, bio-oils from different biomass resources, or lignin, wood bio-oils, but also rosin. And each of them can be placed inside one of these three categories. In this study, we want to focus on the development of a direct alternative binder. In this case, the production of the biobinder must follow what is a consolidated principle that comes from the deserafractionation in bitumen. Therefore, there is a need of an high molecular weight material dispersed in a viscous matrix, a viscous oil. And sometimes consistency agents, like for example waxes, polymers, or fibers, are added into the blend in order to optimize the rheology. As for the high molecular weight material, the colophony rosin is a suitable one. Colophony rosin is obtained mainly from two sources, let's say. One is the tall oil colophony, which is a byproduct from the craft process in the manufacturing of the paper. The other one, the natural one, let's say, is the colophony rosin is the solid residue of the turpentine, which is an oleoresin secreted by pine living trees and collected by tapping the pine living trees, or more in general conifers. Colophony rosin usually undergoes to chemical modification in order to optimize its physiochemical properties according to the future uses. However, those modifications are energy-consuming process as they require the high reaction temperature for long residence time and involved also the use of solvent and other raw materials for the reaction. Therefore, in this research, we want to focus on a biobinder made from colophony rosin in unmodified form, as viscous matrix, waste olive oil no longer suitable for human consumption, and as consistency agents, waxes, SBS, polymer, and crumb rubber. Most important thing to bear in mind is that nowadays the analysis of biobinder still represents a challenge for the for researchers because of their complex behavior, like for example non-linear viscoelastic behavior, or susceptibility to aging, hardening, which is always often misleading with the detection of stiffness. And the common testing protocols developed for the bitumen may fail in properly describe them. Given this premise, we can move on to the materials and methods of this research about the sample preparation. The components are placed together, less than crumb rubber, in the oven for preheated at 180 degrees and for 40 minutes. Then they're placed under mixing, under an egg shear mixing at a speed of 5,000 RPM, maintaining the temperature constant. And in the first 15 minutes, the crumb rubber is gradually added. Then the mixing operation continues for other 45 minutes. By combining 3 different oil rosin ratio and 3 different percentage of SBS, we obtain 9 biobinders blends. And for comparative purposes, we choose also for bitumen 5070 and 7100 penetration grade, and 2 polymer modified, one soft and one hard. Empirical tests of penetration depth and softening point were carried out. Also, rheological tests were performed with the aim of analyze the material phase transition. We performed temperature sweep test, increasing the temperature from 25 to 100 degrees at a constant frequency of 1 Hertz, and by applying the constant stress previously determined in order to guarantee the linear viscoelastic condition. Finally, on just few blends, in order to have an idea on the mixture, we do the most common mechanical tests of Marshall stability and indirect tensile strength. Here the results about the penetration depth. The graphs are grouped according to the percentage of SBS and the oil-rosin ratio, 0.55, 0.45, 0.35. The penetration values decrease as the oil-rosin ratio decrease, and also the SBS content has an influence. If you look from the left to the right of the screen at the same oil-rosin ratio, the penetration depth decrease. And the values for the reference bitumen are always lower, except for the 7100 penetration grade bitumen. As for the softening point, a greater amount of oil decreased the softening point. That was somehow expected. In contrast, the percentage of SBS does not have an influence, seems to not have an influence on the softening point, giving the perspective that maybe this behavior can be it's maybe for the higher softening point of the rosin and the waxes, but also the crumb rubber in the biobinder. As for the rheological response, the graphs show are grouped according to the oil-rosin ratio. Here the storage modulus, which is more than 1 order of magnitude higher for biobinders compared to the reference bitumen. But in the service temperature, all the oil-rosin ratio more or less show the same storage modulus. Whereas the transition phase is shifted to higher temperature with the increasing of SBS, from the lighter to the other curve. About the loss modulus, also here it is higher for biobinders in comparison with the reference bitumen. In contrast with the behavior of the normal bitumen, the loss modulus is lower than the storage in the previous slide, in the range between 25 and 50 degrees in the service temperature. And therefore, due to this predominance, the storage moduli is lower in that range. This could be attributable also to due to the presence of the crumb rubber in the mixture. The phase transition can be placed, included between that of the 50-70 penetration grade bitumen and the soft modified bitumen. Here I show you the mechanical preliminary test. The mixture were made according to an Italian road agency specification. It is a dense graded for friction course with 8 millimeters of nominal maximum aggregate size. We chose an hard and dense limestone. The optimal percentage of biobinders is 5.5% determined by a Marshall study based on aggregate weight, and for the bitumen, the reference bitumen is 4.8%. Also here, the difference could be attributable to the presence of crumb rubber. Here in the green square, I'll show you that the mixture, the blend with an oil rosin ratio of 0.35 and 4% of SBS show values that are slightly above the threshold value provided by the Italian Road Agency specification, 10 kilonewton for the martial stability and 0.72 for the ITS. So the results starts to be encouraging. For the conclusion, we tried to analyze the use of colophony rosin for producing a possible direct alternative binders for road pavement. Although the empirical and rheological tests are essential to understand the main characteristic of the binders, there's also the need as future development to look at chemical tests, SEM analysis, FTIR, for example, to understand in a better way the interaction between the components. Also, the study of the weight ratio between all the components of the blend and the addition or substitution thereof could be useful to enhance the properties of the biobinders. And in addition, tools like life cycle assessment or life cycle cost analysis may be useful to guide this optimization phase. The first mechanical tests were quite good, but of course, by the way, further mechanical characterization are needed to complete the framework, so moisture susceptibility, fatigue behavior, and expected life. Many thanks for your kind attention and greetings from the other member of the research team and our university. Thanks.
Thank you, Manuel. And now, the last presentation is just mine. So I'm going to speak about the analysis of the mixture that we saw a couple of minutes ago from a LCA perspective. So, Mr. Manuel De Rosa spoke about the efforts carried out in getting the right formulation of the biobinder. It is essentially an effort made up of rheological aptitude of the asphalt binder, or better, the binder, to serve as the binder of a mixture, of a road mixture. The perspective now is to carry out an analysis in which each material and each step of the process is considered in order to understand how much friendly are really these materials. So the objectives of this analysis were to understand something in terms of CO2 equivalent and in terms of global energy requirements. We focused on three mixtures. The first one is essentially a common mixture. The second one is a mixture containing crumb rubber, so following the dry method. So we are talking about rubberized asphalt. And this is part of a European project, the EVIA one, while the last one is just the mixture Manuel De Rosa spoke about a couple of minutes ago. So it is a bio-asphalt, or better, a bio-binder. So this picture represents the overall process from the definition of 3 scenarios, the ones we spoke about a couple of minutes ago, the characterization of the alternative payments technologies. We are talking about friction courses. So we are analyzing 3 scenarios in which just the friction course is different. After we defined the functional unit, that is to say the system we are referring to. And we carried out tests. We gathered data in order to carry out the quantitative assessment of the impacts of the processes, of the materials used in 1 square meter of pavement. And finally, we derived the CO2 equivalent per square meter of pavement and the global energy requirement related to the same square meter of pavement. We are talking about traditional materials and we could say innovative materials. So we are talking about aggregates, coarse aggregates, fine aggregates, filler. We are talking about crumb rubber, and in this case we used 2 different crumb rubbers. The first was a pre-treated one, while the second was a common crumb rubber, of course asphalt binder, rosin, or beta colophony rosin, a sort of resin taken from the trees, paraffin wax as an essential component in order to fix the rheology and to fix the penetration grade of the binder, the eco binder, stidiene, butadiene, sirene, and finally olive oil. Yes, olive oil, of course, not even more usable for alimentary purposes. So, as we said, the 3 pavements have had an identical base layer. We're talking about a granular base layer, an identical binder layer, a traditional binder layer 7 centimeter thick, produced with using neat bitumen, mineral aggregates, filler, and 3 different friction courses. The first one is the reference one. So in this case, we used just aggregates and an SBS modified bitumen. It is important to highlight that these friction courses considered were not traditional friction courses, but they were low nominal maximum aggregate size. As is well known, this is due to the opportunity to tune the power spectral density of the texture in order to minimize the production of noise in the interface between the pavement and the tire. So this is a common requirement of the 3 different friction courses, having a low nominal maximum aggregate size. In the second case, by referring to the European project E-VIA, electric vehicle noise control by assessment and optimization of tire-rod interaction, we considered still a modified bitumen. We used again the SBS, but we used in the mixture a pre-treated crumb rubber about 2% by mixed weight. So we referred to a dry method in order to partly substitute the crumb rubber to the aggregates. It is well known that the dichotomy dry versus wet process is just an idea, an idealization. So there is always a surface interaction between the binder and the crumb rubber. This interaction is very important in the case of the wet method, and it is less important just dealing with surface interactions in the dry method. And finally, in the third case, we analyzed the bioasphalt Manuel De Rosa spoke about before. So, apart from the aggregates, I repeat, always using a low nominal maximum aggregate size, we used the resin coming from the colophonic rosin, epoxy wax, crumb rubber, this time wet method, SPS, and waste olive oil, as we said before, are no longer suitable for human consumption. So, through the inventory and carrying out tests, we tried to understand for each step, for each process involved in the production, from the cradle to the grave, the energy needed, the CO2 equivalent involved. So we are talking about the modified bitumen, the biobinder, the characterization, the design of the mixture, the aggregates, always using the same radiation. And we are talking about considering the production of each component, the transportation of each component, and finally the construction. And so, for each step having a corresponding content in terms of CO2 equivalent. So, we did the same. So, we carried out this process dealing with raw materials, extraction and processing, with the production of compost materials, I mean asphalt mixture, biobinder, bioasphalt mixture, and so on, and finally with the road construction. So, we consider the production of each ingredient of these three mixtures, so bitumen, coarse aggregate, fine aggregate, filler, the asphalt mixture, and we used a little bit of hydrated lime, which is common in several areas due to the fact that there is just few filler contained into the coarse and fine aggregate. Crumb rubber, in particular the RAR X1, the non-pretreated crumb rubber, resin, olive oil, and paraffin wax. For each component, we considered the corresponding transportation, and finally, the construction efforts. Now, as you may see, for the base, for the granular base, the global warming potential, so we're talking about kilograms of CO2 equivalent per square meter, so per functional unit. The kilograms are the same, pretty the same. It is okay also for the binder. The reference friction and the rubberized asphalt friction have a comparable GWP, while for the bioasphalt we have something more. We have 7 versus 545. And the problem is the production of the bioasphalt. It is not the transport, it is not construction, it is just the production. So I need to say the first step before using it. There is nothing very interesting to say about the binder coats and the base coats. When we look at the results in terms of plant operations versus single materials, for the reference case, we have about 0.06 kilograms per square meter for plant operations, and so we need to add what is concerned for bitumen, coarse aggregate, and so on, till the calcareous filler. When we talk about rubberized asphalt, the numbers are quite the same. They are quite the same, with slight variations. But if we consider the bioasphalt, there is something different for the colophony rosin, as you can see. So this preliminary assessment in terms of life cycle analysis was carried out thinking mostly to the CO2 equivalent. Is it a comprehensive analysis? No, it is not. It's not, because when we talk about life cycle, if we compare three solutions, we need to understand that the expected life of the solution is going to affect greatly the results. So in a sort of implicit way, the considerations above were carried out without considering the expected life of the three different payments. Now, if this expected life were really almost the same, we could say that these conclusions could be considered well supported, well based. So the limitation of this study is that we did not carry out fatigue life tests or other assessments dealing with the expected life of each of the three solutions. Under this assumption, it is possible to say that if we fix the aggregate gradation, and we did it in order to better tune the power spectral density of the textile, so in order to reduce the contribution in terms of noise, it is possible to carry out this kind of analysis. The bioasphalt, which has a huge possibility, a huge potential in terms of eco-inventions, but that where is needed an attentive, a careful analysis of all the externalities and all the mechanistic related instances, generate significant amounts of air pollutants, CO2 equivalent. And this is essentially due to the production of the resin, or that is to say, the colophony rosin. The bioasphalt, which doesn't imply any addition of bitumen, allows for preserving the consumption of bitumen, but its production involves a lot of CO2 equivalent. So the air emissions generated, on the contrary, during the construction of a scenario with the rubberized asphalt, we use in this case the RARIX pre-treated cramp rubber, were approximately the same as the reference case. And under these assumptions, these are the conclusions, and with that, thank you for the attention. So I think that many of you are going to ask something to our colleagues, and that there are several questions to pose to Professor Way or to Professor Sousa and to the other presenters. Is there any questions? Okay, I will start with the questions. I was fascinated by the presentation of Professor Way and Professor Sousa. And I was wondering how much impacting is the process dealing with the reactive rubber. Yes, how much impacting is in terms of energy or
Thank you for the question. During a European program, which we silent rubber pave, it was a $2 million project, European, that we received. We were forced by the regulations to compare, and Abaleo is a company completely different than any, never heard of them. They compared in all 13 different important aspects like the water, the energy, the CO2, and pavements, and they checked all the energy consumption going into making RAREX, transport, everything. Mixes with pavements with RAREX have half in that scale that they have is about half of the footprint of conventional mixes and even SBX mixes. So I can send you the report because clearly you are doing that. It's actually a very interesting report because it contains things that I never heard in my life. So.
Thank you. Just another question, just because the innovation captures our attention. What about the temperatures at the asphalt plant?
Excellent question. Okay. Normally, we mix, we use let's say the aggregates are at about 180. The bitumen is about 170, 175, because when we put the chrome rubber is at ambient temperature and we want everything to be made at 175. Now, but some consider, okay, let's lower the temperature. It's okay. There's now products in the market that allow you to do that. But I want to remind you that generally, when you do mixes with these kind of mixes, they are replacing mixes on a scale of 1 to 2, meaning instead of putting 5, you put 2.5. Instead of putting 10, you put 5. So in the big picture of things, instead of warming up some mix to 160 degrees, normally that's what we do in Portugal, this one you do to 175, but only half of the mix. So just without even worrying about putting additives to lower the mix temperatures, which is okay, these are already environmentally better than the others because you are warming up less. Now, the important thing here is actually not so much the temperature of the mix. You need to consider this, is that these mixes are placed thin, most of them. So what you need to worry about is the time between you place and when the roller comes. You cannot go take a coffee and have lunch and come and pave after because you're not going to pave. That's finished, okay? So my recommendation is that you tie a rope or, those collars to the man on the roller that is like 10 meters, and then, he has to stay there compacting near the paver for these thin mixes because they're going to cool quickly. And after they cool, they become very elastic. I actually have seen they force the compaction of these cold mixes, they turn on the vibrator, and literally it jumps the roller, because that thing is elastic surface, which was not squished to put contact to contact of the aggregates. So the key thing, let's call it difficult, just to be difficult, is that when you put the mix, you must have the roller on it. Doesn't cost more.
Thank you. That's excellent. I mean, it is very important what you said. So you are thinking to the entire process, and you are thinking how to manage novelties, improving the overall processing of the construction. So we are talking about the time needed to roll, the distance between the asphalt plant and the location of a new pavement, etc. So excellent. Thank you for your excellent presentation.
Now, you just touch on something that is really not a big deal, is the distance. Some people say, oh my God, that's like 2 hours, 1 hour and a half. No, no problem. These mixes have so much rubber, they act as an insulator. If you cover the truck, they stay there a long time. So warm. So it's that part, our fire, because, oh my God, that thing is like 1 hour away. So what? It's fantastic. Keep it there. It's cooking.
And thank you also for this detail dealing with the thermodynamics of the system, and so the thermal characteristics of rubber, essentially. Thank you. And so I hope that in the future, many analyses will be carried out dealing also with the benefit-cost ratio, which appears very interesting for this innovation. Any other questions? Please don't. Okay, great.
Hello everyone, my name is Marshall, and I come from Copenhagen, Denmark, and so cycling is a part of our culture or the way of life for us, and it was interesting to listen to Professor Cesare about the impact absorption pavement, and so it might be very specific to the North Europe countries, but have you done this pavement in cycleways?
Yeah, thank you for your question. Yeah, as I said during my presentation, we only did a few square meters on a real pavement. We actually used an electric paver, which was also an interesting thing. No, we have planned to do longer stretches with a new project I showed you before on the slide. So I hope that we can do, instead of 10 square meters, at least 1,000 square meters or more. Okay. So, sorry again.
It's just, I think our major problems in Denmark, or one of the major problems is we have around 5 to 6 months around frost temperature, so -5 to +5. And I had accident while cycling because you cannot see the black ice or something like that. So maybe you can also consider that as well.
Well, of course, when you reduce the temperature, the stiffness of the material will be reduced as well. But I think the drop in HIC, the drop in critical falling height would not be that much. So you will still survive an impact if you consider that critical falling height for asphalt is 20 centimeters, 30 centimeters. So we have 6 times that at the moment. We can easily go to 4 times, and it's still good for pedestrians and cyclists. So we'll try to save your knees and hips and everything.
Thank you for that.
May I follow up on this for Professor San Giorgio about the impact absorbing pavement you talked about? I assume it's softer, but then is it still, well, let's say it's usable? Does it an impact on, if you use it as a bicycle lane, for example, is there an impact on the ride comfort or not? Is it still usable as a sidewalk, that if it's so soft that you can't push a wheelchair over it, or how does it work?
Yeah, thank you for your question. It's a common question that we have. Of course, we are not, at the moment, we're not going on a real road, because that will totally change the story about rolling resistance. If you walk or cycle in it, it's perfectly fine. We tried it. We also asked the people in the nearbys to walk and try it. It's actually more comfortable, and it helps when you walk. It pushes your feet a little bit, so you basically feel less effort in walking. In this project, in the next project, we will have a collaboration with UCL London. I don't know if you're familiar with Pearl. It's a facility lab. It's a unique lab where they can basically model any pavement and do any scenario, and then we will test the walkability in different conditions with slopes and little steps and similar. So we'll address the accessibility of the pavement at the same time. So it's meant also for vulnerable users. So I'm also specifically talking about elder people and young people, or people with disabilities.
I have also a question about this special surface. I have my doubts about the durability of it. I know that it's only for pedestrians and for bicycles, but anyway, so I have some experience with poroelastic road surfaces. It's not the same, it's with bitumen, but I have great concerns that it will ravel very quickly. That is, should be tested. I know it's not a road, but even on the cycle path, I'm a little bit afraid. Also, under influence of sun radiation, it degrades quite quickly, I'm afraid.
Indeed, this is the other concern about the pavement that we are proposing. And first of all, what we tried is to do a little surface treatment on the material in order to protect it. In the trial, I haven't shown the picture because I was worried about being too long with the presentation, but we have been checking the material regularly in the following year. And there was indeed, as a first trial, we were expecting some damages. We saw some damages, but we could fix them, and that was interesting. So we could do easy maintenance. We took cores, and we could replace the cores with the same material. We also impregnated the surface with some additional material, like it was a transparent binder in that case. So we are on that. You're right, the problem of durability is the one that we will address also in the next project. Well, we already did some freeze and thaw testing and other aging testing, and it does behave well. So hopefully within the future we will be able to solve also more and more the durability problem. But it's so far so good.
Thank you, Cesare. Any other question? I think that we are in good time for lunch. Let me double check. It seems that it is a... No, we have a couple of... So, if there are any other questions?
Hi, I'm Hugo Silva from University of Minho. I would like to make two questions, one for Jorge Sousa, concerning the use of rubber. I don't know, probably that issue is, or this question is already made in the past, but as we use sulfur in rubber, I would like to ask if there is any problem with oxides from sulfur that can bring some problems of acid rain when we are using this type of solution. And I would like to make a question also to Filippo Pratico about the industrial phase of using biobinders, because in this phase I think we are not using it in an industrial way or in that phase. And I would like to know what will be the main changes or challenges to start using this type of solution in an industrial scale, because I think it will be slightly difficult at this phase to pass to that phase. Okay, thank you.
Well, thank you for that question, because I'll report to two stories in California. When they passed the law to mandate the use of 35% of the mixes in California to have asphalt rubber, there was a big reaction from the industry in many kinds of ways. In three stories. One was something, like you said, they were worried about the leaching and the sulfur going into the rivers and causing the different problems. So extensive tests, okay? And they even had masks, you know, like zombies going around measuring everything, like they detected nothing. Like, actually, they detected that mixes with asphalt rubber let go much less than mixes, conventional mixes. Another story, so that we address everything now, is someone, they start saying, oh, these mixes, they cannot recycle them, okay? So there was a mayor in Santa Barbara, I believe, that had been using asphalt rubber, and they start being pressuring. Well, so he picked up on the new pavement, okay? Recycled the old pavement with these men with suits trying to prove everything. Obviously, can't find anything. So you can recycle it immediately after if you want, or you can wait 20 years and recycle it later, because these pavements usually last that long. And there was another one that they invented. So the people, when they were producing asphalt rubber in California, some companies, the people start reporting, oh, I'm feeling very sick, I have headaches, okay? Well, they realized later that they've been paid to do that. So let's eliminate all these things. These materials have been used for 60, 70 years, since 1970. So solid technology with a lot of negative tries to make sure that this technology doesn't go forward from many competing interests. So thank you for bringing that up, but you can drive in these pavements, don't worry about the sulfur. It's not going to go out of the pavement.
So about the second question, I agree with you about issues in industrializing these biobinders or other solutions. This notwithstanding, it is not a good reason for not attempting to have alternatives to the traditional oil-based solutions. So I absolutely agree with you about the issues. Probably doing research in this field is very important because of our preparedness with respect to concerns in extracting more oil. So this is something which is more taught from an economical standpoint, a geopolitical standpoint, than from a scientific standpoint. But science is important also because of the possibility to think to something that actually at this moment is very far from industry. Thank you again. And if there are not other questions, I would like to remind you that at 1:10 it is scheduled lunch, and thank you for attending this session.
Olha, a apresentação do minhoto.
Espera aí, deixa-me só tirar aqui. Quer passar? Quer-me... Qual é? É a que horas?
É a última do dia, é às 6:30 para aí. Eu?
Yeah, the George. There we go, there we go. Yeah.
I have two. Oh, copy.
Thank you.
Ok.
You are Elizabeth, right?
Yes.
You?
Sim.
Onde é que está?
Tá aqui.
Tem. Ok, muito obrigado.
Estamos na sessão 7.
So that was section. Oh, this is condition, right? The same.
Yep.
Okay, good afternoon, everyone. We are going to start a section that's called Surface Texture. And my name is James Tsai. I'm a professor in at the School of the Civil and Environmental Engineering at Georgia Tech. So without further ado, I would like to introduce the first invited speaker, Filippo Bratko. And Dr. Filippo Bratko received a laureate degree in the civil engineering at Pisa University with a PhD in transportation infrastructure in the Palermo University. At the Mediterranean University, he became associate professor in 2002 and became full professor in 2012, and also serving as a deputy of master school, deputy of Pavement department, director of the Roll Laboratory, a member of TRB, and chair of several international committees involving in national and international research industry projects, and consultant to several companies and agencies in Europe, the Middle East, and Africa. And he also enlisted by the Stanford University for the world ranking top 2 scientists list for many years. So without further ado, let's welcome the Dr. Filippo Bratko to give a talk.
Thank you, Mr. Chairman. Thank you, organizer. Title of my speech is A Discourse on Criticalities and Perspectives in Road Texture. But probably a better title would be the following. Does the gone make the fire? So, in my unsatisfactory Portuguese, o hábito faz o monge. Yes, because texture is a sort of skin. So talking about texture means talking about a sort of boundary of a system. Let's start from a couple of pictures of the past. 2002, proving ground over Nardò, design and validation of the proving ground according to the ISO 10844. Then was just a draft. 2004, another consultancy we did for the Ferrari, dealing with the micro texture in the aim of predicting during the races, predicting the friction. 2011, proving ground of the Piaggio. Piaggio means motorcycles. Assessment of the texture level and of the noise level. And so 2009, South Italy, assessment of friction and microtexture over time. And finally, motorway A2, the one that runs in South Italy till the island, Sicily, assessing power spectral densities and noise impact. So my conversation will focus on 4 main parts. The introduction, which is supposed to be something about what texture is, the effects that texture has or may have, and after, several attempts to rule the texture in order to rule the final effects. Let's start briefly from surface texture. Surface texture is what we feel through a hand when we pose the hand on the pavement, and there are hundreds and hundreds of indicators, among which the ones in which the profile of the texture is considered a stationary and ergodic signal. So it is supposed to be treated in terms of the theory of signals, and in particular through the FFT, the DFT, and so on. The overall framework is here represented. We have several causes on your right, causes in terms of production, composition, hundreds of indicators. Several possible effects, which is the texture, and hundreds of indicators dealing with texture, from the ones in which the texture is a simple number to the ones in which the texture is a vector. And finally, the performance that are supposed to be dependent mainly on the texture. So among the performance that are supposed to depend on the texture, there is, for example, the friction. And we listened to very fascinating discussions about texture, about its dependency on microtexture, on macrotexture, on the possibility to interpret the transition from micro to macro in a little bit more fuzzy way. And so about the possibility to focus just on micro in terms of several tests and on macro in terms of other tests. When we deal with friction, and in particular when we deal with the wet friction, and in particular when we deal with the wet friction at high speed, it is possible to find a lot of more or less empirical relationships in which you have a certain positive dependency of a given indicator, for example, the skid number, on a given indicator of texture, for example, the macro texture, the mean texture depth. When you deal with real data, for example, a British pendulum number, which is currently termed portable value tester, you have a certain evolution over time with probably a peak in the first 24 months. And similarly, you have a certain evolution over time of the macro texture. And just the title of this conversation focuses on how much relevant is surface texture. Now, if we look at these simple plots, for sure we see that there are different ways of treating the evolution of friction, and that probably there is something in common with the texture. But the relationships appears quite complex. So we have the doubt that apart from the traffic and from other environmental laws, the texture could be just one secondary cause, or better, a sort of a picture of the current situation. And we need other factors, for example, other mechanical factors to predict the friction over time. So this dependency of the friction on the texture appears a little bit blurry, a little bit complex. When we talk about hydroplaning, speed, there are a lot of relationships in which the hydroplaning speed depends on the macro texture, and so also for the water film depth. So we will find a lot of empirical relationships that come from more or less detailed experimental campaign on a lot of functional properties, or for example also for comfort. When we talk about comfort and we talk about the way of interpreting comfort in terms of spectral texture, we know that there is the possibility to think to the spectral representation of texture in the area of comfort through a coefficient that probably depends really on the comfort in terms of, for example, International Roughness Index. Applies also to rolling resistance. We have had the possibility to listen to a fascinating presentation in which the importance of macro texture in the attempt to describe, to quantify the rolling resistance was highlighted. And here, a lot of relationships too. The problem appears even more complex when we talk about the relationship between the texture and the noise. A lot of empirical efforts and a lot of more or less fundamental efforts. For example, if we think at if we look at the spectral representation of the texture, and if we think to the spectral representation of noise, it is quite genuine and normal to think to a relationship. But we have a lot of fundamental parameters on both the ends of this complex relationship. So we could think to the geometry, we could think to the generation factors or the equation of van der Pol. Roughly speaking, if we think that there is a pavement, if we think that this pavement is can be represented in terms of a stationary and ergodic signal, and so there is the possibility to arrive to have a certain power spectral density, we could think to the possibility to link the PSD of the texture and the spectrum of the noise. And we could think also to link the generation factors of the van der Pol equation to the spectral content of texture. And by the way, there are many studies that partly confirm this standpoint. We are speaking about the relationship between the power spectral density and noise spectrum. Honestly speaking, tire rod noise spectrum. For example, let's think to this contour plot that has been taken from a very recent publication after De Leon, Lisitra, Italia. In the lower part of this blue and red contour plot, we have that there is a positive correlation between the wavelength of the texture spectrum and several frequencies, mainly in the lower part of the spectrum, so lower than 1 kilohertz or something like that. And if we look to the representation of Legge Italia in 1992, there was something similar. This time, distinguishing between a strong correlation for lower frequencies and weak correlation for high frequencies. So in a word, there are a lot of relationships more or less supported by theoretical efforts that say to us that texture is very relevant for the functional properties of a pavement. It is very relevant from a research standpoint. It is very relevant from a theoretical standpoint. But for an engineer, maybe it is not so much, because we need to control, predict, and rule the functional properties starting from the production. So we need theoretical or experimental laws to model the power spectral density, to obtain a given power spectral density based on the elementary processes that happen in the asphalt plant, in the transportation of the mixture, and finally in the laydown on site. So let's think to a packing model. Let's think to the, for example, to the hexagonal packing model as a theoretical representation of a bituminous mixture. Of course, in 3D or in 2D. So if we elaborate on this hexagonal packing, we are able to say that there is a sort of proportionality between the macro texture and the air voids and the radius of the spheres of this theoretical hexagonal packing model. Yes, but the AV, the air void content, in summarizing, is something that I'm not able to govern. I'm able to govern the air void content if I choose a well-known mixture. In that case, yes, I know that an open graded friction course, a porous European asphalt has 20%, and I know that a common dense graded friction course is at 4%. But it is not what I'm looking for. We are looking for a way to rule, to govern the texture based on the elementary operations that happen in the asphalt plant. So we need easy to handle formulas. So AV is not enough. So let us express AV in terms of the volume that fills the skeleton. It is a very easy concept. The volume that fills the skeleton. And this volume is mainly sand, filler, and bitumen. So let's term it filling volume. And let's try to understand if this model really works, considering many types of filling volume expressions, from the simplest to the more complex. Based on that, it is possible to derive expressions in which we have the dependency of the macrotexture on the nominal maximum aggregate size and the filling volume. From the previous formulas to these last formulas, there is just a sort of algebraic manipulation. But we are still talking about an hexagonal packing model and its results. So, in order to understand if this model is really able to predict the macrotexture in very different mixtures we may find in different contract specifications, we considered many mixtures in terms of the first set of mixtures, and also in terms of validation set. And we understood that, yes, the nominal maximum aggregate size and the filling volume are able to explain about the 90% of the variance of the process. Okay, but when we were talking about noise, we have said that understanding, predicting noise is even more complex because we are talking about the prediction of a vector, not the prediction of a scalar. So we are talking about the prediction of a spectrum. But the formula above is just a formula for predicting macrotexture. We don't understand anything about the spectrum, the peak, etc., etc. So let's look at this picture on the right. On the right, we will find a picture, and these are spectra of a lot of mixtures that we practically use every day in the world, including the isomixture, which is the red one, almost the lowest curve. So it is possible to look at this mixture thinking to a sort of curve in which we have usually one main peak, and after we have a sort of long branch on the right, a small curve on the left. But if we look at the x-axis, and if we express the x-axis in terms of a logarithm, this apparent diversity becomes very interesting. And so we are able to model these curves in terms, for example, of a curve with just one peak, two branches, and this dependency is made possible by using a simple absolute value of the logarithm of the ratio between two wavelengths. So we tried to understand if it is possible to have a link between the texture and the aggregate gradation based on these models. So we carry out a lot of analysis considering a calibration set and a validation set. And the validation set was chosen based also on an experimental effort. You know, this element, such as the previous research, are very important. And they are as much important as important is the effort towards mixtures that are low-noise mixtures, not only based on the porous asphalt concept, but also based on the concept of an optimized texture. So these are the results. When we talk about the ISO gradation, we talk about, in practice, of an historical low nominal maximum aggregate size texture. On these experimental efforts and these theoretical efforts, the ISO gradation confirms to constitute still now a benchmark. By referring to the nominal maximum aggregate size concept, small improvements in the aptitude to describe and to predict come from passing from the usual concept of the nominal maximum aggregate size, where we refer to 10%, to similar concepts in which we substituted 10% with 15, with 20, with 70, in order to better describe the importance of the nominal maximum aggregate size, to the end of describing the final results, that is to say, the spectrum of the texture. So, very good results have been obtained through these models, and of course, even better results were obtained by thinking to more complex models in which basically we are speaking about, I'm talking about the blue models, the ones on the right. We're thinking about feeling what the superior skeleton is leaving and iterating this process from higher to the lower gradations. So, in summarizing, we talked about these quite strong relationships between what I feel touching the pavement and many important functional properties. It is enough to think to the friction. But there is a sort of skepticism in considering the texture as the mother of the friction. The only way, the highest level, the best predictor of friction. In the end, we all know that if we choose in a certain way the aggregate gradation, we will obtain a certain spectral texture spectrum. It is absolutely well known. So if we govern the aggregate gradation, we are going to dominate the power spectral densities of the texture. But it is an evidence that the friction evolution or the same texture evolution over time do not depend on the state of the texture at the time t. In other terms, it seems that the condition of the spectra tomorrow for sure depends on the condition of the spectra today, but it is not enough. It is, we could think, for example, to the polish and stall value, to the hardness of the rocks. So there is something else. So this kind of studies in which we are trying to address the evolution of the texture over time or the evolution of friction over time are very complex because we are not able to dominate the texture of tomorrow through the texture of today. It is important, but it is not enough. It is a necessary condition. It is not a sufficient condition. But it is important because we have a lot of contrast specification around the world in which we have at the same time a requirement in terms of, for example, PSV, or in terms of, for example, of hardness of the rocks, and the requirement in terms of friction. So we need to establish a connection between causes and effects. And anyway, these requirements are usually referred to a given type of mixture. So, for example, for an open-graded friction course, we have a certain relationship, more or less implicit, between the PSV and the friction over time. So the friction measured, for example, in the first 180 days, and the friction at the end of the expected life. And so, on the expected life itself. And so, we are talking of money, because we are talking about the expected life of a friction course. So, this is a complex issue, and who knows, maybe that the PSV is enough, maybe it is not enough. I mean, besides the texture. But what can we do today when we talk about texture? We are saying that texture is not enough, but can we still use texture to handle pavement management systems, to handle safety in a given short period? Let's think about sensing systems. Let's think about the possibility to have high-speed measurements or to put a sensor into a tire or to put a sensor within the pavement or to put a sensing system close to the pavement or to use the same autonomous or non-autonomous vehicles and their cameras to the aim of knowing the actual, the today's state of the texture. So in this case, we probably are going to know the level of texture today, and we probably are able to understand, using simple models or using the artificial intelligence, what is expected in terms of the performance. So we are making treasure of the texture. Once we understood that the surface texture is not everything, but it's an important picture of today's state of the functional characteristics, but just today. So for sure there's room to improve our capability to govern the functional properties. For sure, texture is very relevant, but unfortunately, it is not sufficient to govern, to predict the evolution of a given performance, such as friction, such as noise. So we probably will need more data or simply mechanistic properties of the aggregates to understand what is going to happen tomorrow. By the way, we are saying that we need mechanical characteristics, but also the same texture. Today, texture could be very usable to understand tomorrow properties. We mustn't forget that the shape of that pillar may affect his expected life together with the steel and together with the cement percentage. So probably in this sort of bifurcation of the equilibrium, both the mechanistic properties, for example, the hardness of the rock, and the surface texture are going to play a role. I'm talking about the fifth derivative. I'm talking about the evolution of noise or friction over time. So, in summarizing, the habit is the gown. The gown of the monk is very important, but probably it helps understanding today's situation, and it could be useful but not sufficient for tomorrow's situation. After all, tomorrow is another day.
Thank you very much for the inspiring talk, and we will keep the question toward to the end. So the next presenter is going to be Manuel de Costa, and the topic is going to be surface inspection and characteristic textures. Please.
Good afternoon. My name is Manuel Costa. I come from the Department of Physics of the University of Minho, working at the Center of Physics of the University of Minho and of Porto. And I'm a physicist, I'm not a civil engineer. I'm involved in optical metrology for over 3 decades. And for about 2 decades, I was asked to perform the inspection, or if you like, the microtopography inspection of samples used in civil engineering, beginning with granite samples and going for the many types of materials used in civil engineering, and finally, more recently, well, almost 10 years, also with pavements, with asphalt, granite, different kinds of cements, and so on. So this presentation will be a very brief one, and I will just give you a short insight about a rather complex problem. We heard Professor Filippo talk about the difficulty to get a relationship between texture and function. Is indeed a very difficult issue to deal with. And one of the reasons comes from the definition of texture itself. What is texture? And how can we assess it? And that's about that I'm going to talk a little bit in this presentation. So this comes from the abstract of my presentation. The success of a process of evaluating the texture of a surface is highly dependent not only on the meteorological tolerances that are always important in engineering, but also on the particular characteristics of the surface. And here we have another fundamental problem. What is a surface? How to define a surface? A surface is something for a mechanical engineer will be a different thing for an optical engineer. The characteristics of surface, both physical and compositional, but also on what concerns its three-dimensionality. Not only the roughness, the way the height of the surface varies from point to point, but also on the way these irregularities are placed or along the surface itself, on the plane of the surface. When we measure texture, we have to perform some kind of test, we use some kind of method or instrument, and we need and more to perform non-invasive and non-contact measurements in order to reduce uncertainty, in order to not destroy the samples we are working with. Going a little bit to texture here, and if we look at the definition of texture, and Professor Filippo also gave us a very simple, but certainly very complete, and the only definition that we cannot argue is feeling. It has to do with feeling. If you go to the Cambridge Dictionary, you can see texture is the quality of something that can be decided by touch. Something is rough or smooth or soft or hard. It's hard to find something less unclearly defined as texture. And so trying to put a number to something like this is surely not an easy thing. To set a function that will characterize the texture of a surface is certainly not an easy thing to do. Well, if we go to texture of pavements, we can find different definitions here. The texture means, sorry, I have to take out my glasses, smoothness, roughness, or bumpiness of the surface of an object. So what's smoothness, what's roughness, what's bumpiness, Bumpiness is a little bit more clear to understand. If we drive our car on the surface, we'll understand what that bumpiness is. But if we like to characterize it in a quantitative way, it might not be so easy. Road surface characteristics with waves shorter than road surface. And finally, the physical appearance. So, a rather complex thing to do. Texture is rated by definition with touch. And it's true that when we measure texture of different kinds of surfaces, including pavement, initially the measures were done with stylus, with touch sensors that travel over the surface, and by the changing of the height of the surface, there was a signal that was generated. Well, the interaction was a mechanical one, and there was some destruction of the sample, at least potentially. So we have to move to non-invasive, non-contact techniques, and optical inspection methods are surely a good solution. But if we go to optical methods, we have to define what's a soft, what's a hard, what is a smooth, or is a rough surface. And there are many definitions we may use to discriminate between a smooth and a rough surface, but in general, a rough surface, optically, is a surface where the average roughness is in the order of the wavelength of the light that used to illuminate the sample, or to measure the sample, if you'd like. So below that value, we are in the roughness regime, so we have a rough surface, surface with a roughness lower than typically a tenth of micron will be considered a smooth surface and will react on light in a different way. So if we have a smooth surface, light is reflected using the reflection law that is known for many, many centuries, millennia. But if we have a rough surface, light is reflected in a rather complex way. If light shines on an object from a certain direction, light is reflected in all directions in different ways. So we can see the object. You can get some information from the object, but it will be different depending on the direction where we are looking at the surface. And so it is a rather complex process. But we have to deal with it. We have to be able to discriminate between all the characteristics of the texture of a surface. And if you look at this, we have, this is, I think this is an aluminum plate that was textured with a laser. There was an hole inside, and there is a very rough surface here. There is some shape here on the surface. So there is a variety of dimensions of heights that we can observe, but also they are being distributed along the surface in a different way, in different ways. So we have to characterize not only on Z direction, but also on the plane of the sample, the X and Y plane. And also, as I told you, we can have very fine relief structure. So things change along the plane of the surface in a very frequent way, with higher frequency. But we may have also variations that are smoother, that correspond to lower frequencies, to higher wavelengths. And so we discriminate between micro roughness and also macro roughness. Of course, above all these these two dimensions, we have another one. Any object has a form. It can be a flat one, but it can also be the cylinder of a soda can, for instance. So there is the shape of the object, and over the shape of the object, we have the waviness, those irregularities that correspond to a large wavelength, and then the micro roughness, the small bumps and holes that we can find in the surface that will have certainly an important significance if we consider, for instance, if the sample, the surface, is shiny or not, for instance. So in order to separate between those regimes, those roughness regimes, micro and micro roughness, there are different international standards. ISO, you have it here, some, and I'm going to show you the last one that was published quite recently, 2 years ago. But essentially, in order to separate these roughness regimes that might have different functional outputs, we can apply different kinds of filters, from the simple RC filters to double Gaussian filters, and applying, for instance, Fourier transform and Fourier filtering. But one of the most efficient ways of making this discrimination is to use, for instance, the DIN, the German DIN 4760 standard, or the corresponding ICO standard, that is 1851. And essentially, what this standard says is that we are in the micro roughness regime when the relation between the spacing and the height, so relating what happens in the plane of the surface and what happens perpendicular to the plane of the surface, the relation between spacing and depth is of between 5:1 to 100:1. Above that, in the range between 100:1 to 1,000:1, we are in the micro roughness, the waviness regime of the surface. And above 1,000:1, the relation between the wavelength and the height variation, if you like, the mean roughness, we are in the range of the form of the object. So the ISO 4288 gives another way of relating these different ranges of roughness. Sorry, this is in Portuguese, but we don't have time to go through this in depth, just showing the process of using a profile of a sample. This was a thermoplastic rubble that was bent in a certain way. We can adjust a curve and get the form from the surface. We'll get the profile that we usually call the profile P, or total profile of the sample. And this is composed with a roughness or a micro roughness and a waviness or a macro waviness that we can filter, and we'll get the waviness here, large wavelength, smaller frequencies, and the roughness itself. Sorry, the roughness itself, or if you like, the micro roughness itself. Well, time is running very fast. The optical methods made to, or used to, or employed to evaluate the texture of surface are extremely varied. Where I'm going to go through very quickly over the most important ones, and I begin with focus sensing. Focus sensing, essentially, we have a light beam that is focused on the surface, and depending on the way it is focused on the surface and above or below, we are going to get an electronic signal in a detector. This is a fairly easy process to do. We simply move a lens or an optical system up or down. We focus or defocus the signal on the surface, and we get an electronic signal at very high speeds, and we can assess the height of the surface. If we move the surface, we have the profile. If you move it in two different directions, we will have a topographic map of the surface. If you have a confocal structure, so if light comes from a point and is detected in a point-like sensor, we are going to have the confocal microscopes that are also sensors based in focal sensors in a way. If we use not a point of light, but a sheet of light, a plane of light. We have what we call the structural lightning or fringe projection or eventually the triangulation. Usually these three types of methods or systems use triangulation. The fact that the direction of light incident is reflected with the direction of light as it reflected on the surface, and are usually very, very flexible and sturdy, let's say. Optical triangulation is also used with AFMs, and atomic force microscopes are widely used. If you go to a lab to characterize some material, you most likely already use it. The measures are made using a laser with a simple triangulation measure, but the interaction between the tip and the sensor that is and the surface is electromagnetic in a sense. So the way light, the sensor interacts with the sample is quite different from an optical one, or at least is different from an optical one. One of the characteristics of laser light is coherence. And when light is coherent and is reflected in an object, in a surface that is not smooth, a special kind of image is formed. We have this speckle-like image. The illuminated point on the surface looks very complex. And the shape of this distribution will change if the surface changes in a minor way. If it moves a little bit, if temperature changes a little bit, a fraction of a tenth or 100 of degrees centigrade, or if the roughness varies in some way. So we can assess the roughness of the surface using speckle correlation. Ellipsometry is another tool widely used for characterizing materials, not only the composition, but also the texture of the surface. Use essentially the polarization of light. If we look at the way light is reflected on the surface by measuring the amount of light that is reflected in all directions and compare it with the amount of light reflected in the specular direction, so we get the total integrated scattering. And we can use it in a spectrophotometer. Most of them allow these kind of measures that allow us to get the average roughness or the root mean square roughness of the surface. That is the characterization of the micro roughness of the surface in a fairly easy and efficient way. Well, light reflects on the surface in different ways depending on the direction of the shining of light. How much, Simon? 2 minutes, okay. Well, we'll end at that. So if we get the function that relates the intensity, or if you like, the radiance on different directions, and we plot this in function of the directions of the observation of light, we can get different parameters that characterize the surface, including the roughness. Interferometry can also be applied to rough surface like pavements, especially if you use different wavelengths in our interferometers. And of course, we have also the time of flight, the LiDAR, that is more and more used to evaluate the shape, the three-dimensional shape of the surface, including characterization of the textures of bigger objects. Other systems exist that do perform the evaluation of textures, area methods, including 2D image processing with a variety of sensors with a huge number of pixels available, and processing systems that allow us to process information in an extremely fast way are also being used, and increasingly, but there is a problem always in using this kind of systems. We have to make assumptions on the way surface reflects light. And these assumptions are valid for a kind of surface, will not be valid for a different kind of surface. And mostly, and including by the fact that we don't know the light that we are going to receive in a pixel, where it comes from. If it comes from a certain point of surface, or it comes from different points of the surface. So there is a degree of uncertainty that is rather high in these systems, that, however, are extremely efficient because they are extremely fast. In my system, I use a point-by-point triangulation in different approaches. The problem, you have the figures here, the problem is it's extremely slow process. 2,000 points, inspected points, at most in 1 minute. So this is an extremely slow process. So I will end now. If you have any questions, you have my contact here. Oh, another thing that I have to show you is the number of parameters that we use to characterize texture. And this is what we produce in our system as automatically it comes out, this sheet of data, and it's huge. But this is only a small part of the number of the statistical parameters that we have to characterize the surface. We have the 2D parameters and also the 3D parameters that are now used commonly. Well, definition of parameters is here, no problem. We can also get, as we heard about the PSD, the power spectral density function that comes from the Fourier transform of the surface. So we can transform the Cartesian space to a frequency space and get a different picture of the texture of the surface. That is also very, very interesting and give us lots of interesting information.
Okay.
Well, thank you so much.
Okay, thank you very much. I think this is a very interesting talk. I think it's just due to a limited time, so I think we need to stop here, but later on we can follow up with a question. So next presentation is going to be presented by
Good afternoon, everyone. This presentation comes from a work by our PhD student, Wang Tangjie. It's all meant to solve a practical problem. The practical problem of measuring mean texture depth in a road network. Mean texture depth is the most commonly used macro texture pavement index by pavement engineers. In the last 50 years or so, so much data and experience is accumulated on the basis of mean texture depth. Although a definition is given on mean texture depth in ASTM and Euro standard, but the most common definition adopted by pavement engineers on the whole is the measurement made by sand-patch method. In fact, without giving any specific definition, pavement engineers, when come together to discuss about macro texture, we refer to mean texture depth measured by sand-patch method. Well, when it comes to the road network, measuring mean texture become a practical problem. Although today, with a laser profiler, and according to standards like ASTM, many engineers are using mean profile depth, MPD, to estimate mean texture depth. Now, in my opinion, this is totally unsatisfactory. The formula that relates MPD to MTD doesn't work. We all know it doesn't work. When you when you measure the MPD along a pavement section of a certain mixture compared to MPD measure on another road section of a different mix design, you know that the relationship in ASTM doesn't hold. The reason is simple. MPD is a two-dimensional index, while MTD is a three-dimension index. How could you use two-dimensional index to predict a three-dimensional index? It is unacceptable to many of us who know the problems involved in making some such prediction of a three-dimensional index from a two-dimensional index. We are trying to solve the problem in today's presentation. Well, this is the outline of my presentation. MTD is important because it affects drainage, it affects skid resistance, and it affects tire pavement noise. Well, we are not the first trying to attempt to solve this practical problem using readings from laser profilers or the whatever laser devices you have today, obtaining a three-dimensional digital image. From there, we estimate or predict MTD. There are already several methods in the literature adopting this approach. It is the approach that going to solve the problem we have of MTD measurement in the road network. Well, when you look at all this MTD prediction method from three-dimensional digital images, we found a common problem. A common problem of all the methods presented in the literature you can find today. The common problem is that when MTD was calculated from a three-dimensional digital image, it was commonly assumed that the sand field surface will reach the tip of all the peaks. Well, we found that this assumption is not valid. Now look at what we see from the sand patch method we have done. All of us in this room must have done sand patch method yourself. And you may have seen this series of pictures that shows here. When you look at the sand patch and you measure the dimension, you realize that you could see numerous aggregate surface. It is obvious to us, if you look at the lower two graphs, that we actually derive from the three-dimensional digital image that the sand field surface is lower than the peaks of quite a number of aggregates. It is not a valid assumption to say that the sand field surface will reach the tip of a number of peaks on the pavement texture. So it's obvious that those methods that assume the sand field surface will reach the tip of aggregates will not give a correct value of MTD. We will show you, indeed, they did not correctly predict MTD. Well, we would like to introduce the concept of pollination surface, the natural erosion process. In the natural erosion process, the higher hills or peaks will be eroded naturally, and the residue will be brought down to cover the lower portion of the land. And in the end, the land tend to become level. However, in the erosion process, it takes quite a long time to reach the ultimate absolute plain surface. That probably will not reach in a very long time. And what we normally see is a plane surface covered by residue with protruding isolated peaks. Now this erosion, natural erosion process is very similar to what we do in the measurement of MTD using the sand patch method. What we do is to bring the sand, like a residue, into the lower portion of the pavement texture surface. So by making use of this concept of planation, we proceed to derive the top level of the sand field surface. Well, what we do? First, we arrange all the peaks according to the height, and we introduce a point height ratio of each data point, and then arrange them sequentially from the largest point height ratio to the lowest in sequence. Step 1. Step 2, we plot the point height, and you're going to see this. This is a plot of the point height in sequence from the highest peak to the lowest point in the three-dimensional digital image. That is point 2. Step 3, we calculate the derivative of that point height curve. And we found that when we do the second derivative, we are going to get something that looks like the natural eroded planation surface. You have a few isolated peaks represented by the right-hand side of the curve, and then you're going to have a series of peaks that are almost the same in height. And that is what we get. We repeat it for different specimens, at different degree of polish. We found that this is true for any pavement surface at any stage of polishing. We will get the same type of curve. And that is very interesting. So we did a lab study. We have a pavement slab, and we polish it at different levels, and then we pick up the small area that will be covered by our laser sensor. We have 3 for each slab. Totally, we had about 15 such specimens. So we process the laser images, and then we do the step 1, 2, 3, as we can see. Now, this is what we did by having specimen slab of AC13, AC16, SMA 13, AC16, SMA 16. So we have different maximum top size aggregate and different grading. And we did exactly what I described earlier on in the 3 steps, and you could see that is a typical shape of the second derivative we have obtained. We find that by looking at the percentile point height ratio, we obtain something quite interesting. We have the measured MTD, and then we have the calculated MTD, and we look at the percent error of the mean calculated MTD. And we found that from the range of 94th to 96th percentile, it changed to match the measured MTD very well. Well, we thought this percentile that give the correct MTD may vary from mixed type to mixed type. We thought it would, but we were proven wrong. We found that regardless of the mixed type we had, AC13, AC16, SMA 13, SMA 16, we found that percentile from 94th to 96th point height ratio remains the range that will give the best estimation of MTD. Well, we were not quite convinced, and we went on to the field, to the actual road section on the road, at different parts of the road, at different level, different degree of polishing, we did the same. So these are in-service pavements. We've gone through polishing by actual traffic. We found that the same conclusions valid. So in fact, regardless of initial state in the natural erosion process, the ultimate stage is about the same. I think that we could easily appreciate in the natural erosion process. And that probably explains why in the case of pavement, regardless of the type of mixed design, the type of gradation we have, we still get the same trend of behavior. And our conclusion was that we can pick the point height percentile at 94 to 96, and it will give us very good estimation of MTD. We compare it with other method of prediction that I mentioned earlier in the literature. Method A based on the highest peak of a pavement texture surface. Pavement B join all the peaks on the texture surface and calculate the area covered. Method C divide the test area into smaller blocks and then calculates in each block the area covered by a line of the surface that joins the peaks in that block. So these three methods is found in the literature. And we compare our method to the method existing in the literature, and our conclusion clearly shows that our method, based on the natural erosion process that match what we observe in the actual sand patch test, would give the best result. And I would like to conclude that the non-contact MTD measurements from 3D digital images is possible. It will give us reliable estimate of the measured sand patch MTD. And the concept of natural erosion, the concept of planation is applicable. And it's important to know that the sand field surface in the sand patch method doesn't cover the peak of the texture, pavement texture surface. And compared with our existing numerical methods, our proposed method provides more accurate prediction of the measured MTD. Well, I thank you for your attention.
Okay, thank you. So I think we have a next presenter, which is Wood Schwimmen. Next presenter. Is that next presenter here or not? Okay. Oh, okay, the title of presentation is reference calibration. Oh, Wasser's nodding. Okay, you're presenting. Okay. Okay.
Okay. Pointer.
Follow pointer.
Yeah, it's okay. It's okay. It's okay. It's okay. Sorry for the confusion. My name is Luc Hubert. I'm member of this ISO working group 39, which is responsible for the standards for the texture measurement. And this presentation is actually presentation made by Wout Schwanen from M+P, but he couldn't make it. So there are other the people here on the authors are all members of this working group 39, and Thomas Lundberg is our convener, and Ulf Sandberg was our previous convener, and all the other people have more contributed to this work than myself, but they gave me the honor to present it. So it's actually the revision about the work that we did for the revision of part 4 of a standard about spectral analysis of texture. We have, I will discuss the old version of 2008, why we had to do something on it, we had to modify it, and what we have done, and the new, how the new standard looks like. And I will also present the improvements and the comparison with the previous version. Actually, this is, we are actually responsible for 6 standards, and the first one is the wicked standard about MPD. I must say, if I heard the previous contributor. So it's a standard about mean profile depth, and then we have 2, how would I say, supporting standards terminology, and one with space specification of profilometers, and then we have part 4, which is actually still a technical specification, but in the revision it will become a full standard. And that's about the spectral analysis of texture, and texture up to a wavelength of 0.5 meters. So what is larger than 0.5 meter is not in the scope. We have a part 5 as well, which is specifically about megatextures, and this one is under revision currently. And then we have a part 6, which actually only publicly available specification, which is actually a collection of tests that you can do with your profilometer to check if it's working properly. Background, why do we revise this standard? Actually, we have, of course, the phenomenon that the technology is evolving, and texture spectral analysis is more and more common, but it's the standard, the technical specification is actually not so well known. We had some technical problems that popped up. We had the problem of invalid readings that I will come back to. We have a problem that sometimes the evaluation length is a bit short with respect to the maximum wavelength which is considered. The BT product is often not respected. BT, bandwidth times time. In this case, it's actually bandwidth times length. Is often not complied with. And there, in the previous version, we had different ways of doing the spectral analysis, and we got rid of this because we realized that actually a standard is not a kind of a menu that you can choose from whatever you like. We impose one way to do it. So same for the different bandwidths which were available in the previous version, and the different scales, we also got rid of that. So the purpose of this presentation is to inform you, of course, about the revision of this standard, to explain in detail the revision, to show examples, good and bad, to show the validations that we did, and to raise awareness, a little bit of publicity for the standard for our work. So the feature of the old standards, we did have some dropout correction when you have a laser profilometer measuring. Then there is a kind of a linear camera watching the laser spots which is moving over the surface, and sometimes this camera cannot see the laser spot, and then it is mandatory that it says it records it at this point is uncertain, that for instance, if there is a deep hole in the surface, the laser spot disappears into the deep hole for a second. The camera looks at it and then it cannot see it. that is dropout detection, that it says, okay, this value that we measured here is uncertain and we should not take it into account. This is a dropout correction, and this was already foreseen in this standard, but it appears not to be sufficient. We had different methods to perform spectral analysis. We had analog filtering, which is a bit obsolete. We had the constant percentage bandwidth, which is withheld in the new standard, and we also had the fast Fourier transform, which you could use, but we will get rid of this. The uncertainty analysis was present. It was already mandatory, but it was very limited, so we have elaborated it. Some examples of texture spectra from very smooth ones, like the dense asphalt concrete 011, the red curve, and then we have also, this is a quite smooth surface. We go to, for instance, the porous asphalt concrete 016 with an MPD value of 1.45 is a quite rough one, and there's the orange one. So you see that you have typically in the octave bands, you have differences between the smooth and the quite rough surfaces, about 15 decibels. So now about this dropout, where you see the red circles, this is what you see in a rough profile that you measure. Sometimes it goes down very deeply. In fact, in practice, you can get any value. It can go down, but it also can go up. And there's, of course, worse. In this case, it goes down and the value is uncertain. And normally the system itself, it detects that the intensity of the laser spot is too low, and then it says, it puts a flag of uncertain, it's a dropout. So these are the dropouts. But what we also have seen that when you do measurements, that sometimes you get some like spikes. You get higher values and the system says nothing. So it considers it as a valid value. But it is actually a problem because it doesn't make sense often. So it is a kind of an artificial value, and it can peak and it can be quite annoying because it can destroy the measurement, especially when you do this, when you have this in the case of the MPD measurement, but also for the spectral analysis. So this is what we call a spike. So this is to illustrate, you have the original, you have the original analysis in blue. It's quite high. When you do the dropout correction, you get the yellow. You get rid of these values that are invalid, that has been recognized by the system. But when you also remove these spikes, which shouldn't be there, but has not been identified as a bad value, you get actually the real spectrum. You see there is a big difference. There can be, that's not always the case, but there can be a very big difference between what you should have and what you get when you don't do anything about this pre-processing. So this error can be up to 10 decibels, which is quite important. So we can say that the dropout correction, so the correction for the values that are recognized by the system is necessary, but also there is a spike removal necessary. Now, we did some round-robin tests, kind of a round-robin test with the previous version, and there was measurement data which was provided by one of the members. 6 organizations, they processed this same data, the same numerical data, with their in-house software, and the results were compared and analyzed. And what we saw, it was not that dramatic, but we saw some important differences anyway, especially at the larger wavelengths. And this is for one track, for a rougher one, this is for a smoother one, and we also see it here that there are some differences. When you put it, the standard deviation per texture wavelengths, you see that for this long wavelengths, you have quite some high values. You get standard deviations up to 2.5 decibel, which is quite significant, and the average standard deviation was 0.6 decibels. So there is scope for improvement. Because this variation is by the different spectral analysis methods, caused by different spectral analysis methods, and also by the differences in pre-processing. Some people don't remove the spikes, for instance. We had a new, we found out that actually the analog filtering is obsolete, so we got rid of it. The removal of the spikes is essential, and we had already developed a method to remove the spikes in an automatic way, which was already introduced in part 1, so for the MPD calculation. So we copy and pasted it in this new version. And so we limited the way of calculation. So we limited to the constant. So we got a new version. We had this old analog technique is removed. So there is one normative method for spectral analysis, as I said, and we had this removal of dropouts and spikes consistent with part 1. We had some look at the requirements for the shortest and longest wavelengths covered without loss of accuracy. I'll come back to that. So we have the raw surface. We have, first of all, what we do first is the dropout identification and correction by linear interpolation. Then we resample the profile to constant spatial resolution because it is prescribed that the acquisition is made in the time domain. So we resample it to the spatial domain to have constant distances between the data points. Then we might have the spikes, and the spikes are removed, and then we calculate we do the spectral analysis with constant percentage bandwidth filtering according to this IEC standards in thirds of octave bands. Evaluation length. So the evaluation length is the length of the profile that you are doing the calculation on. And of course, this evaluation length is shorter or equal to the length that you have measured. Of course, never greater, which is logic. But the evaluation length influences the longest texture wavelength that you can consider, that you can determine. Typically, the ratio between the evaluation length and the maximum texture wavelength determines the accuracy, and this is independent from the texture wavelengths. So we found if you have, you can perfectly understand that when you have you measure, for instance, a profile of 1 meter length, that you cannot consider the texture wavelength of 1 meter. So you have to have more wavelengths in your evaluation lengths than the length of your largest wavelength. So it is put in the standard now that you have to have at least 12 times the maximum wavelengths for 1/3 octave bands. In that case, you get a good accuracy. For the shorter, on the other side, you have the spatial resolution as the distance between the data points. And of course, if you have a lesser and lesser data points per wavelength, then you get a larger and larger error. If you have at least 5 points per for your shortest wavelength, then you have hardly any influence. But if you have less and less points, then the uncertainty becomes larger and larger. So we require in the standard a minimum of 2.5 points per data points for your in your smallest wavelength to consider. So what we did after all these new specifications, we did a new round-robin tests with the same profiles, and what we got is this. And you would say, well, this is only the result of one, but actually it's the result of the three, but they are all just nicely covering each other. So we have very, very little variation for the porous asphalt, and the same for the SMA. So that looks very, very good. And when we put it in a diagram, the standard deviation, you see it's very, very low. So we get the maximum deviation here at the longest wavelength of 0.7 and an average standard deviation of 0.2 decibels. So it's much, much better than previously. So this is a comparison what we got with the old standard, and this is what we got with the new version. It's not yet a standard; it's still in a committee draft. Conclusions and recommendations. So it was certainly no bad word about the previous version. It was very useful to gather experience and to see where the problems are. But we needed certainly some a better description to reduce the variation. So this new procedure that we have put in the new standards leads to much more reproducible results. It's much better now. So this reference calculation, it's interesting for the users of the standards, and very soon this reference profiles will be available on the ERPUG website, so that everyone can test his or her own software and see if it's good compared to the known result. I thank you for your attention.
Okay, thank you. So we have a next presenter, which is the Pedro Ferreira. By the way, I apologize. I did not control the sound quite well. So I think after this presentation, we will another presentation. Yeah, thank you.
Good afternoon. Not working.
Oh, it should be. So yours is
this.
Yours is this one, yeah, right?
Yes.
Seeing mouse. This is the
Here. It's here, I think. It's working.
Yeah. Okay.
Well, my name is Pedro Ferreira. I'm managing partner of Scurvia. Scurvia owns this equipment that you see, is equipment to do shot blasting on pavements, roads, airports, to rubber removal, and so on. Well, next slide. We will begin here when the rubber meets the asphalt and when we have water in beneath. Continuing, we have this graphic looking on the perspective of the tire. We have new tires, three classes, and we have 3 types of tire, new, 50% of worn out, and legal worn tire limit. It's the minimum that we have. And then we have also the speed. And when we read on this line, we have 50 kilometers, 70 and 90. Practically, the contact zone that is the 3 here, that's the contact zone with the asphalt and the rubber, almost nothing happened. These results are from images of a plate. The speed is measured. The plate is, how can I explain, is acrylic and photographed beneath. And when the speed of the car is 50 kilometers, the footprint is this, 70 is this, and 90 is this. Well, when we have no tread depth enough, 4 millimeters, half of the 8 millimeters, the macro texture that we provided by the tire, it will diminish very, very, very rapid. And because the transparency and it's like a glass, there's no micro texture. There's no texture at all. If we read with the 50 kilometers in the vertical, there's no big problem. We have always some contact zone. At 70, we are losing, and in this part, we have probably in aquaplaning, in the threshold of aquaplaning. And 90 kilometers, well, it's the worst thing that can happen. But happily, we have pavements, even in this smooth and polish, is much better than that, because the pavement will give some structure, some grip to the tire. The most important is highlighted here, is the surface macro and micro must be present always. It's the best in function of speed. Well, I think okay. This is what we must achieve with the pavement, with the aggregate very hardened, and the micro and micro texture must be on this position. The tendency along the years of usage, it becomes from the position A to B. of course, we'll have that situation. It's rough but polished, and that's why the grip or the skid resistance here is high, but here is not so good. Well, I will pass the other ones. Is not. I don't will have talk about that, but I will introduce panic stopping in wet conditions with different tie thread depth. It's very important. It's a small movie, and I think
Feedback from drivers concerned about wet traction as their treads wore down told us it was time to measure the performance of the tires with different tread depths. Our test compared several sets of the same tires with new, worn, and nearly legally worn out tread depths. Our tests consisted of 70-mile-per-hour runs ended by ABS-assisted panic stops on asphalt covered by just 5 to 6/100 of an inch of water, typical of what's experienced during moderate rain showers. Speeds and distances traveled were recorded until the vehicle came to a complete stop. Perhaps the best view for comparing the tires was from the side, where distances were readily apparent. One of the most amazing discoveries was that the sedan equipped with 2 32nd-inch deep tires was still traveling 44 miles an hour when it passed the distance in which the 4 32nd-inch deep tires had brought the vehicle to a complete stop. We then repeated the same evaluations using a popular pickup truck. As expected, even with new tires, the heavier weight pickup took longer to stop than the lighter weight sedan. While the side view comparison again documented the action, it's amazing that neither the 4 32nd nor 2 32nd-inch deep tires could stop the pickup in a distance that kept the vehicle on the screen. And we were again surprised to learn the pickup equipped with the 2 32nd-inch deep tires was still traveling 47 miles an hour when it passed the distance in which the 4 32nd-inch deep tires had brought the pickup to a complete stop.
Well, as we see, the warning, the thread of the tires, they have a significant importance on the distance of stopping. And here, this is the minimum. We never know, for my example, I never know where the wearing of the tire, but this is important to stop very, the tire is very important for that. That's why probably the texture, the micro and micro texture must be on the asphalt because it's the common ground for everything, and we can probably anticipate this kind of problem. Now I'm gonna talk about shot blasting. Shot blasting is the projection of those high carbon steel with various grades. For instance, this one is 3 millimeters diameter, and this one is almost dust. We use usually on our works on highways and roads, and those four, especially this one to that one. And in the interiors, to prepare surface on pavements of industrial pavements, we use usually those small ones. Well, we will see a small movie. Okay.
The danger on roads during heavy rain is the loss of grip between tires and the surface. When the road or runway is new, it has two characteristics, providing a good grip for tires. Macro texture, which is characterized by the spacing and depth between the aggregates and enables optimum draining for the road or runway. Micro texture, which is characterized by the additional asperities on the aggregates that breaks through the film of water and wins contact with tires on wet roads and runways. Over a period of time, and depending on the type of covering, aggregate, and the frequency of traffic, the rubber marks left by car or aircraft tires will gradually make the aggregate smooth and eliminate the micro texture. Soil on the road or runway surface will eliminate the macro roughness. Without macro texture, the covering no longer helps to drain the water from the road or runway, and the film of water that then appears on the surface is responsible for aquaplaning. In order to reduce accidents on roads and runways, and to make our roads and runways safer, the roughness and skid resistance has to be upgraded to its original value. It is only a mechanical action that can recreate both the macro and micro texture needed for ensuring a safe process. Thanks to the Blast Track non-destructive shot blasting technology, we are able to regenerate both macro and micro structure to its original value, and most of the times even better. In this animation, we briefly show you the working principle of the Blast Track truck with the 2-45D blast head in front, and the efficiency of the new improved process of dust handling. The blast head throws little steel balls called shot with high velocity onto the surface to be treated. The steel balls simultaneously create both micro and macro structure on the surface. Skid resistance figures can be improved up to 100% compared to the value before shot blasting. The 2-45D blast unit is able to throw up to 800 kilograms per minute of these little steel balls onto the surface. While blasting roads or highways, big quantities of debris are produced. Depending on the surface, concrete or asphalt, and the grade of pollution, debris production can vary between 1 and 2 tons per hour.
The truck is that one, and this one is a small ride-on articulated that we use for roundabouts and small spaces. The other one is for highways, runways on the airport to remove rubber, and so on. There are some aspects. We also use shot blasting to remove paint, to remove horizontal marks, and those are in the airports and airfields. This is two kinds of pavements. That one this one is before shot blasting, is typical. The aggregate is basalt, and the small aggregate is limestone. And limestone, it dissolves with water, and probably here what we see is a very polished aggregate, and the rubber of the tires, they are here vulcanized, and that's why the polishing. After shot blasting, this is the same pavement, and the pavement here is blast and is not. We see that one passage, 1.2 meters of wide, and look at the top without damaging. It's only to give mostly micro texture. Those are results before and after with the screen, with not screen, but with a grip tester. And we see the evolution from before and after. Well, the benefits improve the coefficient of friction, contributes to the lowest carbon footprint, recycles the steel shot. That material, the steel shot, is running inside of the machine, and we don't need any kind of water and that's why it's environmentally friendly. And contributes also to the extension of lifespan of pavement. We have a typical behavior of the new asphalt layer. The first 3 months we have a coating of bitumen, and then in the beginning the values are not so high, but with the time and the traffic it increases until gets the maximum. And then we have, it depends on the aggregate, if it's hard or soft. We can have probably this time between interventions. Here, if at this point the road is needed for intervention, if we do shot blasting, probably it repeat the characteristics in the beginning of the pavement. More probably is not more, but at least the behavior or the performance of shot blasting is directly with the quality of aggregates and bitumen. This is a characterization of pavement before and after. It was a study made by University of Minho, and we see it on A4, the truck over there, and the first passage we measure with this vehicle, with the laser for MBPD, and the results almost nothing special, one side on the other. It was almost the same. Because the aggregate was hard, there's no clogging, and then the measure of grip. We have well, I think it's to finish. Yes. Okay.
Okay. Thank you very much. Okay. Thank you. So we have. Sorry, the time is tight. So I think we have a last presenter, and then we'll finish this section here. So I apologize. I think the last presenter is the Mariela. Okay, and then the topic is the evaluation of the braking performance of the autonomous shuttles. Yeah. Go ahead, please.
Good afternoon. I am Manuela, and I will present. It's my pleasure to introduce the ENA project. It's a project about the experiments with autonomous shuttle. So I will make a short presentation to show the evaluation of the brake performance of this vehicle and show the impact of the pavement texture, speed, and water weight. So the ENA project is about the experiments with autonomous shuttle. ENA consortium responded to a call for project to set up experiments of autonomous shuttle in different areas. The goal is to improve the mobility in urban and in rural areas, and offering on-demand mobility service in sparsely populated rural areas, and complementing the existing urban transport network. This project is coordinated by University Gustavo Eiffel, and we have also academic experts and the partners, industrial partners. Air safety is very important for us, so before that passenger go on board in the vehicle autonomous, we make tests. We make tests in our test track inland to recreate a real-life situation. So I will show you some results. So the objective of our laboratory in this project is carrying out tests to evaluate the comfort and the safety of the user. So we realize the brake testing in our test track in various situations and in different surfaces. So about the autonomous vehicle, so an autonomous car are vehicles that operate without human intervention, and thanks to advanced technology with the lidars, the cameras, and the artificial intelligence. Today actually we have 6 levels of autonomous, vary to level 0 to level 5, and level 0 is a fully manual vehicle, and level 5 is a completely autonomous vehicle without human intervention. The autonomous vehicle used in our project operates at level 3 and 4. Sometimes it can operate without human intervention, and sometimes we have to conduct it in your itinerary. So it's a 100% electric and autonomous vehicle, capacity to 15 persons, and the speed is until 20 km/h, so not so high speed, and is a symmetric vehicle, so it can drive in both directions. And so to simplify how autonomous vehicle works, imagine you navigate a city with a GPS or a maps, and similarly the shuttle, as already mapped, it 3D surrounds. So as it travels, it compares the recorded data to detect the difference between the data outside the computer and the surround. And when it encounters an obstacle, the shuttle promptly stops to ensure the safety of the passenger and to avoid the collision. So for the configuration of the test tracks, we went on the community of Cœur de Berne. This is a case of a student in the project to measure the properties of the surface. And after we select 3 surfaces on our test track, one surface similar to the case of study, and to another surface with the properties different. So here I have the small pictures of the surface and the characteristic of the macro texture and the micro texture. And all test was made in the dry condition and wet condition, so with a film of water between 0.2 and 0.5, and a very wet condition with a water depth of plus than 0.5 millimeters. For the braking methodology, during the brake test, we have to use the autonomous vehicle, we have to create paths with using software. So the vehicle, we have to conduct manually the vehicle using a joystick of like a PlayStation 1. So to conduct the vehicle until the paths. So once the vehicle is on the path programmed, we can launch the vehicle, and in this time it can driving in autonomous mode. For the paths, we can choose the speed, the acceleration, deceleration, and the itinerary. So we create the paths on our test track. So you can see here is the itinerary where vehicle will ride. And also we make an instrumentation, a very light instrumentation using the accelerometer, triaxial one and uniaxial in 4 points of the vehicle. So here a small video to show. We put I don't can I say this in English to make where the brake test will start. And for the brake methodology, we use, so I said 3 surface, 3 speed, and 3 wetting, and 2 kinds of braking. So emergency braking to simulate the presence of an obstacle. So for this, we don't put the obstacle. We use the button of emergency to brake the shuttle each time in the same point. And in the programmed brake, in our path, we programmed a stop station, and the shuttle brake automatically when it arrives in the station. Here we have some results of the emergency brake. So we looked at how different surface conditions of pavement affect emergency brake. So the graph showed the deceleration values for emergency braking. There was little variation in the average and the maximum deceleration during emergency braking across different surface conditions or pavement types. The average deceleration values was around 3.7 and per second square, and the maximum value was around 7 meters per second, 7. And independent of the set point acceleration and the speed, we have these values of emergency brake. I'm sorry, deceleration. I have a problem here in the title. For the programmed braking, we have some curves of deceleration, and here we can see here in this part is when I put a cable grommet on the track to analyze the shuttle brake behavior. We have some deceleration curve of the shuttle during programmed braking, and we have analyzed how the shuttle behaves when different values of deceleration and speed are reused. We found that the shuttle adjusts its braking process according to its rolling speed to achieve the desired stop point. However, there are some issues that we need to consider. Firstly, the shuttle does not always follow this deceleration instruction. On the paths we program, we use a set deceleration. So we ask the shuttle to use this deceleration for braking, but they don't respect each time this consignment. So when the acceleration set point is to 1 meters per second square, here, I'm sorry, here is 0.5 in the 1, the shuttle does not comply with the set point. So this result is a high peak deceleration, which can be uncomfortable for the passenger. So when shuttle braking, we have the comfort on the shuttle is not so good. Secondly, we observe that the deceleration peaks are weaker when the shuttle is moved at a high speed. This means that the brake process takes longer at a high speed. Additionally, the shuttle's brake has 2 peaks and a speed rebound, which can also be uncomfortable for the passenger. With the curves, we calculate the brake distance. So for the calculate of the brake distance, the shuttle, we use a filter, a median filter and a Gaussian filter to remove the noise, and no constant deceleration to calculate using infinitesimal stepping, considering constant deceleration at each step. So we use this equation for the calculate at each step, though is the sum of each small distance. And here we have some results for the emergency brake. We see the impact of pavement texture, and here we have the three surface and the 3 wetting state of surface. And for the emergency brake, we have around 5 meters, and in the programmed brake around 50 meters, and we don't have a significant difference between different surface, probably due the speed that was very, very small, only 20 km/h. And brake distance, we see the impact of the speed, and we have 3 speed here, and the values of emergency and program brake distance vary depending on the speed of the shuttle, and the level of wetness had a little effect on the brake distance values. For the program braking, we have a big difference between 3 and 5, because the shuttle knows that it will brake, so it programmed very, very early the beginning of the braking process. I will come back here just to show, and here we have the shuttle use 5 meters per second, and here 3. And we see in the black point, it start the process of brake. So it's very long. And here, shuttle start the process of brake very, very late. We compared with this, and for this we have a very long distance brake. And here we see the effect of set point deceleration in the distance braking. So for the emergency braking, the shuttle don't take into account the set deceleration because shuttle is in a emergency mode. So it will forget the set deceleration, and it will use the emergency parameters. And here, in the programmed braking, when you use a different set deceleration, the distance of braking will be different. So with a a superior values of set deceleration, we have a small distance of brake. So to conclude, we have conducted a brake test both in programmed and emergency braking in autonomous shuttle at University Gustavo Eiffel University Test Track in Nantes. Our findings have shown that the emergency brake distance values vary depending on the shuttle speed. No significant difference was observed in the brake distance when the wetness of the surface was taken into account, possibly due to the shuttle low speed, very low speed. We also found that the set deceleration plays a crucial role in reducing the shuttle brake distance in programmed mode. However, we did observe that a speed rebound after the initial braking phase, which may be uncomfortable for the passenger. In conclusion, our findings suggest that understanding the dynamic of autonomous vehicle is crucial for ensuring safe and comfortable transportation. So we will continue to analyze our results to further improve the performance of the shuttle. Thank you for your attention.
Okay, I think with that, since time is tight, I think, but I think those talk there are very good, especially there's a cover different topic from some of the quite inspiring talk to the end, some of the application. However, I think this is like only 20 minutes to the next section. So with that, I think we will stop here. So please join me still kind of thank you for all the presenter and for their excellent presentation. So we'll take a 20 minutes break and then we're coming to the next section. Okay, thank you. Hey, do you know there's a timer or something? I think I try to put in that so that way that's easier. Do you know there's a timer that I can control? Because I feel that would be better. For example, you can set up a clock. Show it to me, I can see that.
May I look at this?
Because I believe, hold on a second,
Polar is that
Yeah,
the
it is.
movie. Take away.
Delete.
And then number one. They want to do.
One, F2. Okay, you want a pen?
Oh yeah. Thank you.
This one to take out.
Take out. Oh, no, no.
Your pen is here. Is that no?
Yeah, no, 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 no. Where is it? Oh, photos of the first two second one.
Is this,
Copy,
oh,
copy,
everything?
copy, everything.
That will be for closing.
Not for closer.
I'll
You can choose some photos from.
copy everything here.
At least this one.
And what do I do with this one?
Just leave it. All these photos for you. You can choose some useful for you.
Okay.
This is a funnel.
Mm-hmm. But it was to presenting at the end?
No, 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 no. Only into the Professor Bar. During the break, they can display this kind of the photos.
Oh, oh. Thank you. Mm-hmm.
Let's start next session.
In 20 minutes. tomorrow morning, yours? That one?
Yes.
So good afternoon. Good afternoon and welcome to this new session. The title of the session is Condition Data Collection and Analysis. And Professor James Tsai is going to talk about automated pavement condition evaluation using 3D technology and machine learning. Professor James Tsai is currently a professor in the School of Civil and Environmental Engineering and also an adjunct professor in the School of Electrical and Computer Engineering at Georgia Tech. His research focuses on the development of spatial information and sensing optimization methodologies, concentrating on applications to roadway infrastructure, health and safety condition evaluation, prediction and management with a special emphasis on pavements, sidewalks and science assets. His research project has been competitively selected for the 2017 Harstor High Value Research Award, National Award, because of the successful implementation of 3D laser technologies for AI on a large-scale system. Since 2010, he has served as the associate editor of ASCE Journal of Computing in Civil Engineer. Please join me in welcoming Professor James Tsai.
Okay, thank you very much for the introduction. First of all, thank you for the Paula, inviting me to give a talk. And then thank you for the community organized such a wonderful event. I learned a whole lot through the process too. So today what I'm going to share with you is automatically 3D pavement condition evaluation using machine learning. So specifically, I want to give you an update in terms of what in the U.S. up-to-date technology and the implementation in the U.S. as well as in our research team, especially focus on automatically condition evaluation system. Since through the past 12 years, we have contributed a lot in the U.S. In this area. And a lot of the technology, the one I showed it to you, is already implemented. And then we kind of looking for the next stage there, which is so much data you collected, how do you utilize that to create a new value, new knowledge? That's what we're interested in. So as the one underneath there is related for optimized payment assets management, because you have such enormous the payment distress data, how do you utilize them? So this slide here is kind of showed it to you in terms of outline for my presentation. And so I'm going to share with you what's my research team. I kind of start with some of the key takeaways, which is the end, what I'm going to deliver in terms of some of the key message there. And I'm going to share with you what's the 3D laser technology and then how that become popular in the US as well as worldwide. We probably worldwide #1 start with this technology, and then that was back to 2010, with a $3.7 million US DOT project with the 2 phases. And then almost, we're kind of using LCMS sensing system, and almost 5 years, probably nobody used that. Until right now, it's become a popular technology. Almost more than 90% of US DOT, they are using that. In a minute, I will share that with you. Even some of the state DOT, like Georgia DOT, Texas DOT, they collected more than 4 years data for the whole entire state. So this is a quite popular, kind of common practice now. So I'll share with you where I'm located in Georgia Tech. It's located in the Atlanta 1996 Olympic game. And so it's a business airport, in the US as well as in the world. And then also CDC, the headquarters, CDC, CNN, UPS, as well as Delta Airline, Home Depot, etc. They are all located in the Atlanta. This is my research team. I have a quite diverse team, a fair amount of them in the structure, transportation, construction management, as well as I'm guiding electrical computer engineering PhD, as well as computer science, as well as ISYE, so I can easily do a lot of innovative research. And then Georgia Tech overall is quite well known in engineer school. So all the 11 schools, they all at least in the top 10 in the US. A lot of them, they're almost number one, continue more than 28 years, like industrial engineering. So I think the blue color indicates the student I have in my team. They are coming from quite a diverse group in different major. This is one kind of share with you what some of the key takeaway that we have in terms of 3D technology. The one I share with you is already become a mainstream technology in the US. There's more than 90% of the state DOT, they use that for automatically payment condition evaluation. And some of the state DOT, as earlier I mentioned about, they collect more than 4 years data. So it's not just starting this year or last year. No, it's been for a while already. And it's an implement that is quite popular now. And the other one there, machine learning, has provided excellent means to support automatically detect and classify payment distresses. And a standardized payment performance evaluation is quite important, and I think this is the one I'm going to touch on. And because so many people, so many paper every year, that in just crack detection, I think more than hundreds paper, but hey, you detect 90% and he detects 75%, does that mean anything? Probably doesn't mean anything. Because they are testing different performance evaluation, they are testing using different data set. Some of those, they are even consistent data set, not diverse conditions. So what do you compare with? Therefore, I think hindered the entire advancement of the automatically payment distress condition in our industry. So how do we make the advance of the science and forward? The other one there, QA/QC, I think this data here has become popular. I think when we set a goal, typically in my research team, we set a goal in 10 years. We should change the US as well as change worldwide. I think that was 10, 12 years ago we set, and we achieved this one here. And so QA/QC is another one there is quite important because most of the state DOT, like Texas DOT, to collect the data, I think it's more than 4 years now. And then now they recognize the data quality is an issue. Sometimes it's there's no treatment being applied. How come next year the treatment, the rating has become better? So sometimes the one that we just finished, so we kind of finished the technical standard in the US, the AASHTO MP47, which is the open format standard, try to improve the utilization of the data. As well as we just published, which is not published yet, we just complete after 4 years, another 8 technical standard about the 3D data. Because 3D data now is kind of, it can collect the IRI, collect the rotting, cracking, and all different kind of distresses, even the texture itself. But how did you know the quality of the data itself? So I think it's kind of quite important to set up a standard similar to IRI to have a standard procedure. So that's, we're kind of setting that up. So for 50 state data, I think they can follow up. The other one there is a new performance indicator. This one here is try to share with you is an analogy to medical area. Long time ago when people putting the CT and MRI, people, all the doctors there 50 years ago, they probably don't know what is technology about. So they still, the doctors still haven't changed their mindset. So all they do is just using X-rays approach to differentiate tumor and cancer. That's probably what our industry now is doing. Really did not reveal the data, the advantage of that very detailed data. So that is related to It took almost 10, 20, 30 years, so medical industry understand that. So they take advantage of CT and MRI, and they know that there are different signature representing tumor and cancer, as well as higher, not 1 centimeter, but sub-millimeter. So can we apply that concept in our industry? This is high, much detailed resolution of data. So most of the people is just using copy the past 40 years, the payment type and distress, just automate them. I think that's a little bit overkill for the technology itself. So in our thinking, can we create some value out of this data? Which is previously, yesterday, there's a lot of discussion. Data itself is mean nothing. Only you create a value itself. So this is the one I kind of share with you, just a couple of them there in terms of how you create a value, new performance indicator, which is previously doesn't exist. The next one there is related crack fundamental element there. So keep in mind, right now this detailed data there is collect the whole entire Texas, the entire Georgia, right? It's a laboratory research grade data. And then you have all the detailed topology. So the imagination is about, this is a detailed behavior change. It's in the research grade. It's a large scale real world situation. And so there's a huge amount of analysis you can analyze. So in a minute, I think I will share with you what's my thought on that, so move forward. The other one there is kind of share with you the second bullet item there, what we can move forward on this one here. Can I apply the concept in medical? In a way, traditionally, if your arm have a problem there, then probably you just cut off your arm because there's no precision condition assessment. So the same thing there for us in our industry. A lot of time at 1 mile is a condition, you got only 1 rating. You do not know the detail. But right now, with a lot of detail resolution, we're talking about 3R, right time, right treatment, right location. Now we can use that to entirely change our payment access management. So how we revolutionize the whole thing. So this is just beginning. Most of the people, they haven't get to that. They just try to using the, basically the sensing technology, even automatically extract the data in an old-fashioned way. But there's an opportunity there, which is if you're using medical industry, you can kind of have a lot of imagination to change our industry. And the whole key there is to cut down the money. If you're thinking about Florida DOT 1 year, 1 year's payment resurfacing budget, how much that is? It's $1 billion. So if you can cut down that $1 billion, just 5% or certain percentage, a huge amount of money you can cut down. The other one there is expanding this data here. This data here is a very, very detailed data. Can we expand that beyond what we are using? Yes. Can we using this one here to support? Right now, most of the time, we just support that for what? For payment planning, because every year you need to do prioritization. But right now, like a Texas DOT, we are working with them. They try to thinking about, can I do the machine, the crack seeding quantitative analysis in the project label, not an AWAR label. Can I using that to support machine guided the crack sealing, crack filling? So there's a lot more can do because this is detailed data. And then we did in almost 10 years ago, well, 8 years ago, the project we have is to micro-meaning. When you do the meaning there, how did you control the quality? Because it's a non-traditional meaning. So you use the 3D technology to do the meaning quality control with a new performance indicator in construction quality. So all of those there exist, and we are already putting that in Texas, in Georgia DOT's construction quality control using 3D technology. This is the one can be used in the safe navigation of connect vehicle, autonomous vehicle too. So how do we be able to broaden the impact of our payment industry to autonomously connected and autonomous vehicle? So there's opportunity on that. And this data here, can it provide a rolling resistance? Because thinking about this is not just 1,000 mile, it's 100,000 mile, whole US already collected, and every year. So anyway, just kind of broaden the impact. And there's, I think Europe are getting more and more, they're using this data here too. So what is 3D data? So the 3D data itself, Let me also check my time there, so make sure I know the time. So this I kind of share with you using this project here. This is one of where we started with the US DOT project. We compared selected. So this is a sensing vehicle. And then, so we have a laser on the right-hand side. The blue color is the one I'm going to talk about. But the system we have 10 years ago setting up, we have a LiDAR, we have camera, and the IMU system, as well as the 3D laser. And what's the system about the 3D laser data that I've showed it to you? This is the one I showed it to you now. You can see the system itself. The concept is very simple, which is the previous, the section that people are talking about triangulation. So that's kind of a simple concept there, almost exists in the physics a long time ago. However, this performance has become possible after the advance of laser technology. So you can see the driving direction is almost the 4,000 point in 4 meters. So it's a 1 millimeter resolution. And then driving direction in longitudinal direction is quite a 1 to 5 millimeter resolution, depends on how you set. And Z is 0.5 millimeter. And this is driving speed. It's 100 kilometer per hour. So you can collect all the detailed data here. And then this is the one that is the one I showed it to you. If you look at this data here, you can see that this is the data collect on the interstate highway. This is a manhole. And you can see the detailed data there that you can see that I just highlight a specific spot here. For example, this is a spot here. There's an aggregate loss, and it's 4 millimeter. So when you're driving 100 kilometer on the interstate highway, you kind of easily see this is a 4 millimeter aggregate loss. And you will say what to do with the data. Data mean nothing, only you create a value. A lot of time we're talking about climate change, sustainability. You're talking about loss aggregate because the snow hitting Atlanta in 2010, right? So can you using the technology to say that this is the one originally only 2% of aggregate loss, but now it's 4%. So my pavement life originally lasts 10 years, but now cut down to just 8 years. So 20% loss of the infrastructure life, which is out of my $100 billion of assets. So that way you have idea. Can you use this one here to find out where's the weakest link? How come this location here deteriorates so quickly after a big snow or extreme weather? How come this location here does not change? Extreme weather condition is still deteriorate not. So a lot of time in the past, most of the project there, research people just talk about sustainability. But I think with the technology, we can move next step to actually measure the system. Keep in mind, this is in the system in the entire Georgia or in the entire US already collected, right? How do we create a value to utilize that? This is the other one there that if you not look at the texture, this is just one wheel path, 2 meter. So this is close to Savannah Port, it's a heavy loading. So this is roughly 2 inch of the wheel path. And what does that mean? Traditionally, we set up in pavement just 1D rod depth, but now it's 3D rod shape now. So vehicle loss control, etc. Now I can trigger the maintenance using the rod shape because this data here now is commonly collected. So can you define it differently? Can you define the loss control? Can you define this is the one impact the autonomous vehicle, connect vehicle? Since this data here is every roadway there in the US being collected, right? Every year, now it's 4 years. So there's a lot of opportunity on this one here, be able to create it. And this is what I showed it to you on the top, indicating that's what we are doing using this data here for. Most of the industry there in collecting that. But what I'm thinking about, can we create one that, so in our PSI, the national standard MP, AASHTO MP 47, we kind of put in there specific, this data, the one we created open format, support OpenCRG, which is CAV, the connect vehicle, autonomous vehicle. Because I'm interested to making a link between our industry payment data and autonomous vehicle, connect vehicle, so that we can contribute to that area there tangibly. So this is the one that why the 3D data is one help us. So this is one that, as you can see on the bottom there, traditionally it's using 2D image. And the issue there is related to lighting, always a big issue. So on the top there that you can see that's nighttime, and then there's a shadow, and daytime, no shadow. But all of them, the cracking using the 3D system, it doesn't matter. Because the nature there, the 2D lighting is based on intensity, but 3D is based on elevation difference. So there's no elevation difference, no matter it's night, or there's a shadow or something. So there's no difference. So you can see their crack detection is the same. They are all 90% or 99% the same. On the right-hand side, you can see that if it's based on 2D image, it's very difficult. You see that this is OGFC. There's a crack, but it's so difficult to see, right? But if you look at the 3D image elevation difference, it becomes so easy to see. So in a way that it has its advantage, so that way the technology suddenly move forward very quickly. And this is the one kind of showed it to you, the crack detection here. And I kind of move forward there, say that this is the one that through the time, the detection, this is kind of show that to you in terms of the automatically data acquisition and changed in terms of from 2D and to 3D. And this slide here try to show it to you in the history, the one that we did. At the very beginning, we started sponsored by US DOT. So this is the first research project supported by the US DOT to evaluate this since 2010. And through the time, we kind of putting a lot of effort, develop the algorithm, start on crack detection and its deterioration, rotting, concrete joint, and then even construction quality, micro-meaning, and then as well as the faulting measurement and all of those there. The 2015, I think we also have the NCHRP idea, innovation, deserving exploratory analysis regarding the loss aggregate using 3D technology. We competitively selected. 2017, we received a national award because we implement that with machine learning and 3D technology on the entire Georgia's interstate highway system. So this is not a research only, it's been implemented. So 2018 there, that I think I kind of give a talk, the lecture, entire US. So it's about a pavement maintenance programming using the 3D laser technology, because this one here gradually changed the whole operation there. So there's more than 300 people registered to the class. And this is the one as earlier I mentioned about we putting the PSI, the open format standard, because right now I believe European country, I think you're using like LCMS, etc. But a lot of time this is proprietary format. You cannot even use it. And so in the US, they're putting a lot of effort to try to putting that as an open format. So I'm a PI, we putting the format there called PSI, which is open format. Every people can use that. In the meantime, I think we also finished another project with another 8 technical standard about the quality itself, because you collect so much money spent, collect so many data, how you ensure the quality. Keep in mind, this is much, much larger than IRI. IRI is just part of the outcome for this. You collect the texture, you collect cracking, rotting, everything. So how do you ensure the data quality itself? So we kind of spent 4 years sponsored by the NCHRP to putting the standard too. So this is the other one there. And so 2021 there, this is the one that we kind of keep a keynote speech in terms of this data here is so much detail. How can we utilize the data itself? Because this is going to be quite a big change in the US as well as worldwide. And 2022, I think in the TRP, there's a special section and kind of give a talk. It's automatically payment condition evaluation, as well as later on give a keynote in Japan in terms of how to utilize 3D system. So those are just some of the highlight in terms of what we are doing. This is the one I'm going to share with you in terms of automatically data collection, show you some example here. So traditionally, people kind of define this variable in here in quantitatively, label 1, 2, 3, right? It's kind of human health condition assessment. On the bottom there is severity level 1, 2, 3. I think a little bit loss of aggregate. And now you're getting more and more loss of aggregate in the wheel path. Now the whole thing peeling off. And so in this specific case here, the project was sponsored by NCHRP, Innovation Design Exploratory Analysis. This is almost we finished in 2015. So you'll be able to classify those into 3 different categories. So in a way, instead of traditionally manual assessment, now this is the automatically assessment. This is the one kind of heading to the Atlanta. So you can see there's no loss of aggregate. So the system itself automatically detect and assess. This is the indicator there's a severity level 1 loss of aggregate. And then this is the one kind of move forward toward to Atlanta. And this is kind of severity level 3. There's a fair amount of aggregate lost. So you're using machine learning and 3D technology automatically detect them. This is the one kind of showed kind of continuously that we automatically using the, there's a 10 different distress in Georgia DOT. I kind of managed Georgia Department's transportation almost 20 years. We're putting a payment management system for them and implement for them. So now I think you need to replace with the 3D technology. So cracking here, you can see there's different definition, low cracking, severity level 1, 2, 3, 4. And then in the case here, block cracking. And so in a way that this is kind of one of the AI confusing. I'm the associate editor, review so many paper. A lot of people just publish the AI, but sometimes they don't know what they are doing. And so, for example, this is crack detection. Some of the people say, oh, this image has crack, no crack. Or this polygon here has crack, no crack. That's an AI test definition. Can they help your payment management system? And this is the one say that those pixel there has a crack, no crack. So I can define it on the wheel path, non-wheel path, crack direction, etc. So a lot of time, a lot of automatically crack detection does not help you agency at all. It's just called automatic crack detection, but they may not define or formulate a problem correctly. But it's just a paper they can publish. So this is the one, another issue there we find out that, as earlier mentioned about, we're kind of putting a comprehensive quantitative crack detection algorithm. We find out the industry need is not short of detect the developmental cracking algorithm, but it's short of a standard to evaluate them. So a lot of time your algorithm is 70% accuracy. The other one there, I get it 90%, but how do I know which one is good or which one is bad? So this one here, we kind of set up, one is performance matrix, standardize that based on medical, how the medical use. Because the algorithm itself, a lot of students I have, they're also working on medical. In the middle there is what kind of data diversity I can use. And then we come out with your score. I can tell you your score is 63. But you are working well, it's the OGFC, or you are working very well in concrete, or the complicated cracking, or what's the different crack width, and then what's the detailed distress. So there are 3 labels of output, give that to you, and we try to putting this into a website so every people can play with. We try to put in a game and with 3D data so that every people worldwide can play with that, and they can come out with using their algorithm and then see how that is their consistent data set, consistent performance measure. So there's a website there too. This is the one that we putting together, and this is 3D data on the left-hand side. In the middle there is a crack detection, different color, indicate different crack width. So through the automatically detection and classification, you can see on the right-hand side, it's automatically classified what kind of cracking and detection, etc. So we finished that on the entire interstate highway in 2017 and received a national award. And in a way, it's not research stage, it's operation. So later on, then they routinely collect the data that way. So this is kind of showed it to you. 2 years later, I think at the very beginning, we did not cover the concrete pavement, which is gray color. But 2 years later, I think we're including the concrete pavement too in the whole process. So this is the one kind I want to show it to you. Previously, there's a question in terms of, you got so many data here, what can you do different beyond what traditionally do? Because the previous section I talked to you so far is just automated, what people already done. But we can do something differently. how do we do something different? As earlier I mentioned about medical cases there. So this is the one, how do we come out with innovation? Innovation coming from, now I have this detailed data now available. So traditionally there's a distress type and severity label. So it's been defined. Because 40 years ago, people can see only that type of distress. But now the computer see differently. But how do I create differently? So how do I innovate? And the way you did is just determine what's treatment method and treatment timing. Those are the same as medical. So how did you define, can I determine some of the detailed distress can support machine-guided crack sealing? Can I have some distresses be able to support determine the treatment timing, etc.? Now I have a detailed data. Then I think this is the one I presented in Cambridge University when I was invited to give a talk. So I need a topological mathematical framework to support this. So I detect the cracking. The crack itself has what? Has location, has extent, have the width, even the depth itself, orientation. Now it grow up into intersection point. So you have intersection point. And you will say intersection point, is that important to crack timing and crack treatment method? It is. And how come 40 years ago they did not detect that? Well, it's quite clear. It's impossible 40 years ago to detect that. But right now it's available. And this is the one that timing there is spalling, right? How big the polygon there. So this is the one that actual data, you can see the real world is available, right? It's just the lab research grade. And you can see those, the one 2021, 2013. You can see there's a different cracking, how they grow. A lot of time we think mechanical engineering and then pavement design, we're assuming what we did is correct. So, but I think, is that still true or not? This is the one kind of allow us to, this 100 feet. Now I start looking at topology. You can see that how they grow, right? 2011, this is the one I look at the grow, okay. I look at the grow in terms of crack, right? Length, and then this one here, you can see that I divided them into two different types, on the wheel path, non-wheel path. I can see in this 2011, 2013, you can see that blue color, which is indicating on the wheel path, it deteriorates much faster. So I can see, can I see that, because I have a topology, I can analyze whatever I want, right? I can see this longitudinal and transverse and where they grow. You can see this period of time, transverse cracking, growing much faster. And why? So I think in a way it provides a mechanism for you to see, then for you to ask question, why this perform this way? This is the one, the intersection point, right? So the intersection growing in that 100 feet, can you correlate this one here with the correct, the treatment timing as well as the treatment method? Yes. How about the spalling, the polygon size, right? How many polygon there? And can you add in another dimension there, which is polygon size? Because cracking may be different size there, right? And different number, and a long different time there in 10 years. So with that associated with treatment timing. So I'm not necessarily provide the solution yet, but this is the one we published already. Basically just say that this is similar to medical industry, which is long time ago when they have a CT and MRI. At the very beginning, they don't know how to use those doctor, right? They're just using X-ray, but later on, I think they come up with something that be able to differentiate the tumor and cancer much earlier, and you can treat that much earlier and to save the people's life. And this can prolong the pavement life in a low-cost approach. This is just kind of showing the, in terms of the rotting deterioration. You can do that not only cracking too with this 3D data. So I'm not going to repeat, this is the end, key takeaway. So I kind of talking about 3D. This is the end of my presentation. Basically, this has become mainstream. The one I showed it to you is not, in terms of part one, part two. Part one, in the US, this is quite common now. Almost close to 90% or close to 100%, they're all using 3D already. And machine learning, all of those been utilized. But in terms of the one quality control in the US now, it just happened to check the quality because they recognize there's a lot of issue in quality. But in terms of the performance indicator, just happening now. Because in the US, even they just use in a way, the old-fashioned way. But haven't thinking about how to create a value. So this is something still a very big opportunity there for us to create a value. As earlier I mentioned about in just one state, Florida, it's $1 billion payment researching every year. If I can cut down 5%, I can easily save $50 million per year. So there's a huge amount of opportunity on that. And how do I use that? Precision maintenance. I think we calculate with Florida DOT, you can easily, based on the data I have, to create just the raveling itself. If you put in the right treatment in the right location and the right timing, you can easily cut down $17 million for them easily. I think we go through that exercise. And just using the new data with much higher granularity. That's it. With that, I think I stop here to answer any question you may have.
Thanks, Professor Tsai. And now, please, join me welcoming Professor Leif Sjøren. Sorry for my pronunciation.
Okay.
Is going to present, to speak about the importance of road surface characteristic references and quality assurance. Leif Sjøren is a senior researcher at VTI, the Swedish Road and Transport Research Institute. Currently, he is part-time retired. The floor is yours. Thank you.
Thank you. Okay, so I will talk a little bit about the importance of reference equipment or references when doing condition measurements. So, I mean, roads is the most important infrastructure that we have. So, and as we heard earlier, it's a lot of money involved in roads and infrastructure, and especially in maintenance and doing maintenance at the right time. So we can say that what we look on when we do maintenance and maintain our roads is the functional performance, but also the technical performance. The functional performance, I mean safety, vehicle operating costs, ride comfort, environmental impact. But normally and traditionally, at least in Europe, it is the technical performance or the technical conditions that we use when we decide on maintenance. So the technical performance that is today indicators for evenness, transverse and longitudinal. And the idea is that if we maintain the technical performance, in the long run, the functional performance take benefits of this. So it's important to remember also that there are different types of damages to a surface. A lot of damages is acute, local damages, potholes, and even cracks. And they are probably needed to be detected in the short term, almost daily operations repaired. But then we have the long-term or more damages depending on the aging. So as I said, it's at least in Europe today, it's the evenness, transverse and longitudinal, that we are using for the long-term planning. Despite there are a lot of different road surface characteristics, all of them are involved in having good references when we decide on their quality. So, and just a traditional graph showing that longitudinal evenness is very important for a lot of functional performances: vehicle operating cost, safety, ride comfort, and environmental impact. And for the long-term planning, we use mainly some deterioration models, and they are mainly based on for the road condition. It's the transverse and longitudinal data that is used. HDM4, Austria roads have a new model, and we have models in Sweden for rut depth evaluation that we use in the long-term planning. So the deterioration models needs to be updated because they, they have to be up to date and meet new constructions, possibilities, new materials, and so on. So they continuously need to be updated with new data, and a deterioration model is always built on historical data. And you need at least 3 points in time to create a trend. And in road management, this probably means 3 to 6 years before you have 3 times in time that you can use, make good use of. So this is one part of why references are good, and you need, probably you need a very, very high quality of the data. Is it reliable and available when needed? And with reliable, I mean repeatable. If you do repetitions on the same spot, same conditions, do it give good enough repetition result? And is it reproducible? I mean, if you use different equipment that say they can do the same indicator, do they look similar? And also, for now I'm talking about the reference durability. I mean, how long is it stable in time? Can it be replaced? So there's a number of quality aspects of references and indicators. The need for have know the resolution of reliability of the indicators. And I don't go through this, but it's so many error sources existing, and have you really looked on all of them? I mean, the data handling. I mean, maybe we are very good at the technical detection. We can detect a crack or a longitudinal evenness, but can the company deliver the data to the user so the user really can use it? So, as I said, requirements on collected data for pavement management is they need to be objective. We don't want to have subjective ratings. Reliable, I mean repeatable and reproducibility, and sustainable. A reference and a data must be stable for many, many years. We cannot change too often because then you are lost. And this is just to show examples of the needed resolution today, or possible resolution, I should say. If we look in US, it seems like for longitudinal roughness, in the IRI index, 0.1 millimeter seems to be a resolution they use, demand, require. Or for rut depth, it's 1 millimeter. In Sweden, I know the rut depth development is around 0.5 millimeter to 1 millimeter every year. So that's also set the requirements of resolution. And at the bottom, I hope you see, in the ARPAG organization, we once had a competition who in Europe have the most smooth road, measured or indicated by IRI. So a number of countries delivered a longitudinal profile of 2 kilometers. And we calculated the IRI with the same software. And you can see here, it's really smooth roads, 0.4, 0.5. So I think the traditional scale with the IRI is, we have higher requirements today. We also have limits in Sweden. For instance, we have a maintenance standard with limits based on number of traffic and the design speed of the road. So it's important, this is some note, if you do not measure results, you cannot tell success from failure. So, I mean, it's important to measure. And as someone said, it's a lot of equipment out there, and if you have many equipments, you have many results. Skip this, we can go to verify if we have a reliability on measurements of indicators, we do tests. And this is, I just picked up what they presented in US. They have 3 types of tests: static performance, body motion test, and a typical highway test. And our experience is that the static performance, it's important, but it's not for the procured organization who wants measurements, doesn't need to look on this. This is more for the manufacturer to check if his equipment have the static performance it one should have. And it's the same with the body motion cancellation, for instance. But very important for a road user who buy the measurement is to do the typical highway test. Now, what is a reference equipment? I just threw down some ideas. And a reference equipment means a unit of equipment which has documented reliability and can thereby serve as a basis for certification of related equipment. In that sentence, I didn't take in the resolution, because that's the big problem. Can you really do a reference system that has better resolution than the equipment it should test? So that's a little question. But also it's important that it's standardized and stable for many years. Can leave this typical highway test. You need a number of test sections of a certain length. You should measure them with the reference equipment, and then, compare the tested equipment with the reference results. You should use different speeds and things like that. So it's very important to select good test sections as well. And this is an example of a reference equipment we use in Sweden. It's a trailer with 7 scanning lasers. So we have a very high resolution transverse profile. And we move slowly forwards to collect single transverse profiles. And this is just an example of a LiDAR system that is tested against this reference equipment. And the top figure is the transverse profile, and you can see that LiDAR seems to be very, very good. So reference equipments are needed to support the long-term stability and certify reliability. And long-term monitoring needs high quality and reliable data. Sometimes you can hear it's not so important when you do the long-term measurements, but I think they are much more important that you have high resolution, because you create the trends and the error. You accumulate the error if you And also, one important thing with the reference equipment is that the ground truth is impossible to measure. It's too costly. Nobody do it. So we need to define reference equipment. And now, also for crack, as you talked about earlier, it's very difficult with the reference, but also for new intelligent vehicles. It's a very innovative and interesting matter, but they are not built to measure road condition used for pavement management. So that's a problem. And for intelligent vehicles, it's the manufacturers who are setting the rules. And of course, there are different intelligent vehicles companies, Volvo, Saab, or Mercedes, and so on, and they all are different, so there will be many equipment and many results. So therefore, I think reference will be even more important. And I represent AirPag organization, and we are now, creating a benchmark test next year, and where we will use reference equipment and do testings. So I finish there.
Thanks a lot. Thanks for your presentation. And now please join me in welcoming Francisco Rebelo. Use of fiber optic sensors in pavement condition monitoring. Francisco, the floor is yours.
Thank you. So first of all, good afternoon, everyone. My name is Francisco Rebelo, and I'm here to present the work that I've been developing on the last months together with my partners, entitled Use of Fiber Optic Sensors in Pavement Condition Monitoring. To start by the structure of this presentation, I'll begin with the motivation and the framework of this project, this activity. I'll then speak about the FBG sensors technology, the calibration of the measurement systems, as well as their installation on a physical model. Another important aspect is the real-time monitoring. The last stage will be the installation on a real highway section, and to finish, the conclusion and the work in progress. As we know, pavement engineering is currently facing a series of challenges that is directing its area of actuation to developing new strategies for designing and the monitoring of pavements that are more connected to new technologies and also at the same time more sustainable. Those were the challenges that motivated the appearance of this project, the app PAV 4.0 LC, which means life cycle, that is included on the PPS 3 from the mobilizing project Revet Construction here in Portugal. Our main goal with this project is the digitalization of road pavements as an asset. This transition will allow us to get more information in a more accurate way, and also to eliminate some errors that are frequently associated with the human activity, most of the times linked to the maintenance routines and maintenance actions. The goal with this project is to create a digital monitoring app that will allow us to monitor in real time some data about the pavement, namely temperature and strains. Then the collected data will be analyzed using machine learning methods that will be then, this data will be then used to develop pavement behavior prediction models. We think that this will be a valuable tool for the highway managers because with this information they can have a better understanding of the state of the pavement, and they can predict and schedule maintenance routines more effectively. The first step was to do a literature review about which type of sensor we were going to use. We selected optical sensors with the FBG technology. These sensors present some advantages in comparison with the most conventional electrical sensors that are strain gauges. This type of technology is resistant to harsh environments when properly protected, which is a very important aspect. They are flexible, they present high frequency, they have a small size, which makes them less intrusive for the pavement. They also have high precision and sensitivity. They also present multiplexity. This means that we can have dozens of sensors on the same cable consecutively. And they also have immunity to electromagnetic fields. On the middle, we have a small representation of the structure of an FBG sensor. Basically, some markings are made on the fiber core. Then those markings will change the optical properties of the sensor, namely the wavelength. Then when the sensor is stretched or compressed, the wavelength will vary and in according to that stretch or that compression. Then that variation will be read by an interrogator that will transfer or that will translate that variation into strain and temperature. From the research that we have done, we identified some of the main challenges that we were going to face. The first one related with the limited information that we had about the use of this type of technology in continuous monitoring on pavements. And also another big issue, it was related with the difficulty in assuring that we have a correct transmission of the efforts between the pavement and the sensors. And this means that the sensor is effectively reading what the pavement is verifying. Since this technology is not very well known, at least in this context, the first we needed to proceed to the calibration of the measurement systems. On the first phase in a laboratory context here in the Universidade do Minho. Here we performed some 4-point bending and wheel tracking tests to study some parameters like temperature, like the gap filling materials, the different types of FBG sensors that we can have, and also the positioning of sensors, and at last the use of fiberglass rods. Below we can see some of the specimens that we prepared in slabs and also on beams. Here I present some of the results that we got. The first one related with temperature. Temperature is a very important parameter when dealing with FPG sensors. For this test, we just put a simple beam completely at rest, and we reduced the temperature from 25 to 15 and then 5 degrees. The last curve at orange represents the strain without any compensation, and the top curve at yellow represents the strain with both of the temperature compensations done, because temperature requires to do one compensation for the material to which the sensor is glued or it's placed or is inserted, and another compensation for the material of the sensor itself. And as we can see, the difference is pretty significant. We also studied the importance of the sampling rate. This was a test that was done on beams on a 4-point bending machine. And we, since we are dealing with very high measurements, dynamic measurements, we compared the results of using 500 samples per second as a sampling rate, or 50 samples per second, and the results are demonstrative that the influence it's pretty big. And for our use, we will probably need 500 samples per second, or even 1,000, that is the maximum capacity of this technology. We also tested the use of fiberglass rods, this time on slabs. On the graph, we can see the blue slab. It has a fiberglass rod with a sensor inside. The orange curve represents a slab without the fiberglass rod inside. Despite having different levels of strain due to the circumstances of each slab, the average amplitude on each cycle was more or less the same, so it was in accordance with what we wanted. Another very important aspect of our work in the laboratory context was the study of the gap-filling materials for 3 different reasons. First, because this material had to assure us that it would not affect drastically the properties of the bituminous material. It also had to assure that it would protect mechanically the measurement system, and also to not compromise the transmission of efforts. For this task, we chose 3 resins and 1 mastic. Then the procedure was basically we selected 8 beams, and we tested their stiffness modulus. Then we cut them in half. We made a 1 centimeter joint with each one of the material, and we tested the stiffness modulus again to see at what point each material could reduce the stiffness. The first material, Kini resin fix, proved to be to have a stiffness reduction very, very low of just 5%. We continued the test of the gap-filling materials, but this time with fatigue tests. We used the same beams that I talked to you about previously, and we compared some fatigue tests of those beams with the 1 centimeter joint with a beam without any joint. So we had some materials that had great results, some not so good, depending on the nature of the material itself. We also tried to study the gap-filling materials on slabs. Here the approach was to try different scenarios, different configurations. We tried to just make a small slot on the slab and to introduce an FPG sensor wrapped around in a textile fiber. We also tried to make a bigger slot and to introduce a fiberglass rod with a sensor inside, and we also tried to cut the slab in half, like we can see on the left image, and we made a 1 centimeter joint, and then we tested the slabs and analyzed the results. For the results that I just spoke, we compared the results that each of the gap-filling material gave us. There was one material that had a behavior very similar when comparing the slab with that joint and the slab without any joint. That was the Kinimar fix. And for that reason, this was the material that we chose to to use during the rest of the project. In the video, just a small footage of one of the tests that we made. Having some conclusions already drawn in laboratory, we had to increase the scale of application, and for that we used a simulator that it is located on the National Laboratory of Civil Engineering. This simulator, it has a known pavement section, and this way it was possible not only to validate the conclusions that we have drawn earlier, but also to do some calibration tests and to perfect some application details for the next stage. In the picture we can see the pavement section with the wheel on the middle, that it is the simulator. To explain the installation that I just spoke, first we have made a slot on the pavement with three different thicknesses of alpha centimeter, 1 and 2 centimeters. Then we put a fiberglass rod inside, we filled it with resin, and to determine what would be the minimum thickness required to ensure that we have a good connection and a good bonding between all the elements. Then we have chose the 1 centimeter thickness for the gaps. We poured the resin inside, and we have done some calibration tests with falling weight deflectometer and also with passage of other vehicles. In the video, we can see the process of pouring the glue. It's the simple part of the process. Now, another important aspect of this project is the real-time monitoring. This monitoring will allow us to get information about the vehicle speed, the lateral distribution of strains, counting of vehicles and axles, comparing loads versus strains, and also the temperature and the impact that it has on the strains that are measured. On the right side, we have a dashboard that we are planning, one of the dashboards that we are planning to use for the measurement. Basically, when the car passes over although at a very low speed, when the car passes over the sensors, the system will automatically measure it and give us the information about the number of axles, the temperature, and another type of information. This is still initial approach. Now the system is being developed. This is the last physical stage of the project. Here we installed the final measurement system on a real highway section here in Portugal, on the beautiful city of Vila Flor. Basically, we picked 2 highway lanes. We had 4 fiberglass rods profile, and each one of the profiles had 15 FPG sensors, and the other one had 7 FPG sensors for strains, and 1 on each of them for temperature. The criteria here for the architecture of these elements were the lane width, the width of heavy vehicles, and also the average wheel width of 30 centimeters, and this was the reason why we tried to put more sensors on the expected wheel path. To explain a bit more about the process of installation, I chose some photos. First we have the location, then we have the 4 fiberglass rods that we used. Then the slots were opened in the pavement. On the bottom right, the top right corner, we can see the slot made with about 14 centimeters depth. And we can also see the profile, the fiberglass profiles inserted in its position. On the left corner, we can see some fixation pieces that we also placed on the slot to prevent the fiberglass rod from moving when we are filling the slot with the glue or the resin. Then the resin was poured, and another very important task was the handling of the cables that were connecting the sensors to the interrogator and also to the manager of the highway's computer. And the last 2 pictures are the final result of the work that we done. Concluding, at this stage, we can say that the phased planning that we predicted and that we defined initially, it was a success because the conclusions that we drawn in each stage allowed us to guarantee that the next stage would go on without any big problems. Also, the laboratory calibration regarding the gap filling materials, it was very productive, and so far the results are proving it. The intermediate physical model also was very important because besides allowing us to validate the conclusions that we have drawn on the laboratory, it also helped us to perfect some details about the application that are very important in assuring the success of the measurements and the correct transmission of efforts. Now we are currently in the process of calibrating the system that has been installed with falling weight deflectometer and also with the passage of heavy vehicles. And we are also improving the method of processing the collected data and to take conclusions from that data. That's it, and thank you.
Thank you. The next presenter is Kazuya Tomiyama. Three-dimensional analysis of perimeter surface properties based on dual-tree complex wave theory. The floor is yours.
Thank you very much. Thank you very much, Professor Flatko. Good afternoon, everyone. It's my pleasure to be here. Today, I'd like to talk about three-dimensional analysis of pavement surface properties based on dual-tree complex wave theory. So, my presentation consists of 5 parts from background to the summary. The motivation of our research is based on the huge social demand for improving pedestrian zone in line with the government strategy called the Hokomichi plan. Hokomichi stands for roads for pedestrians. And of course, absolutely, we need to observe the barrier-free roads to be everyone safe and comfort. In the light of this background, we, pavement engineer or pavement itself, are responsible for its surface conditions in terms of the road users' safety and comfort. But unfortunately, meantime in Japan, there are no standard inspection or testing method and no maintenance standard as well. And the most important things we need to consider when we analyze the pavement surface condition on the pedestrian zone will be the difference of user flow. The user flow is quite different from the roadways in the pedestrian zone because they are, road users go everywhere. You know that we need to zone-based analysis method. So one of the possible solutions against this background is to use the 3D measurement technologies. As you may know, and Professor Tsai kindly mentioned, the 3D measurement technology has a great opportunity to create the value of the pavement asset management. It includes much information, and we can easily detect the localized irregularities. But on the other hand, we need to identify the information required or information of interest. And the physical properties of the surface need to be associated with the functional perspectives of the pavement surface characteristics. So in the light of this background, we try to apply the Weber theory to the 3D measured surface data. And it enables the effective and efficient data processing, and it could be diagnostic identification of wavelengths, location, as well as the direction. And finally, it provides clear and theoretical evidence for the analysis. So as you can see, the top right will be the 3D point cloud and the contour of it. And is it enough to just take a look at the contour, or can we identify the surface irregularities of interest? I don't think so. So let me show you a couple of examples in this presentation. Okay, so at the beginning of introducing the dual-tree wavelet, I'd like to share with you the basis of the wavelet. Wavelet is very simple. wavelet transform, the original signal can be decomposed into two kind of wave bands. One needs the low pass approximation, and the other one is detailed, a high pass detailed component. And by using the small localized wave called wavelet, the wavelet will be scaling and shifting. And this performance of the wavelet enables us to conduct the time frequency or space frequency analysis, enabling the multi-resolution analysis. And the basics of the dual-tree wavelet is the same as the conventional discrete wavelet, but the dual-tree wavelet introduces a complex wavelet and scaling functions for the wavelet decomposition series. It means the wavelet function and the scaling function involved the complex number as well as the real wavelet. This capability of the dual-tree wavelet make it possible to analyze the approximately shift invariant transform. This performance is quite powerful to decompose, especially for the localized regularities like step function as shown in here. And the conventional discrete wavelet has some shift variant. As you can see, the decomposition result is quite different between the transverse distance. Actually, the shape of the step function should be the same, because the original signal is quite the same shape of the step. In contrast, the dual-tree wavelet make it possible the shift invariant transformation, as shown in the bottom right. Okay, to prove this capability, this performance of dual-tree wavelet, so we conducted the validation study. And the first validation study is to check the accuracy of the measurement and transformation after the transformation using dual-tree wavelet. So we make a simple object by the precast block pavement, and this material are normally used in the pedestrian zone. And we intentionally change the block height, some of the block height as shown here. The assumed displacement was 5, 10, and 20 millimeter. And we measure this precast block by use of the laser scanner from the 4 meter away from the block. And simultaneously, we measure the ground truth using conventional manual methods using calipers and rod and level. And the 3D laser scanner, the performance of 3D laser scanner was scan density is 3 millimeter at a 10 meter distance, and the coordinate accuracy is less than 1.9 millimeter, and the number of scan points are 600 kilo points. And it's enough to distinguish the elevation difference we made. And what you see here is the actual, the experimental condition looks like. Okay, and the accuracy, we check the accuracy of the laser measurement, and as a result, the accuracy is less than 1 millimeter in the average. And please note that the definition of the height is different among the measures. Okay, and taking into consideration the difference of the definition, maybe the accuracy is no problem. Okay, so what you see here is the original contour measured with laser scanner. And you can clearly see the design grade from top left to the bottom right. And in this case, in terms of the road surface evaluation, the design grade is not so much interest. So we need to detect the irregularities or deflection of deformation of the pavement. So in case of the higher elevation, let's say the 20 millimeter, we can clearly see the difference of block elevation. But in case of the short height, the small height, we can not identify the exact location and the condition of deformation. Okay, so to investigate the wavelength concentration of the surface distress, we performed the multi-resolution analysis as shown here. This result is the example for the height of 20 millimeters. So as you can see here, the specific wavelengths indicate the deformation of pavement blocks. Specifically, the decomposition level 1 to 3 highlight the intentionally made pavement step. Okay, so we reconstruct only the wavelengths of interest, which is the level 1 to 6. As shown here is the result of the reconstruction. So as you can clearly see the deviation of the block from the plane. Okay, and design grade completely removed because we needed to. We interested in the pavement only distress. Okay, and another example is conducted in the actual walking pedestrian zone, and we measure the artificial manhole and root heaving. Okay, this is the multi-resolution result of the manhole, and the level 1 to 4 indicates the edge fault of the manhole. In contrast, the level 5 to 7 highlights the roughness or undulation of the pavement. So we reconstruct only the level 1 to 4 and level 5 to 7 separately. So we can clearly see the edge fault in the bottom left. The bottom left figure clearly shows the only edge fault, and in contrast, the bottom right shows the undulation of the pavement. And one of the powerful tool of the advantage of dual 3 wavelet is it can possible to directional analysis in the multi-resolution analysis. This is a simple multi-resolution analysis, but we can make we can focus only on the specific direction, let's say the longitudinal or transverse directions. Okay, so let's focus on the level 5 to 7 of the undulation of the pavement. We reconstruct only the longitudinal, longitudinal directions on top, and the bottom indicates only reconstruction of for the transverse direction. So we can clearly see the direction of the irregularities. So let me conclude my presentation. Even though we need to go through more deep insight, but we can get some findings about the wavelength characteristics, like wavy characteristics of the pavement surface in the roadway. And in the next step, we needed to, to make a relationship between the wavelengths and the functional output. It means the derivative characteristics of the pavement surface. In any way, the dual 3 wavelet is a powerful tool to evaluate the pedestrian zone in a zone-based measurement. And the wavelet is basically the efficient algorithm by means of the multi-resolution analysis. So it enables us to the efficient processing and effective analysis of 3D data, not only for 2D, but also the 3D data. And we can provide the theoretical identification and visualization of surface irregularities, as I mentioned in this presentation. So thank you very much, and muito obrigado. Thank you.
Much. Please, Marcia Rokia, sorry. is going to speak about traffic split deflectometers structure bearing capacity analysis in Portugal. The floor is yours.
Thank you. Good evening, everyone. This is the second last presentation for the day, so please bear with us for another 30 minutes. Well, first of all, I would like to thank Professor Paolo and Professor Elisabete for the hospitality. It was incredible. I think I lost count of how many pastel de nata I had in the last 3 days, so it was pretty good to keep us with the sugar and everything. Greenwood Engineering has been in the market for close to 30 years now, and traffic speed deflectometer has been in the market for more than 25 years. And we have been doing measurements all over the world. And this is a small snippet of some measurement campaign that we tried to do in Spain, but we also did a few measurements on the border of Spain and Portugal. And I will explain a bit or some interesting things that we found in that measurement. And I will also show some examples of what we have been done in the past year, which is not in Portugal, but in other applications and field. So this is a small overview. So I think some of you might know how the TSD works, but I will just show a small animation on the working principle and how it gives you the results for different pavement types. And then our own company has developed a viscoelastic back calculation model, which is compatible to the data made by our equipment. And we will also look into some of the results. This was done by Christopher Nielsen, and it was presented in TRB a few years ago. And we also used this model to be verified on an instrumented road in Finland, and verified we got a good correlation between the sensors that were buried in the pavement and also from the model results. And this was presented last year as well. So if you are interested in these papers, then you can contact me after the presentation. And the third point is the new high-resolution results that we have been looking into. This is an index that we created ourselves, and we are trying to look into the strain at the bottom of the top layer. I know that we have talked a lot about the surface characteristics in the last 2 days, but this will be a little bit different because we also gonna see a few examples of what happens under the asphalt layer. So this is just an animation. So a traffic speed deflectometer, it uses a Doppler lasers to measure the velocity, and it's mounted inside a customized trailer. And we have an external load of 10 tons on the rear axle, so it's 5 tons on each side. So we kind of push the pavement and see how the pavement reacts. And the scale at which we are looking at is around 1 millimeter, so it's a very small area that we are looking at. And the velocity that is picked up by each sensor, it's divided by the driving speed, and this gives you the slope. So basically the slope is like kind of the raw data from our equipment. And when you integrate the slope, then you get the deflection. And the deflection gives you more information to the pavement characteristics. Yeah, and we also calibrate each lasers on the road. And so as you can see, the green curve is the slope curve, and then you integrate and you get the deflection ball. And depending on the stiffness of each layer, the deflection ball is different. And we started putting lasers behind the rear axle so that we can also measure the viscoelastic effect of the pavement. As you can see in this example, the first one, if you know the falling weight, the maximum deflection is in the middle of the rear axle. You can see that if it's like a soft asphalt layer, then the deflection bowl is quite sharp and steep. And here you can see an example where there is an asymmetry. So the maximum deflection is actually behind the center of the rear axle. And this is a tool that is useful for most of the people who are here, who are pavement engineers, and also for road authorities, and they are our clients. So we are trying to integrate other systems with the TST to give more detailed information about the whole pavement structure. So, like I mentioned earlier, we also try to incorporate the GPR data. So the GPR gives you the layer thicknesses for each layer. And we take into account these two systems data, and then we use our own model to calculate the E moduli for each layers and strain at the bottom of the upper layer and at the top of the bottom layer. And we also take into account the Federal Highway Bells model to do the temperature correction E moduli, and from that we can get the fatigue life and rutting life depending on which standard they are using. In the past few years, of course, falling weight deflectometer has been in the market for many decades, and they are completely two different experiments. And we are trying to use this back calculation model to give a data that is compatible for the historical data that was measured by the falling weight deflectometer. So we also have a module that gives that. So this model, it takes into account the rear axle of the trailer and also the rear axle of the prime mover or the truck. So it creates a 3D deflection basin. As you can see that the measurement also has an impact from the rear axle of the prime mover. And so this creates a 3D simulation of the data that is made by the Doppler laser. And for this, you need information about the pavement as well. And that's where the GPR comes into place. This was the measurement that was done. It was 10 kilometers, and we did 2 runs. And we got the GPR layer thicknesses for each layer. And we were able to identify a specific section where you can see that the slopes looks normal that we can see from the simulation that we made earlier, but you can see that there is something happening with the GPR. And when we did the model, it was giving an example of an unusual E moduli in the sublayer, in the base layer. So this is where we kind of give this information to the client, and they will try to, because they are the pavement experts, so they will try to come up with what could be the reason behind it. So our product is like a tool for the pavement engineers and the road contractors to come up with the conclusion and suggestions. The latest thing that we have been doing is to simplify and use the simple plate bending theory, and then with this we just concentrate on 2 sensors and take the slopes from these, and we take the difference between these 2 slopes, and this will give you information about the strain at the bottom of the top layer. And this is like raw data, and this can be at the interval of 5 centimeters, and you don't need any models to integrate, and this is very useful in cases as stiff roads. So some examples that we found, so we tried to do the same runs, and you can see they have a good repeatability, but this was an interesting example we found out. So from the surface, you cannot see what's happening, but when you look into this SCI TST index, then you can see that there are peaks at equidistant position. And then when we compare with the radar data, you can see that they have the shape of a pipe every 20 meters. And then we contacted our client, and then they said, yeah, but we couldn't see anything from the outside or from camera images. But you could see that there are 2 agriculture fields, and then they have used drainage pipes, which is like 15 centimeters from the top of the asphalt layer. So this is something that they have to look into and see like how much damage it can create in their pavement. And this will help the client to rehabilitate or to look into it. In the last few years, one airport authority or maintenance company, they came to us and asked that we had a localized problem and we had to close down the runway, and it costed us $2 million. And we would like to see in beforehand and to predict and maintain our runways. And this came to us where we started measuring the pavements. And here you can see that we made runs. We drove the truck every meter for the whole span of the runway. And then we collected around 200 kilometers of data in a 3-kilometer runway. And you can see that you can like map in 2D with the weighted function of the ACI TST. And this was used to find out a specific point. And here I can see that the scale is from 0 to 50 micrometers. But when you try to go deeper, and then you can see there is a discontinuity here. And this is a localized effect that is in millimeters. And this helped the client to rehabilitate that area. So this is something that is different from the conventional heavyweight deflectometer, where they have to stop the whole process of runway. And we use the TST in between landing and takeoff and then measure. So we measured around the whole 50 lanes on the runway in 4 hours. So this is something that we have been working on, and so there are 2 elements with the runways. One is with the maintenance part, and the other one is giving a standard rating. So we are working on this part at the moment, and this would be something that will be presented in the future. An interesting part we did was we measured another runway where we did surveys with the gap of 2 years. We measured in 2020 during COVID, and then we measured 2 years later. And you could see that the E-moduli of the subgrade layer, it was weaker at the bottom of the screen, and then it was stronger 2 years later. And we were quite astonished on how much it made a difference in 2 years. And then we asked the runway maintenance people or the authority on what happened. So they said that in 2021, when there was still not a lot of traffic in the airport, they started looking into the drainages next to the shoulders. And they kind of rehabilitated the pipes, and they found some leakages, and then they kind of came up with a conclusion that this could be because of the moisture content. There was a lot during the 2020, and then 21 they rehabilitated, and you can see in the results that the stiffness increased. And this is, I know, one of the nemesis of pavement engineers, to have water in the pavement. So we can help in some cases in finding it out. So as we discussed earlier about data, and a lot of talk in the last few years about big data, 3D data, AI, and machine learning, data is not valuable if you cannot give a story and if you cannot give a value to the data. And this is where we are trying to give you a tool, and it's in all of our hands to interpret and give a story to the people and to make it useful. So we can use the traffic speed deflectometer to do a network level data analysis, and then filter out the areas, and then do a project level analysis with these indices. And you can always cross-verify the results from the TST with the other subsystem, like what we did in GPR and the right-of-way camera. Thank you very much for your time.
Excellent presentation, Marshall. And now, please join me in welcoming Professor Pai, who is going to speak about the evaluation of a low-volume unpaved road. Professor Pai, the floor is yours.
Thank you, Philip. Okay, good afternoon, everyone. This is a paper outside of the box. We have asphalt pavement, road pavement. This presentation is about unpaved materials. It's not from me, from my group. It's from colleagues of mine from the Polytechnic University of Bragança. Manuel Minhoto and Miguel Paulo cannot be here, so they asked me to present this work. So the objective of this paper is to evaluate the performance in terms of structural properties and functional properties of an unpaved road. And in some parts of not only in Portugal, but in countries like US, the unpaved roads play an important role for the entire road network of the country. For example, I remember in US, more than 50% of the roads are unpaved roads. And they are not inside the cities, but outside in ecological and agricultural zones. We have a lot of unpaved roads, and it's very important to have efficient roads, and its evaluation in terms of structural and functional properties is extremely important. So this work deals with this evaluation in terms of structural and functional. And my colleagues from Polytechnic University of Bragança did some campaigns for this two types of evaluation. Here they have three results from functional and two for the structural evaluation. So I'll try to present it. If you have questions, please, I'll give you the emails of my colleagues and I'll address any question. So this is the location of the unpaved road. Is at northeast of Portugal, extremely close to Spain in a national park. And the road is important because it connects to dams that supply water for an important part at that region. The altitude of the road is around 1,200 meters. So the climate condition in some times are very bad and influence the main structural behavior of this road. So the length is 3 kilometers, as you can see. So the objective was not to define a method for the evaluation of the condition of the road, but to verify if a method that in Portugal we don't have any method for this type of evaluation, but for example, in Brazil, they have one, and one of the students that work in this project, apply it, and one of the main objectives is to verify if that method can be applied and if it's easy, and how we can analyze the results and to verify the efficiency of this method. This method is presented in this Brazilian standard that define a global index for the condition of the payment, and based on the condition we have a quality for the payment from excellent to very bad. As the global index increase, we are decreasing the quality of the payment. And it is based on the evaluation of the payment condition for a small section of 6 meters, and it is evaluated every 100 meters, as you can see here. And what we evaluate is the absolute frequency for each distress or each problem that we have in the payment. So for each problem, we evaluate the frequency that problem appear in the payment, and if we sum all these frequencies, we have the global index for the payment. So as the index increase, meaning that we have a much more frequency of the problem, we are decreasing the quality of the payment. For the structural evaluation, the method evaluate this distress that we have in the first column of this table, and the problems range from correlation, potholes, eroding, groves, ravel, dust, and the method define how we evaluate this property, and for the different severity levels, and for each one there is a weighting factor that is used to quantify the importance of this problem or this stress in the global index. So this is the severity level or the distress types that are used in the method. In terms of drainage, that is extremely important factor for the unpaved roads. The method define this type of problems since incorrect transverse slope, inappropriate shoulders, drift, culvert, no drains, and so on. And for each one, we have the severity labels and the weighting factor as for as in previous one for superficial distresses. So here we have an example of the problems in the pavement, ranging from, and you can see rutting, groves, potholes, inappropriate shoulders, and inappropriate drains, and for each one there is a severity level that we consider and evaluate the frequency of these problems, and if you multiply by the weighting factor, we have an index for this problem, and if you sum all the partial index, we have the global index, and they put in this presentation the results for 2018, 2019, and 2021, and you can see that in some cases the quality increase or decrease, but you can see in the next slide. They did the same for drainage. I think here, Okay, they put also the results for 3 years, 18, 19, and 21, and the global index is the sum of all properties, and the evolution during the time can be seen here in this figure, and for surface characteristics, the properties, the quality decrease, and for drainage decrease. So sometimes they are not correlated one with each other, but as you can see, the global quality is very, very bad. At the global quality, they put also the results for the individual measurements, and we can see that there are points where the quality is quite good or regular, but we have also peaks with the quality is extremely bad. This is the same results for drainage, and they perform also the evaluation of the structural properties of the pavement, and they measure two main properties, the dynamic models and the dynamical CBR. This is the equipment for dynamic models, lightweight reflectometer. They use the same with a different plate for dynamic CBR. As you can see here they have photos of the measurement, and as you can see, the quality of the road pavement was not so good. And using these results of dynamic models and dynamic CBR, they calculate the cumulative difference to obtain homogeneous sections, and as you can see, in 3 kilometers, they have, in this case, 8 sections, meaning that the quality is changing very fast on the road, and the influence of the water, because the structural evaluation was carried out before and after raining. As you can see, there is a lot of points that were influenced by the presence of water, and mainly for the CBR, where you can see that most of the points, we have 30 points, meaning that we have 3 kilometers were influenced by the water. In fact, they have water. This is the waterfall that was verified before the measurements. The last study that they carried out was the comparison between the dynamic models of the soil and the CBR, mainly to compare with what we have in the design methods. And if you remember, the main model for this correlation was developed by Shell in Shell Pavement Design Met, where the coefficient that correlated the dynamic model with the CBR is 10. They got almost 4. Is a little bit far from 10 that we usually use for the pavement design. Using all the data they have in the university, not only of this project, but the other project, they got something like 5. Is quite good, because the the fiability of the shell equation, meaning that values between 5 and 20 are possible. So they are almost there. As conclusion, I have here a lot of conclusion, but the main conclusion was they verified that the method that are in Brazilian standards is very easy and quick for application in road pavement and produce interesting evaluations for unpaved roads. And probably the most important was last equation that correlate the CBR with the dynamic models. Now outside of the paper, let me present the next conference that we are organizing, MARIPAB 10. Most of you remember the MARIPAB 3. 20 years ago here in the university, in this auditorium, with more people. So I hope, and me, Paulo, and myself, hope to have you and most of the people that you know here in July next year. If you want more information, you can send me an email to me or to Paulo Pereira, but we have this site, MARIPAB 10, inside civil.umi.pt, and the email maripab10@civil.umi.p. Thank you so much.
So, thank you, George, for your excellent presentation, and also because you were in good time. I would like to say if there are questions, but probably it is too late. So we will have time, maybe during the dinner, to speak about the important topics that emerged from this very interesting session. So please join me in thanking again our speakers, and thank you.
Before leaving, please, the ones that would like to visit our simulator, please stay with me. I will take you to the facilities. And the ones that do not want to go, there is a bus in a few minutes outside to take you to the dinner place. It's 10 minutes away. So 7:30, there will be a bus outside, and stay with Professor Paulo Pereira. He will guide you. So for visiting the simulator with me and to continue and go to the dinner, please stay with Professor Paulo Pereira. And thank you for being so patient, and I'll see you at the dinner and tomorrow too.